Next, we have OSPF authentication and virtual link. So let's start with OSPF authentication. Now, actually, it's very easy to configure and it's different than RIP and EIGRP. What we can do, first of all, we can go to the area. So here you can see I'm over OSPF, I'm inside area, I am putting area 0 authentication. Then I can go to the interface level and then I can go and give the authentication key. So we have two things. We have the plain text or clear text, and then we have MD5. Now same way we can go and configure the MD5 as well. So again you have to go to area 0. Here you can see that I'm over area 0 here and the authentication message digest. Then I will go to the interface and then I can assign the message digest key. So it's very easy and straightforward. I'm going to show you in the lab section about the message digest key, this authentication. So more we can discuss in the lab. Now next thing here is what about virtual link? Virtual link is again one of the use case we have in OSPF, that for example, due to any reason the customer network, they are not able to directly connect with area 0. We know that all the areas should be connected with area 0. So suppose you have area 1, 2 and 3. For example, later due to some reason you are connecting area 4 with area 3, not with area 0. So in that case we can create the tunnel in between area 0 and area 4. So the router inside area 4, they will think that I am part of area 0 or I am directly connected with area 0. And that's the concept of virtual link. Again, you will see the configuration here. The configuration you'll find it's a very much like we are creating that tunnel. So router, the area 1 is working as a transit, and then I have tunnel in between, say for example, area 0 and area other area. So let me go back here. So here you can see this is the classical example that you have area 0, area 1 and area 2, and then you are creating the virtual link in between that. Okay, now there are possibility that you may have area 0 and in between you have area 1, and that's again the possibility is less, but still you can create the virtual link in between that. Now once we create the virtual link, then over the area 0 we have put the message digest. So same key we can put over virtual link as well. Okay, so we have seen all these steps, and let's perform the same task in the lab setup. So we'll understand more about the authentication and the virtual link. Let us perform the lab related to authentication and virtual link. I have done the change in my setup. Here you can see that now we have R1, R2, and that's R2, but switch 105, then switch 101, and then switch 102. So R1 switch, and then again switch, and then the switch 102 in the bottom. Subsequent network IP addresses I have changed. So we have network 10.1.1, 10.1.2, 10.1.3.0. And then we have respective area like area 0, area 1 and area 2. Now in lab number 1, we'll go and create or run the OSPF in between area 0, and then we'll do the MD5 authentication. In the same lab later on, we have to create the virtual link and we have to make area 1 as a transit. Alright, so let me show you this IP addresses assignment here. You can see that we have created and assigned the IP addresses only so far as per the diagram. So these are the IP addresses assignment related to R1, R2, related to R1 and all the switch. So now let's start with area 0, that is R1 and switch 105. I'll go here and enable router OSPF 1. Then I have network, say for example 11111. and then I'll put this inside area 0. So let me do that. Then I have network 10.1.1.0. This also I'll put inside area 0. Alright, now we'll go to the switch, that is switch 105, and we can go and check the network. First of all, we'll go and initiate the Ospf process. Then we have one network, that is 10.1.1.0, but we have 105.105 network as well. So let me quickly do that. And 0.0.0.0.0 area 0, for example. Then we have the rest of network. So now you can see I have enabled this, or I ran this command, but still I can't see that Ospf is coming up and running. So I should go and check the IP over E00, and we should have at least IP reachability. So E00 here, it is correct. If I go and check the interface configuration for this switch, so let me try to check 0/0. Wow. So we have this command configured and protocol is up. So if I do the ping, so let me do the ping from here for 10.1.1.1. That's the router IP. And I can see that ping is working. If we could go and check show IP Ospf neighbor, show run section Ospf. So here you can see that I have this network inside area 0, and then I have my network, that's the loopback, but still I can see that they are not forming the neighbor relationship. So now what I'll do, I'll go here and make this network as a 10.1.1.0 area 0, and then I'll remove this network statement. You can see that the problem here we have. Then again I'll go back and delete this and add this. So let me try to do both at a time. In router number 1. Okay, and let's try to check. Show IP Ospf neighbor. Now they are in two-way dweller state. They're stuck in dweller state. Alright, and if I go here and check in this, because we haven't removed Ospf from here, show IP Ospf neighbor. Okay, so the reason may be now it is up. Maybe the network type that we haven't changed, but now it is showing it is up and running, so that's okay. Now we have the Ospf relationship over area 0. What I want to do now, that I want to run the authentication. So I can go to router Ospf 1 and then area 0 authentication. Here you can see that you can do plain text if you want. You can leave with this authentication, or if you want to do the MD5, that is the more secure, then you can go and use this. Now at the moment I have done this, you can see that the neighbor is up, but we are getting one problem here, that authentication key, you don't have any valid key. So now what I'll do, I'll go to 00 and then IP Ospf authentication. You can see that you have authentication and message digest option. So I can go and put the key as a CCNP. You can see here that you can go to authentication and key, and then you can see here that you have option say unencrypted. This is not that I'm looking for, so I can go and give the message digest, but I want to put the key as well. So let's see, IP Ospf authentication, and we can give the authentication if it is a plain text and authentication key. And suppose if I'm using authentication, then I have this option for message digest. Actually, that is quite a confusing option that Cisco is giving to you. So, because obviously natural thing is that we'll go and check IP/OSPF of authentication, and then whatever authentication will be there. But in case of message digest, you should go and check IP/OSPF, and then you have this option of message digest key if you want to put your key. So I'll put key as CCNP, but let's see, yeah, MD5, and then so this is the long command that we need to put here. Now if we go and check show IP OSPF neighbor, we can see that neighbor is down because of mismatch of the, or we don't have the key configured to the other side. So here also we can go to router OSPF1 area 0 and then the authentication message digest, and then we'll go to interface E0/0 IP OSPF message digest key. Now we are getting this error MD5 CCNP. So now you can see that the neighbor is coming back up. So this is the way that we can go and do the authentication inside area 0. Now what I want to do here, that I should go to the I should first of all do the OSPF rest of the configuration, and then we'll create the virtual link. So let me do that. R1 is okay. In R2, let me check show IP route and what network that we have configured so far. So we have router OSPF1. We should have one more network, that is 10 dot let's see the network. That's 10.1.2.0. So 10.1.2.0 0000255, and that is inside area 1. Correct? So this network is in area 1. Now we have switch number 101. So let's do the configuration for switch number 101. And what network we have? We have network 10.1.3.0. That is in area number 2. Then we have network say 101, 101, 101, 101. So for example, I'll put this in area 1, and then finally I have 10.1.2.0 that is inside area number 1. Alright, so we are very much done with this OSPF configuration. Finally, we have switch number 102, where we have 10.13.0 network. So I'll go here as well and should enable OSPF, and then we have network. Say for example, first of all I'll advertise the loop back, and this is inside area 2, And finally, we have network 10.1.3.0. That is again inside area number 2. Now here you will see that after running all these commands, we go and check show IP OSPF neighbor. So he has neighbor that is 102 and 105. Now if you go here and check to the switch 105, you will find show IP OSPF neighbor. So he should also have two neighbor, but if you go and check show IP route for OSPF, you'll find that he is not getting 102 because it is never getting tunneled or passed through the area 1. So in this case, we should go and create the virtual link. Okay, so let's create the virtual. So I'll go and create the virtual link here inside area number 1. So first of all 105 and then 102. So already we are here and router OSPF 1, area 1, and then the virtual link. What is the ID? So we know that the neighbor ID is this. You can see here that we have option for message digest key as well that I'll put later on. But that's it. Area, virtual link, and then the peer device router ID. Now I'll go to 101. I'll go here and router OSPF 1, area 1, virtual link is what's the router ID you're looking for to make the tunnel. That's sorry, not this one. This is 105. Okay, so I'll go and remove this, and that's it. So once you do this, then if you go here and check the OSPF, you'll find that you will start getting the routes. Now, what is happening here in this case that since you don't have key configured, so inside area 0 we have the key configured. You should go here and give the key so it will work properly. Go here and here also we'll go and we should give the key, say CCNP, and now you will see that they will start getting the routes. So if I go here and check show IP OSPF neighbor, now show IP route OSPF, you should get 102, 102, 102. That will be the final valid verification for this. So after running this command, I can't see that anything is happening. And let me go and check here as well. You can see this configuration is 100% correct. You're creating virtual link with this, and in router 1 also the configuration key, everything is correct, but it's still they are not forming this. So what we can do here, that we can go to router OSPF one more time. Router OSPF 1, area 1, say for example the authentication is message digest. This belongs to area 1, and here also we have area 1 as well. Let's see the final configuration. SPF. Now invalid key for 10/0, that we can verify. So what is happening actually here, that if you go and check the configuration, you'll find that once you are putting the key here over the virtual link, now this belongs to inside area 1. These are the interfaces where you have to put the authentication key. So for example, as a MD5. But when we are creating the virtual link, actually, in that case, that is going to propagate area 0 only. So it's not required to put the key there. Okay, but just for the uh, security purpose, I'll go and put the key over 10/0 and E1/2 as well. So E say 10/0 and IP Ospf, or maybe IP, yeah, Ospf message digest key 1 MD5 CCNP, correct? And then finally I can go here and interface E2/1/2. Wow. So this much configuration we have done. And now if you go and check show IP Ospf neighbor, first of all, we should have the neighbor. And if I go to R1 and if I go and check show IP route, so here you can see that it is getting the route as a O routes, as it is directly connected with area 0, and we don't need to put actually authentication over the area 1 interfaces that I have done, but for sake of security we want to put the authentication key at all the places, so you can go and put the authentication keys at all these places. Alright, so this was the authentication. And the next important section, we have Ospf summarization, different type of areas, and the default route concept. So let's start and understand the summarization. Now clearly you can see in the diagram that you have area 0 separated by area 1 and area 2. And for example, if you're getting routes, say 10, 1, 0, 0, 1, 1, 1, 2, 3 up to 7, and other side you can see that is 8, 9 up to 15. Now we are sending all these routes to the core router. Here you can see all the individual route, and hence the database or the topology table of the inside the area 0 will increase. Rather than what we can do, that we can summarize the area 2 as 10.1.8.0 and area 1 as a 10.1.10/21/21. Correct? So in that case, we are sending only one update, and our routing table will be efficiently utilized. Doing so, we can reduce the load over the router CPU. So this is one of the interesting use case we have with inter-area Ospf summarization. Now what's the command? Command is very easy and straightforward. We can go to the router, and over the router you can go to the area, and then you have to use the keyword called range, and then you can use the address and the subnet mask, and then this will be done. Now there is one important point to mention, that suppose if you have some of the routes in between that is not part of subnet. So for example, if I don't have 1.5, 1.6, is still I am using this summarization, that is 10.1.0.0/21. So in that case, what we can do, we can use the concept of static route null 0, and we can point out this summary route towards null 0. So that means that anything that is not matching, that will be garbaged, that will be bit bucket. Correct. Now here you can see that note that after 12.16, and now we are running the modern or advanced version of operating system, even this command is not required. It was required for the earlier version of iOS. Now the second point related to summarization we have is, suppose if the summarization is coming from the external system, it's not related to inter-area routing, but it is coming from outside. Now at this point of time, we should go to the ASBR. Suppose router B is ASBR, who is connected with non-OSPF domain or non-OSPF routing protocol. So in that case, you can do the summarization, but syntax will be little bit different. So in this case, instead of doing area, the command is summary address and then the network and the subnet mask, means whatever network we want to summarize. Correct. So now this concept is very much like we are doing the aggregation, and we have two type of border. We have ABR and we have ASBR, and like that we can easily do the summarization. Now here you can see that we have one use case in case of ASBR summarization, that if you don't want to advertise certain prefixes. So in that case, you can go specifically to that particular network and you can use the keyword called not advertise. If you use not advertise, obviously these networks will not be advertised inside the OSPF. Okay, so this is the concept related to summarization. Now next important concept we have is the OSPF area type. Now I have one summary chart as well where we can go and summarize the OSPF area type after a few slides. So here you can see that you have area type called backbone, non-backbone, stub area, totally stubby area, and not so stubby area. That is NSSA in short. So let's learn and discuss about the area type. Now starting with the basic area, that is the normal or the standard area. We know inside that area we have LSA type 1, we have LSA type 2. So here you can see that we have all the LSAs inside the standard area, say type 1, type 2, type 3 and 4 generated by ABR. Then we have type 5 as well, that is generated by the ASBR. So it is able to understand all the LSA. That's the standard area. Now the second thing here, that when you are making a stub, at the moment you will make the area as a stub, the stub will not accept type 3 and type 5. But remember, they will automatically inject the default route. Now doing so, while doing so, you can think like this, while doing so, we are cutting off the SPF calculation. And who is doing the SPF calculation? My CPU, my process. So that means that we are cutting off the intensive cycles, CPU cycles, and hence we are providing good type of optimization in terms of CPU and memory. Correct? Now what's the command? Again, the CLI command is very easy and straightforward. You can go to the network. So here you can see a router process. First go to the router process, and then you can go to area 1 stub. At the moment you do the stub, that means it will start stopping type 4 and type 5, although it will get router, network and ABR generated LSA. That is type 1, type 2 and type 3. And other thing is that it is generating the default route. Now the third concept we have is the totally stubby area. Now what totally stubby area even will do, that will accept only type 1 and type 2. It will not accept type 3, type 4 and type 5 LSAs, although it will go and generate the default route for type 3, 4 and 5 LSAs. Again, the use case is that we are saving the bandwidth, we are saving the CPU core, process cycles, etc. Now the command here is interesting, that here we have used in a stub area, we have used area 1 stub. For totally a stub area, you have to add one more keyword, that is no summary. So the command is area 1 stub no summary. It will stop LSA 3, 4, 5 and it will generate the default route. Okay. Now the fourth one is not so stubby area. Now, why we need not so stubby area? Here you can see that you may have chance that area 0 is connected with external network, or you may have chance that area 1 is connected with external network. Correct. So in that case, we'll see that when you have area 1 connected with external network and you want to filter some sort of LSA, you are going to use the not so stubby area. Means it's a stubby area, but it's not fully stubby area. What it will do, here we'll see that like a standard stub area, NSSA area routers will share type 1 and type 2 LSAs. Okay, they are not blocking type 1 and type 2. NSSA area will also accept type 3 LSA. So they are going to accept type 1, type 2, type 3. But NSSA will not accept type 4 and type 5. Okay. Now we are going to introduce one new LSA, that is LSA type 7, that we haven't discussed so far, but not so stubby area is linked with LSA type 7. And what's the use of LSA type 7? Now we'll see. So if an ASBR exists within the NSSA area, this is ASBR will generate type 7 LSA. Again, NSSA areas are almost identical to a stub area. If area 1 was configured as NSSA, it would not accept any external route originating from router G as ASBR outside area 1. So here you can see that they are not accepting any type 4 and type 5 LSA. Rather than we have type 7 LSA. So here you can see that it will not accept, this is the router G, it will not accept any external network, external non-OSPF domain network. Correct? Great. However, area 1 also has an ASBR within the area router A. Those external route will be flooded into area 1 as type 7. So here you can see that you have area inside area 1, you have router 1 and who is getting the external routes, and that will be flooded inside area 1. Now these external route will not be forwarded to other area as type 7 LSA. Instead they will convert it into type 5, and that's the key, and that I'm going to summarize. Type 5 LSA by area 1 ABR router C. So what is happening here when you are creating not so stubby area? In that case, you are getting type 7 LSAs, and router C, what he will do, he will convert type 7 LSA to type 5 LSA, and then it will flood it into the other area, or the other area will calculate as per the type 5 LSA update. The configuration is very simple. What you have to do, you have one keyword, go to the route process and then area 1 NSSA. Okay. All right, and final concept we have is totally not so stub area. So let me stop here, and remaining concept we'll discuss in the next recording. But here you can see the summary, and in this summary, let me try to highlight. Backbone LSA 1, 2, 3, 4, and 5. They are not getting LSA 7. Non-backbone like area 1, area 2, etc. They are also getting all the LSA. Stub area LSA 1, 2, and 3. Totally a stub area, only LSA 1 and 2. Remember, they are going to generate the default routes. The not so stubby area, type 1, type 2, 3, and type 7. This type 7 will be converted to type 5, and then it will be reaching to area 0. That's the overall summary we have with this recording. So let's stop here, and next section will continue from here. Let us continue where we have left off. Now next concept we have is not totally not so stubby area, that is TNSSA. So what is the main difference between a stub and totally a stub area? The same difference you'll find between not so stubby area and totally not so stubby area. Totally not so stubby area will allow LSA type 1 and 2, and he is going to filter type 3, 4 and 5. Here you can see the configuration is very straightforward. You can go to OSPF area and then you can give area 1 NSSA. The keyword is no summary. And here we have the summary just for your reference. Now the next topic we have is OSPF and relation with default routes. We know that when we are generating a stub area and totally a stubby area, at that time the OSPF process, they are generating the default route. But in case of ABR and ASPR inside a standard area, we don't have default route. Now suppose you are sending LSA type 3 from router C and you are expecting that you are getting say LSA type 5 from router 1. So you are getting LSA 5 from router 1 and it will go to router C and then other areas. Likewise, LSA type 3 will go to B and A and actually B and then A and then the external network. At that time, suppose for the external network, you want to create the gateway as router A, so we can go and create the default route. So here you can see that additionally force router A to generate a default route, including itself as the next hop for the external network and injects into this inside area 1. Okay. What is the command? Command is router process, go to router process and default information originate. So this will inject the default route. But in case suppose you want to force it, so for example, if a default route does not exist in its routing table, router A can still be forced to advertise a default route using always command. So in that case, if I want to force the default route, in this section it is assumed that we should know EIGRP and then the difference between EIGRP and OSPF. So let's understand about EIGRP. What type of protocol is this? Basically, EIGRP is Cisco proprietary. It's a advanced type of distance routing protocol or distance vector routing protocol. It is using dual algorithm. Its protocol number is 88. It is forming the neighbor table, topology table, and then the routing table. It's a metric basically based on bandwidth plus delay, but there are 3 other factors as well inside EIGRP. So let us drill down inside EIGRP. Now here you can see we have some points. I'll go through these points and then we'll discuss about a very interesting point inside EIGRP, little bit confusing as well. We have a dual algorithm inside EIGRP, that's the diffusion update algorithm that will ensure that we have the loop-free routing environment. We have to define the autonomous system for EIGRP. The multicast address inside EIGRP is used by as again the link local multicast address is 224.0.0.10 just to form the neighbor relationship or to check the neighbors. We are sending these multicast packets and hello packets. It is using reliable transport protocol to ensuring the delivery, and it does not send periodic update. It is supporting VLSM, variable length subnet mask as well, because this is the classless protocol. All right. Other points that its AD is 90, the external AD is 170. Its metric is heavily relying upon bandwidth and delay, but if you see that metric calculation, you'll find that we have 3 more factors: reliability, load, and MTU as well. In some of the books, it is mentioned that MTU is not part of bandwidth, but not part of metric, but Generally, most of the time, we are going to calculate the metric with respect to bandwidth and delay. Its max hop count is 224. Its default hop count is 100. Why hop count? Because this is distance vector protocol. Distance vector protocol generally depends upon the hop counts as well. They are going to form three table, neighbor table, topology table, and from topology table, it will run the dual algorithm and it will form the routing table. In EIGRP, again, we have the neighbors, and by default, the neighbor, they are sending the hello packets after every 5 seconds. And in case of slow link, the hello packet timer is 60 seconds. Likewise, we have the dead timer as well, or the hold down timer as well. Not dead, but the hold down timer. That is 3 times of hellos. That is 15 seconds, and again 60 into 3, that is 180 seconds. We have to configure, say by default it will be like this, but if you want to change the neighbor relationship per interface, you have to go to the interface and then you have to run this command, IP hello interval EIGRP, then the autonomous system, that is 10 in this case, and 7. Likewise, I have to go there and type IP hold down interval EIGRP 10 and 21. So 7 into 3 is 21. That's the hello interval and the dead interval that we can form. Now in the lab section, I will run that show IP EIGRP command, and I'll show you this output. This is something that once you run the neighbor command, or what will be there in the neighbor table. Remember, we have three tables. We have neighbor table, topology table, and the routing table. So in the lab, we'll check all threes in upcoming section. If you want to check the logs, you have the log command as well, like log neighbor changes, log neighbor warning. So these are useful command that we can run and check. Now I told you that we have an interesting concept inside EIGRP and a little bit confusing as well. So let's try to understand the feasible distance, advertised distance, feasible successor, feasible conditions, like that. Okay. So here you can see, let me read out this and then I'll show you in the diagram that all such routes are added to an EIGRP router's topology. The route with the lowest metric to each network will become the feasible distance. The feasible distance for each network will install into the routing table, that is nothing but the successor. So we have successor, primary route, we have feasible successor, that is the backup. Again, the feasible distance is derived from advertised distance. Now here you can see that you may get the terms like, say for example, feasible distance, feasible successor, successor, feasible condition, advertised distance, etc., etc. So let's try to understand how exactly it is working. Let us continue where we left off and try to understand the terminologies inside EIGRP. Now here you can see that in the diagram I have A, and to reach to destination network it is going via B, C, and D. Now for B, C, D, to reach to the destination, the feasible distance is 6 plus 2, 8, 9 plus 14, 23, 4 plus 5, 9. So these are the feasible successor respective to B, C, and D. But what about A? Now, if you go to A has to add his distance as well. So if you go and add, you will find that 8 plus 8, I think I have in the next slide. So let me go to the next slide. So here you can see that 8 plus 8 will become 16, then 23 plus 4, 27, and then 11. So obviously the 11 is the lowest one. So that's why in this direction he will get his successor, correct? So now I have my successor, but we know in EIGRP if you have multiple paths and if they will meet certain condition, then you have the backup path as well. That is nothing but feasible successor. So let's first understand the algorithm by which Eigrp is finding his feasible successor. So here you can see it is clearly mentioned that you have the feasible successor when if it met the condition, feasible condition. What is that condition? A route only become a successor if its advertised distance is less than the current feasible distance. Now in our case, we'll go and try to understand this statement. So in our case here you can see, and I'll write this here, the advertised distance will be less than the current feasible distance, correct? Let me erase, and advertised distance will be less than the current feasible distance. That's the statement to have the backup path. Now here, if you go and check, so already I have my successor. So it is marked as a successor. It will be installed in the routing table. Now searching the feasible successor or the backup path, if we go here and check what is the feasible distance. So here your feasible distance is 8. Here your feasible distance is 23. We are adding 14 plus 9. And what is your distance, advertised distance? So you'll find that your advertised distance total path is 11, correct? So now you can see that 8 is less than 11. So 8 is less than 11. That's the condition actually, correct? So feasible distance should be, in other words, you can tell that feasible distance should be greater than the advertised distance of your neighbor or via which path you are going. So because 8 is greater than, 11 is greater than 8 or 8 is less than 11. So that's why this is the feasible successor. That is not true in case of this path because this is 23, which is bigger than 11. Okay. So that's the algorithm that we can verify. I will upload this slide as well. Now the last thing here in these slides is that suppose if you have failure and if you don't have the backup path, so in that case the Eigrp algorithm rerun, it will move to active state. Active means actively it will try to get the feasible successor or the backup path, correct? All right, so let's stop here. Now we have Eigrp packet types and Eigrp metric value. In Eigrp, we have 5 different type of packet types. Here you can see we have hello packet, update, query, reply, and acknowledgement. Obviously, when devices they try to form the neighbor relationship, at that time they are sending and receiving the hello packets. The mode is multicast. They are using 224.0.0.10. That's the multicast address to send and receive the hello packets. Apart from that, we have update packets, means if I discover new neighbor, then I want to sync my topology and routing table. So for that reason, I can send the update packets. Now in this case, in case of new neighbors, they are using method as unicast. But suppose if you have any change in the route metric, at that time they will use multicast as a transport. We have very important packet type, that is query. Why it is using query? Because suppose your successor and suppose your feasible successor, so both, if they got failed and you don't know how to reach to the network or you don't have the network update, so at that time you're sending the query packet that do you know this network update, and you will wait for the reply. So we have the query, means the router places itself in the active state. So I'm in the active state, I'm sending the query packet and I'm waiting for the response. Now the reply packet are sent to give the response for the query packet, and these reply packets are sent as a unicast to the querying router. Now we know that EIGRP using reliable transport protocol. So that's the reason we don't have acknowledgement for hello packet and acknowledgement itself. But for all the other packets like update, query, and reply, we have acknowledgement. So here you can see that the following packet types employ RTP to ensure reliable delivery. So that's why we have acknowledgement for update, query, and reply packets. Now we have two state in EIGRP. Active state means actively you are looking for the neighbors, or actively actually you are looking for the network, and then the passive state, that is the stable state. So once the routing has been converged, once your topology table and then your routing table, they are stable, at that time that state is passive. If you are still looking for a network, if you are still having a problem in the network, that move to the active state. Now we know that in active state, when I don't have the successor and feasible successor, I have sent my query packet and I'm waiting for the response. Suppose if it will take 3 minutes to take the response back, that state is termed as a stuck in active. So you have sent your request and you haven't got the response, and for 3 minutes you move to a stuck inactive. You are still inactive. You got stuck. Now there are some solution to improve this stuck inactive phase. Either you can do proper summarization, network summarization, or you can use EIGRP features such as a stub. So means your hub and a spoke, think you are the main router hub and then you have the spoke, and those spokes, suppose if you convert those spoke as a stub, then the query will not propagate and it will not unnecessarily overutilize the bandwidth. Okay, so we'll see that concept of a stub later on. Then we have some verification command in the lab section. We'll verify. We can run show IP EIGRP topology. Here you can see the state codes are P for passive, A for active. If it is a converged, then you'll find P as a passive. You have one successor or you have two successor, etc. We can get those information. Here one important point that you can see that you have feasible distance as 2297856. Now how EIGRP is calculating his feasible distance, that we are going to discuss, and that's very interesting calculation we have for the EIGRP metric value. EIGRP uses 5 parameters to calculate the metric value: bandwidth, load, reliability, delay, and MTU. Now here you will see that in some places it is mentioned that the MTU will not come into the picture. Anyways, we have these 5k values for these 5 parameters, or these 5 you can think as a variable or the component for the metric. Now these 5 component for the metric value, we have one very complex formula. So let me show you this formula here. Here you can see the formula. That metric will be calculated as k1 into minimum bandwidth, then plus k2 into minimum bandwidth, 256 minus load, plus k3 into delay, into k5 divided by k4 plus k5 divided by k4 plus reliability into 256, where your bandwidth is 10 to power 7 by divided by least bandwidth. Now this is a really complex formula. So to make this simple, what is happening generally, most of the cases you'll find that the system using K1, K4 and K5 as 000. Then you have K1 and K3, that is bandwidth and delay. And that's the reason you'll find that the calculation for the metric will be dependent mostly upon bandwidth and delay. So again, you can see that 10 to power 7 divided by bandwidth, and then plus delay. Delay will be in microseconds, and this bandwidth will be in kilobits. Okay, so kilobits, and the delay will be in microseconds. Again, uh, the bandwidth will have very huge impact in the metric calculation. So that's why you can think here with this formula that your metric value is indirectly proportional. It's not directly proportional. So sometimes if you check the calculation, that it's inversely proportional to bandwidth, correct? Because you can see 10 to the power 7 divided by minimum bandwidth. Obviously, if you have delay, then you can add that, but the major role played by the bandwidth. All right, so this is the formula to calculate the metric. Now, how you want to apply this metric? If you want to change certain parameters, so for example, we have the CLI command metric weights and 0, 1, 1, 1, 1, 1, like K1 up to K5. And suppose if you want to add any of things, say for example, I'm making K3 as 1. So here you can see K3 as 1. Then again, this formula will get changed, correct? So in my case, K2, K3, K4. So here you can see K2, K3 and K4 will be 1. Then again this calculation will get changed. Again, it's highly unlikely that we are going to change the metric value. Whatever by default is there, we are using it. But yeah, in certain cases, if you want to do some sort of traffic engineering, some sort of load balancing, some sort of change in the metric calculation, then you can go to the interface and either you can change the bandwidth. That's the normal thing that we used to do for the traffic engineering. Either we are changing the bandwidth or we are changing the delay factor. So either if I change the bandwidth or the delay factor, I'm going to change the metric calculation as well. Okay. Now, again, we have one command, IP bandwidth percent Eigrp autonomous system and 30. By default, Eigrp is using 50% of the link bandwidth. And suppose if you want to make this 30%, you can use like this. Your link bandwidth is 64, so you are using 30% of 64. We have option that we can use 100% as well with this command. And again, if you want to change the delay, you can go and use the delay as well. So let's just stop here, and in the lab section, we'll try to understand more whatever we have covered so far. Let us do the Eigrp configuration, and after that configuration, I will go and verify first of all the basic things like how Eigrp having their neighbor table, then their topology table and their routing table. Plus we'll see the various type of packet types that they have. Then we'll go and check the other things that we have studied in the previous section. So let's start, and what I'm going to do, you can see here the diagram R1 and switch 105. So in between that you can see the interfaces. I'm going to assign the IP address to all these related interfaces, and plus I'm going to give one loopback address as well, just for verification purpose or testing purpose. So let me quickly go and assign the IP addresses to all these interfaces. So I have assigned the IP addresses to all the interfaces. Let me quickly show you that. We can go and verify once. Show IP interface brief, and I want to include the manual. We'll go and run this to all these devices 101, 102, 103, 5 and R1, and I should press enter, send the script. So here you can see that over R1 I have this IP address, then switch number 105 I have these IP addresses. Although I haven't pinged and verified that they are reachable or not, but I have assigned the IP addresses over the interfaces and created over the loop loopback interface as well as per our topology. Okay, so next task I have that I should run Eigrp. So let's go and enable the router. Eigrp, we know that we have to give the autonomous system for that. So let me show you from here, from the global config mode, router Eigrp, and then we can assign the autonomous system. For example, I'm using 10. I'm going to use no auto summary, means I don't want to do the automatic summary. So that's why this no auto summary command. Then I want to advertise the network. Now we know that what type of IP we have, and if you want to check the network, connected network, you can go and then do show IP route or show IP route, so you can get the connected network list. But because I have this network here, so I can go and use, and then we have this option that we can use the wildcard bit. Then I can go and use the other network. Oops. Then I have other network as well, that is this one. And I can go and use the wildcard bit here as well. Then the third and the fourth one. So this is my third network. And then finally the fourth one. The loopback address having /32. The CIDR. So I will go and use this 00000 as a wildcard bit. We can quickly check the Eigrp configuration. So here you can see that we have these many network. Now I should go and enable this to the other devices as well. So we have done the configuration to 101. Let me go and do it to 103. So for 103 the network is, so let's go to 103. Router Eigrp 10, we should have the same autonomous system, no auto summary. Then the network, we know that network is this. At the moment I enable or I run this command, you'll see that they will start forming the neighbor table, topology table, and the final is the routing table. So dual algorithm will run here. You can see that it is running the dual algorithm, and then we have the routing table as well. All right, so at this point of time, at least I can go and check show IP Eigrp. First of all, the neighbor table. So here you can see that this guy is the neighbor, the uptime is this many second. Rest of the things we don't have much worry. We don't need to worry about this request timeout, the queue count, sequence number, round trip timer, etc. If you have any issue at that time, you'll see that queue count is increasing, or you have the RTO value is increasing, or round trip timer is increasing, etc. Okay, so first table will be the neighbor table. Then you can go and check the other stuffs as well. Like I can go and check show IP Eigrp topology table. That's the database you have. Now here you can see that you have the successor, feasible distance successors, and then you can see that you have the metric value as well. So here you can see your FT values. Now this calculation, we'll discuss this in upcoming slides, or even now also we can discuss. So I need to open the mathematical calculation and the calculator. So for that we'll go and check what's the bandwidth and how this calculation is coming into the picture. That's 409600. Okay, that's the FT. Again, you can see that P stands for passive, and then you have all the codes. So let me quickly open the calculator and let's do the calculation here. So we know roughly the formula for the metric value is, the metric value is 256 into 7 divided by bandwidth in kbps and plus delay. Roughly this is the rough calculation. So let's try to understand first of all the bandwidth for the interface. Everywhere we are using Mbps, so my bandwidth is 100 Mbps. Now this 100 Mbps, let's calculate it in kbps. So let's try to do this. Now 10 to the power 7, so 4, 5, 6, 7 divided by 100 Mbps means 100 into 1000, means we have to convert into kbps. So number of zeros will be 0, that is 100, and then 30, so that will become the kbps. So the final value will be 100 and plus delay. So I should go and check the delay over the interface. So for example, show interface E0/0. Now if you go here and you can see the delay, this is in microsecond, this is not in this is 10 to the power minus 6, that's the microsecond we have, and that's okay. So what will be the value for this? 1000 into 10 to the minus 6, correct? Okay, and that's correct format actually. So let's see. Let me open the calculator one more time. So that means we should go and add 1000 here, and then if we do 256, 281600, I can see the bandwidth in kilobits, that is showing 10 to the power 4 only. And let's go and verify that what is our metric value. That is 281600, that's correct. So yep, let me open the calculator, and here you can see you have the exact 281600, 281600. Yeah, so this is the way that we can do the calculation for the metric. Okay, so what I'm going to do here now, let's just stop here, and this lab we will study some theory, and again I'm going to build, and I'm going to continuously build this lab as well in the upcoming sections as well. Let us understand some more terminology and theory for EIGRP, and likewise we are going to continue our lab as well. So the next topic we have related to passive interface, auto-summarization and authentication features. Let's see here in the slides, we'll go step by step. Now first of all, when you're doing the baseline configuration that we have already done, go and enable the EIGRP process with autonomous system, and then we have option to advertise the network. Now we can go and add the wildcard bit as well, so we can get the specific network advertisement. Once we do up to this point of time, obviously we know that the hello packets will start exchange, and then they will form the neighbor relationship. First of all, we have the neighbor relationship or neighbor table, then topology table, and then finally the routing table. All these things we are going to see in the upcoming lab as well. Then suppose if you don't want to form the EIGRP neighbor relationship like we have done in Ospf earlier, so then I can go to that particular interface and I can make that interface as a passive interface. Standard format is that you deny all the interfaces like passive interface default, and then selectively you can go and add the interfaces who want to do the Eigrp hello exchange or Eigrp packet exchange. So for that we have the passive interface default, and then we can go and give no passive interface and then the interface name. Now again, we have learned this in OSPF that how we are going to do the summarization. In OSPF we have summarization, or we can do summarization over area. So we have used that command. I have shown you that how that command work, or how we can use that command, and then we can do the summarization for ASBR as well. So we can do the summarization for ABR and ASBR. Here in Eigrp, this summarization is a bit easy. So first of all, in the previous section, in the lab section, we have used the auto summarization, because if you do not do the auto summarization, so in that case, what will happen that it can be converted to their class boundary. So for example, if you have network 10.100/16, if you do not use the auto summarization, like no auto summarization feature, then it will think that his network is 10.0.0/8 because uh, 10 is belonging to class A, whose subnet mask is 255.0.0.0. So like that, we need to use this keyword like no auto summary. You have to use this. And then coming to the manual summarization. Now the same thing that we have discussed in case of OSPF, you have to go to the interface and then summary address Eigrp, the autonomous system, and what you want to summarize. So you can do the summarization. I'm going to cover this in the lab section. We'll create some different type of network, and then we'll do the summarization, and then we'll send to the devices. Now when we do the manual summarization, at that time the AD value is 5. We know that the internal AD value is 90, that Eigrp AD value is 90, but for the summarization, our AD value is 5. Now we have one note here that as with auto summarization, the router performing manual summarization will add the summary route to its routing table with a next hop of null interface as 0. So we know that uh, you're doing no auto summary. See, that's the combination. Do the no auto summary. You're not doing the summary automatically, and then you are doing the manual summarization, and that's the reason we have this AD distance as 5. Obviously, that is more than the internal distance. Okay, so do not mix with auto summarization and use this practice, no auto summary, and then the manual summarization. Then finally, in this section, we have the authentication. First of all, we have to create the authentication key. So here you can see that key chain. Define the key 1, 2, 3, 4, 5, etc. Then key string, define the password. And then over the interface, we have to go and apply it, like IP authentication keychain, autonomous system, and then key. If the authentication or the password will match for both the peer interfaces, then only they will start exchanging the Eigrp hellos. Okay, so these are the topics that I'm going to cover. Let me open the lab section and let me show you whatever we have discussed here and what are the things that we have in the leftover in the previous section as well. As per our lab topology, what we have done that we have enabled Eigrp over 101 and 103. So now if I go here and I can show you this, show IP Eigrp neighbor, show IP Eigrp topology, and show IP Eigrp. Better I do show IP route Eigrp. That's the routing table. So whoever is your feasible successor, that you will see in the routing table as well. So here you can see that what is the network that I am learning here, and that's why it is there. Rest all the network actually is connected. So you can see all are connected routes, and then finally I'm learning one of the loopback, so that's why it is coming inside this routing table. We should check all these things first of all. Then if you want to check the packets, so we have the show IP Eigrp, and here you can see the traffic. Here you can see that what type of packets you have: hellos, update, query, replies, acts, stuck in active. So all those packets we have. With this command, we can go and check the packets as well. Okay, and then how we can go and change the metric values, so that we have discussed in the previous section. I can go to Eigrp, and then you have command metric weights, and then you can see that say for example type of service K1, then K2 for example, then K3, K4, K5. So like that we can go and put all these values. I'll not put this value, and just showing you that you can go and check these values. Now let me go here and let me show you show IP route Eigrp. So here you can see that you have your AD value, you have your metric value. Now if you go to the interface E0/2 and 0/2 where it is, so we are here, that is going to switch 103, and I have this option that I can go and change the bandwidth. So if I go and change the bandwidth to 5000, and if I check show run interface E0/2, show interface E0/2, here you can see this bandwidth is 5000, and here it is 5000. Now if you go and check the metric value, because we know that the metric value will get changed, so now it become this. Initially it was, so now it is 1 2 3 4 5 6 digit, because initially I think that was 10000, I think 1 and 4 times 0 the bandwidth. Now if I go up and if I can show you the bandwidth that was before change, so 1 2 3 4 5 6 409 600, that is increased because this increment is bandwidth and metric are inversely proportional. So if this number is increasing, that means the bandwidth is decreasing. What I am telling you, that if you go to interface E0/2 and if you give the bandwidth, say for example 1 move 0, so if this will increase, this will decrease, correct? Do show IP Eigrp, or do show IP route Eigrp. So now you can see that this is decreasing. So if you increase the bandwidth, your metric will decrease, and that will become more and more preferable. All right, so these things are related to the previous section. Whatever things we have studied now, that let's cover that. So first of all, we have a study about the passive interface. If I go here and let me do one thing, I'll enable the Eigrp over these devices as well, 101 and 105. So let me quickly go to 105 and enable the Eigrp. And before that, let me check what is there inside 101, what interfaces we have. So we have 1 2 3 3 interfaces, that's correct. And then we'll go here to 105 and we are going to add the interfaces. So we have 10120, 10130 and 1. So 1 2 and 3. All right, so let's do this. Say router Eigrp 10, no auto summary network 10.1.1.0. Then we have 2 and 3, correct? And then we have one loopback as well, so 2, and then we have 3, and then we have network related to 105, 105, 105, 105, 0000255. Alright, so here the network we have. Now since it is not coming up, that means something is wrong related to interface is down or something that we need to check. 10.1.20 E11 and E10/0. So if I go and check to show run interface, say do show run interface E10/0, I can see that the interface is correctly defined. Then I'll go and check to E1/2, E1/10.1.2, and if I go and check to show run or show run section Eigrp, should have a routing for that. So I can see 10.1.2.12.105. Yep, some issue seems to be related to connectivity or maybe interface that we need to figure out. So here you can see the issue. My interface should have correct IP address. So IP address is 10.1.2.105, and you can see 2.1 and 1.2, how minor mistake that was, but again we should give the correct IPs, and now it is up and running. I can go and check show IP Eigrp topology, or I can go and check show IP route Eigrp because I'm interested in that. So here you can see that it is getting the loopback 103 and it is getting the loopback 101. That's why I've given the loopback addresses. So that means I have the reachability. Now if I go to 101, because he has two neighbor at this point of time, so IP Eigrp neighbor, one of the neighbor I want to make passive interface. So for that, I can go to router Eigrp 10, say passive interface default. That means everything is passive. Then we can do no passive interface E, say for example 1/2, and then I can go and do no passive interface for E 0/2. So this is the use of passive interface as well. Okay. Now what we can do next, that we have the summarization option as well. So for that I can go to, let me open this diagram. I can go to 103 and I can create some loopback addresses here. So for example 7 or maybe 103, anything. So let me go and create some of the loopback. So I'll go to 103 and I will create few loopbacks, say interface loopback 101, IP address, say for example 2.2.2.1, then interface loopback 102, IP address 2.2.2.2, and then interface loopback 3, or maybe anything, IP address 2.2.2.3, 255.255.255.255, interface loopback 4, IP address 2.2.2.4. Like that, I can go and create some of the loopback I want to do the summarization for. Then I can go to router Eigrp 10. I can do the advertisement, say network 2.2.2.2.0.0.0.7. Do show IP interface brief if you want to check your loopback. So 3, 4, 101, 102, etc. But network is 1, 2, 3, 4. Now if I can go and check these routes here, show IP routes for EIGRP. Do I am getting the loopback? So here you can see that we are getting four network. Rather, I want to want one advertisement. So what I can do here, that I can go to the interface. So let me check what interface we have. Brief, we have interface inside 103. So let me show you this diagram here. So we can go to 103 interface 0/0 and we can do the summarization. Okay, so interface is 0/0 IP, and then the summary address EIGRP 10, and then we can do the summarization. So 2.2.2.0, and then we can give the mask, say 255.255.248. All right. Then if I go here to 105, you can see the AD value is 90. 105 is getting this single advertisement. That's okay. And if I go to, I'll cover that. So now you can see that this, once you do the summarization, the EIGRP algorithm will rerun, it resynced, and it has sent the summary. Now if I go to 102, and here if I go and check, oops, we'll wait, and let's see the final command. So what we have, show run section EIGRP, and we have done this summary. Great. So we'll go to the 102, and in 102 also I'll go and verify that what advertisement exactly I'm getting here. So we'll go here and check show IP route EIGRP. Where we are, I should go to 101 as per the diagram. We haven't done any configuration for 102. So show IP route EIGRP, and we are getting this advertisement. And if I go to 103, who is the originator, show IP route EIGRP, it is sending the summary to the null, and then it is getting advertised to all the devices, correct? Now we are going to discuss the theory of load balancing, stub areas, and authentication lab will do in the upcoming section that we have already discussed. EIGRP is a protocol that can do unequal cost equal load balancing. So what does it mean? It means that if you have feasible successor, if you have successor and feasible successor, or vice versa, so in that case, one is your primary link, or one is your primary path, one is your backup, but still with help of variance, we can make both as an active link. So that means that we know that successor only get installed in routing table. But if you use the variance command, both the successor and backup successors, or the feasible successor or backup paths, those things will get installed in routing table, and you will get, although you have the unequal path. So for example, you can see these two paths, still you will see that those things will be installed in routing table. So you have the successor and you have the feasible successor, that's your backup, but still if you send 4 packets, 2 will go via this, 2 will go via this. Just an example. The devices, they are not doing packet based load balancing, but it's something called flow based load balancing. So what's the command? Variance. We'll see that how much variance we can use up to 128. We'll see that in the lab section. Maximum path by default it will be 4. We'll see that how much maximum path load balance it can do. Maximum it will be 6, but in higher version of operating system it may be more. By default it will be 4. Next topic we have a stub. Now we have discussed this earlier that suppose if I lose my successor and feasible successor, so at that time I will send the query packet, and query packet will get propagated until unless we get the reply. Suppose if I get the reply within 3 minutes, that's okay. Otherwise this process is known as a stuck inactive. Now to mitigate or to overcome from this, that already I know that network is not after this particular hop or router, I can make that spoke router as a stub. So that means that I am sending a query packet, but you will simply reply no. You don't have your what you are looking for from this direction or from this route or from this gateway. So that the query will get answered that this is the stub. All right, what's the command? We have the command. We should go to the Eigrp process. We can go and run this command Eigrp stub, and then we have 4 options. Receive only, that will not share the update with neighbor. We have connected, static, and summary options. Connected means advertise connected routes. Static means router will only advertise a static route. Summary means router will advertise only summary route. Okay. So these options we have with the stub. Then we have some verification command. We have seen this show IP Eigrp neighbor. Then we have seen show IP eIGP topology. You can check who is the successor, feasible successor, FT and AD, those values we can check. Show IP eIGRP traffic already we have seen. Show interface, and you can go and check the interface, what is the delay, what is the bandwidth, reliability, load, etc. Show IP protocols we haven't checked so far, so we'll run this in the lab. Show IP protocol will tell you detail about the protocol. It's a very useful command. It is giving the detail structure or detailing about that particular protocol. Show IP route, we can check the routing table. Show IP route EIGRP if you want to filter it. And then finally we have some debug commands such as debug EIGRP neighbor, packet route, and summary. Remember, do not run this debug command until unless you have the maintenance window. All right, so what we can do now from this point of time, I can go and log into the lab. We can continue our lab because we have to run or we have to verify few of the things one by one. Load balancing a stub, and then we have to do the authentication lab. All right, so we are inside the lab section. So far we have ran that EIGRP over 101, and let me quickly see that if we have done over 102. 102 we haven't run, so let's go and do that. What is the network we have? We have 3 and 4. So I can go here and router EIGRP 10, no auto summary, network 10.1.4.0, and then the wildcard. Then other network we have 3.0, so I can go and do that. We have 3.0, and then we have network 102, 102, 102, 102, 0000. Okay, so here also I can see that the protocol, EIGRP protocol is not coming up. Let me quickly go and check the interface. Maybe the IPs assigned are not correct. So we have 4 and 3, that's correct. Let me quickly check where it is connected. So it is connected 0/0 and 1/2 as per the diagram. Here you can see that should go to 101, and seems this 0/0 may be passive interface that we have done. So I can go here and you can see the usefulness of passive interface. So I can go and check the configuration first. Router Eigrp 10, I should do no passive interface for E0/0, and let's see. So now here you can see that the protocol is running. Great. From this direction it's okay. Let's quickly check 10/1. So I can go to 105 and I can check here the Eigrp protocol. Do we are running the network command or not? So I can go here and check section Eigrp. We have 10, 1, 2 and 3. Is it correct? So we have 10.1, 10.2, 10.1.3. That's correct. Let me go and quickly check E10/1. So run interface E10/1 and we have wrong IP. So E10/1 IP address should be 10.1.3.105 and then 255.255.255.0. Alright, so now we can see that it is working correct. Now if I go and check show IP route Eigrp, so here you can see that you have the loopback 1, 3, 5. So we have the loopback 105, 101, 103. All these we are getting. Finally, let's quickly go here to router 1 and check do we have the configuration for the Eigrp. We don't have, and we have some configuration related to summary as well that I actually don't need. So I can go to 00 and I can remove this command. Let's do router Eigrp 10, no auto summary, network 10.1.1.0, and then we have one loopback. That loopback is 0000. Now if I go to any of this switch, say for example 103 also, I should get all the loopback. So let us continue and perform the lab related to authentication, and then we have the unequal cost equal load balancing, and then we'll see that what is the command for the stub as well. So let's start this. We have the topology here. You can see I'm going to enable the authentication in between R1 and switch 105. The common interface is E0/0. So how we are going to do, first of all, you need to create the keychain. Say for example, the name is CCNP in caps, just to refer this is the name. Then key I can give one, and then I can go and give the key string, say CCNP and then key. Okay, great. Then we have to go to the interface E0/0, and then we have the keyword called IP authentication. I should give the mode as Eigrp 10 and MD5. So we have actually two commands. One is IP authentication, and at the moment I have executed this command. You can see this neighbor relationship is down. Then we have the keychain option, keychain Eigrp, and then the name of the key chain, that is the CCNP. Okay, that's it. So these are the commands we need to run. in order to enable the authentication. Now the same copy paste I can do to this side, and you can see this neighbor is down. I can go and create the keychain first. Then I can go to the interface, and then over the interface also we can go and run this command. So let's do this. Over the interface I have these authentication command. We can go and enable this. Now we'll see that the neighbor will converge, and now I have the neighbor relationship with the router 1, that is 10.1.1.1.0. Just now it came back up 10 seconds back. Alright, so this is the way that we can do the authentication. Next we have the variance. So let's try to understand the unequal cost equal load balancing. Now here you can see that I can go and reach via this path to R1, and then I have the other path as well. So let's try to check the loop back that we have here, that is nothing but 1.1.1.1. So how many path we have to reach to 1.1.1.1 from switch 101. If I go to switch number 101, and if we go and check show IP route for 11111, and I should give the network. So 11111, here you can see that I have only one path to reach there via E1/2. And if you go and check show IP Eigrp topology, and then if we go and check 1111/32, so inside topology it is telling that you have 2.105 and 4.102. So here you can see that it can go via 102 this way, and it can go via 105 this way. Obviously the metric value that you can see here, the FT and AD values, those are different. But you have two paths. Now, is it a successor? So we know that who is the successor. Successor is this, because obviously it has lower FT. Here you can see 435200. And if you go and check this output in this manner, just to see that to reach 11111, I have only one successor. Okay, although we have two paths to reach there, so in this case this will be direct like this via 105, other one will be via 102, and then 105, and then R1. So what we can do now, I just wanted to add up the value for two different paths. So suppose if I want to decrement this, first of all let's try to understand, can I do some sort of traffic engineering that traffic will go via this direction rather than directly? Let's try. So that means I have a bandwidth here defined and here defined, and that means that I have to increase the bandwidth at 2 points over switch 101 and then switch 102, correct? Because all the links have equal bandwidth. So if we go and check the bandwidth for 0/0, show interface is 0/0, here you can see that it has bandwidth this. Now I should increase the bandwidth. So 1, 2, 3, 4. What I'll do, I'll go to interface E0/0, bandwidth is, so for example 5, 1, 2, 3, 4. Now let's see the show IP route for 1111, how it is going. So now you can see that still it is going via 105, that is still it is going directly. Now next what I will do, I'll go to 102 and I'll change the bandwidth of E1/2. So I am here, E1/2, bandwidth is 1234. If I go here and check, so what we are doing here, that we are trying to forcing the bandwidth so it will change its metric value, and so we can see that show IP Eigrp topology, that it is going via E1/2 rather than it is going via E0/0. And if we go and check topology for 1111/32, now if you check the composite metric here and composite metric here, still we don't have much change in the composite metric. Obviously the reason here is that you are changing the metric here and you are changing the metric value here. We should change here also, that is E0/0, and the bandwidth is, so we are just forcing the bandwidth. Now if you go and check, and still we can see that it is preferring this way. So IP route, so there is no change while we have changed the metric. For 1111, it is still going via the directly connected path. Okay, still it is going via this direction, although we try to change the calculation because still it may be less than what we are getting from two link. So for example, 102 you can see what's the metric value here, 2048000, and then if you go and check the metric value from here, so if I go and check show IP route to reach to 1111, so switch number 2 to reach to router number 1, here you can see this is the metric, and if you go here, so seems the metrics are very much same. So how these guys are reaching is that they are coming to this this point, and then it is getting advertised to these directions, correct? All right, so here you can see that in this case, if you want to do traffic engineering, it's very difficult to do the traffic engineering, but one thing that we can do here is unequal cost equal load balancing, correct? So if we have successor and if we have feasible successor, then it will be very easy to do it. Now in this case, I don't have any feasible successor. So IP Eigrp topology. So I can see here that I have only successor. I don't have any feasible successor. If I have feasible successor, then it's easy to do, but still I can go and use the router Eigrp 10 and then the command, say we have variance, I'll give the worst case, that is 128. And then if you go and check show IP route, specifically I want to see for uh, one of the route, but here I can see that 105 now have two different having equal cost multipathing, although you can see the metric value is different. So if I go here to the topology, you can see that from switch 101 to reach to 105, and obviously you have one loop back. I have two paths, this path and this path, these two paths. You can see their metric value is different. One is 2300, one is 409, and how we are doing the calculation actually, that's 230 and 409. You have to simply divide it, and you'll find it's almost double. So the difference is of double. So what I'm telling here is that when you are using the Eigrp value, we have given the variance of 128, that's the worst. You can give 3 also. And then if you go and check the route, you'll find that they are doing the unequal cost equal load balancing. And again, if I go and check show IP route, or maybe show IP Eigrp topology for this guy, and should do this with 32. So now here you can see that you have this path that is going via directly to the switch and then loop back, and then it is going via the other switch, and then here you can see the metric value, this and this. The difference is almost double. Okay, so now we can see this, and if I go and check show IP Eigrp topology, so here in the topology you can see that it is 105. So here you can see that you have two successor. So at this point of time it is showing two successor. Obviously if you have successor, then that will be installed in the routing table, because we have done so many changes in the bandwidth also. So that may be one of the reason the metric values get very much balanced. So let me quickly go and revert back the change. So I'll go to 102 and I'll change the bandwidth for E12 and E00. So let's do this. 00 bandwidth is 1234, E1/2, 1/2. The bandwidth is, because again if you change the bandwidth, you'll go and see the values will get changed. So for 105 now you can see that you have only one successor, although we have used the command called variance. So if I go ahead and check show IP route for 105, there you can see that you have only one path. Okay, so this is the use of the changing the metric value with help of bandwidth. Although we know that we can change with a delay as well, but I'm not showing here. We can change with the bandwidth, and then we can play around with the variance command. Finally, we have one use case related to stub. So suppose in this case, if I got some issue, and if something will happen with my destination network, somehow if I am not able to get my destination network, so what will happen? So in this case, suppose if 105 is the hub, so this guy here is the hub and these are the spokes. So you can go to the spoke and simply you can enable the command called stub. So suppose if this link will go down, for example, just in case of example, and because this is the stub, so the query will not processed, and simply the stub will respond to the hub that, oh, you can't go beyond me. I don't have any network that you're looking for. So in this case, what we can go do that we can directly go here and we can go to router Eigrp and we can check the stub command. So if we have Eigrp and stub, now you can see that you have connected, leak map, receive only, static, summary. So we can give connected and summary. Now you can see that it reran the algorithm. So now this become the stub, and the theoretical aspect of this we have already discussed. Alright, so let's stop here. In 3.2 we have to study about border gateway protocol. Although the syllabus, you can see it's very small, that we should configure and verify eBGP and do some path selection or learn best path selection criteria. But I'm going to start with zero. I'm going to start with the beginning of BGP. So what is BGP, what is iBGP, eBGP, etc., etc. So let's start. What is border gateway protocol? The first question arises is that already there are protocols, routing protocols. There is still why I need one extra protocol. Now the answer for this is that this is the exterior gateway protocol. Means this will override or this will run on top of any of the underlying protocol, any of the underlying IGP protocol, and it will work such as the application protocol. And that's true. If you see the port number that BGP is using, this is using TCP port number 179. Generally, applications, they are using TCP port numbers, or they are using TCP or UDP. So BGP is a type of application protocol generally built to run over the over any of the protocol and cross the one or one autonomous system. Again, the autonomous system is one region, so cross one region and then it can go to multiple regions. Or if you want to control multiple region routing or the network advertisement or the routing control you want across the multiple region, then that's the protocol. Or in other words, we are telling that it's a protocol for internet. It's a highly robust protocol, and it has so many tuning options. It has so many attributes, so we can tune it, and that's the thing. So it says advanced vector protocol with high level of tunability that can go across the regions. It is a type of application protocol, and the final point about this is that it can interact, or it can hold, actually it can hold a big amount of a routing database or routing table. Okay, defined by the AS path, we know that autonomous system to autonomous system, it has its reachability. It is a distance vector protocol. It has the autonomous system number defined here. You can see from 1 to 65K. Few of the numbers are private and reserved. Nowadays we have dotted notations as well for the BGP. Now here you can see that why you want to use BGP. So when you have multiple connection exist to external autonomous system, means you have multiple exit, or you have multiple ISP connected with you. Either those multiple connections with the same carrier or provider but connect via routing policy. The existing routing equipment can handle the additional demands. So it is highly tunable. So if you want to do some sort of preference, path preference, some sort of load balancing, etc., etc., so those things are achievable with help of BGP tuning capabilities. Okay. Now, one very important point here is that BGP true benefit is to controlling how traffic enters the local AS, local autonomous system, rather than how traffic exit from it. So the true benefit is that how you are controlling the traffic when it is coming to you, when it is coming to local AS. Now we can have two type of neighbor. We can have iBGP or we can have eBGP, exterior and interior BGP. iBGP means within the autonomous system. So in this diagram, router B, C, and D, they are iBGP peer or they can be iBGP peer. And then different autonomous systems like AS 100, 200, 300, they can be eBGP, exterior BGP peers. Now we have options that what type of iBGP relationship I want. Do we have full mesh or what other tuning options we have? We'll go and check later on that we have multiple options when we are talking about the internal neighbor relationship or interior neighbor relationship. Generally, when we are creating the iBGP relationship, we should create fully meshed. Otherwise, there are some other options to uh, do the advertisement for the network that one iBGP peer is getting and advertising to other devices. Now, one device can have only can be part of one autonomous system, and if you want to make part of multiple, it will throw an error. We have the AD value fixed for eBGP. For eBGP, the AD value, the administrative distance is 20, and for iBGP, it is 200. Okay, so that means the eBGP routes are preferred than iBGP routes. So 20 versus 200, lower is better. That thing we know. Now the BGP peer messages, we have BGP peer messages. What type of messages we have? So we have open message, we have keep alive, we have update and notification. Now open means that I want to form the relationship with my neighbor, and here you can see that an open message is sent between peer to initiate the session. The open message has several parameters like version, local AS, BGP router ID. Then you have the keep alive. Keep alive is something like you are sending the keep alive message to your neighbor that you are alive or not. In BGP by default, it is sending that keep alive message after every 60 seconds. A 60 second into 3, that is 180 second, is the hold down timer. So after 3 keep alive message, if you are not getting response, that means your BGP neighbor is dead. You will mark this as a dead with help of notification message. So now this notification message is sent when there is a fatal error condition. If a notification message is sent, the BGP peer session is toned down or reset. Anyways, if your peer is down, that means you will send the notification peer is down. Then we have the update message that are used to exchange the route between the peers. Now here in BGP state machine, that is the finite state machine, we have some other messages as well. So what exactly this is, that when a BGP peer session is forming, at that time, if you go, suppose if I have two routers and I want to form the BGP neighbor relationship in between that, so you will find that they will exchange some sort of messages. Those are idle, connect, active, open send, open confirm, established. Correct? So idle means that it is initiating the BGP state. Then connect, that you are waiting for the remote peer. Active, that you are actively initiating the connection. Obviously the connection is TCP. Then open sent. Open sent means you have sent the open message. Once you send the open message, then BGP listen for a reply keep alive. So you have sent the message, you got the acknowledgement, that is open confirm, and then the finite state machine will establish the connection. Correct? So it's very easy. Idle, connect, active, open send, open confirm, and they establish. Now if peer is stuck in active state, the potential problem may be that maybe you have password mismatch, maybe ACL is blocking port number 179, maybe you have incorrect AX, maybe you have incorrect neighbor statement, and so on. So if it is stuck in the active state, that means it is not good. Correct? Then you have to troubleshoot and make this as a working. Now, how we are going to configure it? We know that one router can be part of one BGP autonomous system. Go to the router BGP, and then the autonomous system. If it is a eBGP peer, remember, if it is a eBGP peer, they have the TTL value of 1. So they are always thinking that their next hop is, or their peer is, one hop away. So in that case, you don't need to modify the TTL value. You don't need to modify anything, any other thing. Means router B of AS 100 and router C of AS 900, they have to give simple command router BGP neighbor and remote AS. That's it. Now, if it is a iBGP pair, then you can go and you want to update the source. So for example, generally we are using a loopback as a router ID. So in case of iBGP neighbor relationship, you need this update source loopback command, correct? And I'll come to that eBGP multi-hop option as well. Suppose if you have eBGP relationship and it is multiple hop away, then you can go and use the eBGP multi-hop. So for example, 200. So in this example, it is showing simply that suppose if you are using the loopback address instead of this physical address, if you are going to use the loopback address, that is again one hop away, then how you will form the relationship? So in that case, say for example, the router C is using the neighbor 1111, and we can see that who is 1111. Obviously this router B loopback address is 11111. So in that case, that will be hop away. For that we should go and use neighbor 111 eBGP multi hop 2. So you should count how many hops away your peer is, and then you can use this multi eBGP multi hop command. Finally, we can go and use the password with the neighbor command. So for that we have the neighbor password, and so for example Cisco. We have other option as well, that if you want to change the keep alive timer, we have discussed this about that the default keep alive is 60 seconds and 180 seconds is the hold down timer. But suppose if we want to use some aggressive timer, we can go and use timers BGP 30 and 90. And in that case, we can go and set the BGP timers. All right, so let's stop here, and in the next section, we'll perform the lab, whatever we have covered in this section. Now we have to perform the lab related to BGP. Here you can see in the diagram that I have router 1 in AS100. So AS100 and AS200 router and switch 105, they are going to form eBGP relationship, exterior BGP. And in between AS200, say for example switch 101 and 105, they are going to form iBGP relationship. Okay, so let's start the configuration for R1. If I go to R1, I can go and I can initiate the router BGP process. So for example, AS is 100. Then what is your neighbor? Now for neighbor, I can go and check the directly connected neighbor. So that is directly connected neighbor is this 10.1.1.1, 10.1.1.1.0.5. So he has the neighbor 10.1.1.1.1.0.5. And then what is the remote ACE? So we should go and give the remote ACE. Say for example 200 I'm going to configure. Then here if I go and check show IP BGP summary, you can see that state is idle, correct? So it has initiated, and if I go and do some debug IP BGP, what type of packets I want to debug. So for example, I don't want all, but if I can get events, and monitor. So I can go here. Yeah, I can see some of the messages. So already we are monitoring over the screen, showing some of the events. If we debug IP BGP, just wanted to see the TCP number. So all address families and import in IPv4, keep alive, don't want that, out in, etc. Okay, if I do all, then it will be big output. Okay, now one other command we have. So here you can see that at least I'm getting this message, active went to active to idle. It's tried to move from idle to active, but it is not. And then here you can see that you have the TCB. So if we go and check show TCP, TCB, and then enter, show TCP, and if you want to see the brief, you just wanted to see the open ports if you have, and if you have any other option related to that. So you have the TCP, TCB, actually that's the command, TCP, TCB is the command, and if you know the TCB address, that will work. Anyways, so let's move on and go to the other side. Here I want to initiate the router BGP process 200, and then the neighbor is a 10.1.1.1 whose remote AS is 100. That's it. So now if I go here and if we see the packet, here you can see, let's stop the screen. So here you can see that you have the open, capability is open, and then a route phrase, then open, again active, went to open, send to open confirm. These exchange we have actually checked in our session, and then you can see the neighbor is up. And now if you go and check the TCP TCB, so now you're getting this established session, and you have the address as well. And let me do let me undebug, and now you can see the output for this. You can see the port number is this, so local port is this, the foreign port is this. Great. So most of the information we are getting from here. All right, so now the eBGP relationship is up and running. Now what I want, that as per our diagram, I want to create iBGP relationship as well. So for that, I know that neighbor is say 101.101.101.101, and whose remote AS is the same that I have. But since I am using the neighbor command, which is the loopback address, so I want to do the update source loopback 0, and I should check show an interface loopback 0. So yeah, that's correct. Now I'll go to 101. So let's go there and let's do the configuration for this. First of all, let's enable the BGP 100 whose neighbor is 105, whose remote AS is the same that I have, and then the neighbor, this update source loopback 0. Now if you go to 103, we go to 105, you will get one message, show IP BGP summary, that you have two neighbor, both are up and running. So one is up and running, that you can see here, You have 0 prefixes. State is up and running. Now if everything is okay and correct, in between 105 and 101, so 101 and 105, then they should form the BGP. But it is not, so let's quickly check the BGP configurations, show run section BGP. So here you can see that the I am part of 200 and this is also part of 200. So here you can see that directly you can see that problem that we should have correct configuration. This is part of 200 and now you can see that we are getting some sort of notification messages. We have seen that this is something when you have some error notification messages, we are getting some malform construct. And if you go here and you check the summary neighbor idle, like that it is coming. Let's go back and let's change the AS and we'll come back to 10. Alright, so let's complete the basic lab. Now here if we go to 101, we can see that the BGP AS is wrong. So I will go and do the changes. We'll go and change this to 200 and then rest of the configurations are correct. Alright, now once we done that, we can go and check the summary. You can see this is up and running. Likewise, if you go and check show IP BGP summary, that is up and running. Alright, so now once we have this, what we can do, we can check other basic stuffs as well. Now, for example, that we are going to continue the lab, plus I'm going to add few topics more in the lab section. We'll go and check the BGP neighbors once we enable run the BGP. Then we'll go and check the BGP neighbor. Plus we have one concept related to BGP synchronization. What does it mean by BGP synchronization? Although our lab setup is different, but I'm going to take same type of structure that I have one device for eBGP and few devices for iBGP, and then already we have checked the iBGP and eBGP, how we are going to form these BGP tables. Now what is happening that once we have the neighbor table, then it will build the BGP table and then we have the routing table. Correct, but one of the important table we have is the neighbor table. We have this command show IP BGP neighbor, where we can go and check the BGP neighbor details. If you want to check the specific detail to a specific neighbor, then you can go and use this command show IP BGP neighbor and the neighbor address. Next we have the BGP synchronization rule. Now this is important. What is happening that the general rule for BGP, or the golden rule for BGP, is that if your BGP is there inside the autonomous system or within the autonomous system, so you should enable iBGP rule, or you should do iBGP full mesh capability inside the autonomous system. Suppose if you do not do like this, so what will happen? Say, for example, in this diagram, this AS wants to reach to this network. Now suppose if I have iBGP relationship here, so here I have obviously the eBGP, and here obviously we have the eBGP relationship. So the traffic or the update will come to B, and then B it can go to D, because remember in BGP the iBGP neighbor relationship, it is not mandatory that they should have physical connectivity. So these BGP relationship can form over non-connected interfaces as well. Okay, so that means that I can have the iBGP relationship in between B and D. Now then it will go and reach to E. Now at this point of time, the router C, he don't know about this network 10505 etc. 10500. Next time if the return traffic will go and hit to D, and again suppose if it will go to C, since C is not having the update related to 10500, he don't know how to reach to 10500, he will be working as a black hole. He will start black holing the traffic. So what is the rule then? Then the rule here is that you should have eBGP relationship, should have iBGP relationship in between all the devices, correct? And that's the rule you have. You should have this type of mesh rule or the topology, and that's the reason we are using some sort of other technology like configuration or route reflection, because say if you have so many devices within autonomous system, and if you go and turn on BGP, and if you do this full mesh iBGP relationship, then obviously the CPU, the core utilization, memory utilization will increase. So this is not the optimal design solution. This is not that all the routers could achieve this target, because obviously they have to think more, because they have more number of control packets to process. The same explanation here, what we can do for BGP synchronization. The local AS is not a transit, so in which case you don't need if your AS is transit, or all routers in the transit AS run iBGP and are fully meshed. Okay, so the question here is that when you don't need the synchronization rule, answer is when your AS is not working as a transit. Second, when you all the devices in the transit, they are running the iBGP rule. How you can disable the synchronization? The command is no synchronization, and you can see that 12.28T synchronization is disabled by default. So in latest code, the synchronization rule is disabled. All right. So let's stop here, and we'll go back to our lab section, and whatever small and basic verification commands are there, first of all, we'll check that before moving further. Now we are going to perform the lab task. You can see in the diagram that we have AS100, we have AS200. Inside AS200, we have devices that are going to form the iBGP relationship, and in between AS100 and 200, we have the eBGP relationship. So let me quickly log into the devices. We are going to perform some of the tasks that we have covered already in the theoretical section. So let me quickly show you that what configuration I have over these devices, and obviously let's see the IP addresses as well over these devices. So if I send this script, you can see over switch 101 we have this IP. Let me show you this diagram as well. So here you can see the diagram and the IP schema. Router 1, that is inside AS100, having loopback 1111. All the switches, they have loopback as their name. So for example, here you can see the loopback IP, then the interface IP, then the interface IP. All right, so you can refer the diagram that we have, and as per our diagram, we have assigned the IP addresses to the interfaces. All right, now next thing that we should go and check the BGP neighbor. So I can go and check show IP BGP summary to all the devices. Now here I can see that as per our diagram, we have eBGP relationship and the iBGP relationship. Now, if we have this type of topology, still what you want that switch 103 and 105, although they are not directly connected, they are indirectly connected, they should form the neighbor relationship. In that case only they have the full mesh, correct? So suppose even I have the back-to-back connection here, although I don't have, but still I can go and form the neighbor relationship in between the 103 and 105 because underlay we have EIGRP up and running. So before doing that, you can see here that all the devices, they have their eBGP and iBGP relationship running on. eBGP in between R1 and 105. So 105, one interface having eBGP relationship, other one is having iBGP. Now suppose if you want to know detail about that particular neighbor, so what we can do, we can go and check show IP BGP neighbor. And first of all, let's see that in this neighbor command, let me see that what outputs you have. So you can go and simply check show IP BGP neighbor. Obviously, it will show you all the neighbors. So here the neighbor ID is this, belonging to 100 as a autonomous system, the router ID, the establishment, what time the neighbor got established, what type of messages they have exchanged. Here you can see open, notification, update, keep alive, and route fresh. So like that we can get the details. Now if I am very much specific to a certain neighbor, then I can go and run the neighbor command related to that particular neighbor. So I have one neighbor 10.1.1.1 and I can run and I can verify that. Okay. So what I will do first of all, that I want to show you that we can form the iBGP relationship in between 105 and 103. So let's do that. I'm already inside 105. I can go here and router BGP 200. I have my neighbor, for example, 103, and whose remote is the same. And then for this neighbor, I can go and use update source loopback 0. Now again, I will go to the 103 and we can run the same command. Then we have the neighbor, say 105, 105, 105, 105, and the remote is the same, and then the neighbor update source is loopback 0. Alright, so we can see here now show IP BGP summary that we have one new neighbor added. So not only my directly connected neighbor, but my indirectly connected neighbor is also there. That's the true power we have with the BGP, because this is working as a overlay type of protocol. Alright, so once we have all this information, then what I want, so I want to have a, so for example in router 1 and 105, if you go to router 105 and you want to put the password, suppose if I go to neighbor, say neighbor 10.1.1.1, and you can give the password the Cisco. So if you put password from one side, other side also you should go and check the password, router BGP 100, and just to show you that it will take some time because we know that keep alive is sending after every 60 seconds and the hold down timer is 180 seconds. So it will take some time to tear down the neighbor relationship. Still your neighbor is up and running because BGP is meant to be slow protocol due to various reasons. So if you wait, it will take some time because one side your neighbor having the password, other side we don't have the password. So I'll wait till the timer will expire and then I can come back here and I can set the password. Meanwhile, we'll go and check the other option. So we have timer option as well. So for example, I can go here to the router process and then I can check the timers for BGP. Oops, timers, BGP, and then keep alive. I can give 30 and then hold down. Suppose if I 10 and 30, keep alive 10 and hold down if I give 30. That means for all the neighbors it is true. Now suppose if you are specific and you want to change the timer for a specific neighbor, so for example 105, 105, 105, 105, then also you can do that. So where we can go and check the timers here, you can see so many options we have. So for example 20 and 60. So it is telling that you should go and specify the keep alive, say for example 20 and the hold down is 60 as a peer group. So then it will take that command. We can check later on about the peer group as well. So we can leave it, but yeah, we have option that we can go and specify over the per neighbor as well. Okay. So let's quickly see this BGP configuration. So here I have the neighbor with some timer, and then if I go here and check, and we can go and check show IP BGP neighbor 10.1.1.1. So here you can see that we have the neighbor established time. It is showing that what is the hold down timer and the keep alive. Although if you go here and check show IP BGP neighbor 105 and what is my neighbor, that is 10.1.1.105, and here you can see that still is this because maybe the command that we have run is okay. So here you can see the timers and the neighbor command. When we are running this neighbor command earlier, so let me show you that we are getting some error because that was not my neighbor. So that's the reason it was throwing an error, correct? Because my actual neighbor is 10 11110 not 105 105 105. So what I'll do now, I can go here and I can do this neighbor and then 10 11.105 timers. I can specify say 10 and 30, and that's it. All right, we'll go here as well, and I can go here router BGP 200, neighbor is 10.1.1.1, timers are 10, 30, and then we can go and check show IP, BGP summary, clear IP, BGP. Say star. I'm clearing the BGP table, and now if we go and check the neighbor table, so let's go and check the summary. Now you can see that after clearing that, we have the authentication issue because we haven't put the password for one side, and here you can see the password issue is there. So I should go and show this neighbor and with the password. So I can go here and give the password as Cisco. Once I do that, you'll see that it will get converged and the neighbor will come back up. Now it is up. So we know that in BGP, first of all, it will form the neighbor table, then it will go and form the BGP table, then it will go and form the routing table, or those things will go and get added inside the routing table. Okay, so let's stop here, and next section we'll discuss more about all these behaviors. Next topic we have BGP route reflectors, confederation, and the peer group. Now what is happening in case of iBGP relationship is that whenever iBGP peers, they are getting the update from outside. So what they are doing, they are assuming that all the neighbors, either it is physically directly connected or it's not physically connected, they assume to be in full mesh. Now if they are in the full mesh, then all the iBGP neighbors will send the update to everyone. Otherwise, there are chances that, say for example, router D will get the update, he will send to A, but A will not send to the other router because he will think that update will come from some other way that is again connected in full mesh. Now, while we are doing the approach of iBGP full mesh behavior or approach, so in that case, what we are doing that we are using some more bandwidth. We are consuming actually more bandwidth, more processing and cycles. So why? Because we have more number of BGP neighbors, correct? So if you have more number of neighbors, more number of control packets will send and receive to maintain that BGP state or BGP neighbor tables, correct? So that's one of the thing that what we can do, that we can use a route reflector. So the idea behind this is that any of the router which is there who is working as a symmetrical device. Now what does it mean by symmetrical device? Symmetrical device means he is approachable or reachable to most of the other routers. So that particular device, we are making this as a route reflector. So when he get the update, now his responsibility is to give the update to all the other devices. And this approach actually has been taken inside software defined networking as well. How? So if you go and check software defined networking, you will find that we have clause architecture. We have leaf, spine, and leaf. And again, suppose if you have more spines, a spine 1 and a spine 2. So all the leaves are assumed to be connected with the spines. So what does it mean? It means that behind the scene, all these spines, they are working as a route reflector. So at the moment they are getting the update, now their responsibility to send the update to all the leaves. And that's the fundamental here in route reflector. At the moment he will get the update, so suppose if I make him as a route reflector, now his responsibility is to give the update to all the other iBGP neighbors. Rather than we have the full mesh topology, route reflector will reduce the number of code, reduce the number of iBGP peers will drastically increase the CPU and the memory performance. Correct? Now, not only the route reflector is the technique, we have other technique as well. We will see in the next slide. So how you can do this? Here you can see I can go to router 1 and I can tell router 1 that your router B and D are the route reflector client. So the configuration is very easy. Just use neighbor, the route neighbor ID, remote AS, neighbor ID, route reflector client. That's it. Now we have other approach as well. We can use BGP Confederation to come to the same place or to achieve same target. Although the configuration look like little bit tricky, but the concept behind this is to reduce the number of iBGP pair, and inside iBGP you can use eBGP type of behavior. So what is happening in this case, you can see in the diagram that you have main autonomous system. These main autonomous system, they will form the eBGP relationship. Inside this main autonomous system, I have sub-autonomous system who is responsible, and you can think that who is child of the main autonomous system. So he is the child. But now since you have two different autonomous system, so 777 and 888, they will form eBGP type of relationship. So they will send and receive the updates because there is no problem with the eBGP relationship. We have this issue only with iBGP relationship. So inside the autonomous system, although it is showing only one device, but you may have multiple devices inside one AS. So they can exchange their neighbor tables, or they can exchange their updates within the across the autonomous system. Correct? So that's one concept, that you can see that you have different autonomous system inside same autonomous system. But what about AS500? When AS500 will see, he can see only AS300. He will not see the inside autonomous system, and that's the key here. Now the configuration is again straightforward, but it's like a little bit tricky. So first of all, this 888 is part of 300, 777 is part of again 300. So here you can see that router BGP Confederation identifier this, then router Confederation peer is this, then neighbor this, neighbor this. So you can see this configuration. If you go and check, you'll find that inside the configuration you have to think that these are the eBGP peers, and inside that these devices can peer, but they are part of the main group, that is 300. So your 888 and 777, they are part of the identifier 300. Again, you can see that BGP Confederation peer is 77, so for him he is the peer. This is the configuration for router B. Likewise, if you go and do the configuration for router A, you have to follow the same step. So you can see that step number 1, step number 2, step number 3, and then this is the same one that we used to use, correct? And then finally, the remote AS that he has is the having the AS 500. Okay, so these are the steps that we should follow, and you can go and check all these steps. You can refer the diagram, and then you can have all these steps as well. So let me quickly go back and let me quickly show you that if you are here you can see router B is a part of eBGP. It's part of Confederation group as well. So that's why you have this last line. Apart from that, you have these 4 lines. So it's tricky because see that he is part of main AS. He is doing the BGP with this AS, and he is doing the eBGP relationship. Now all these commands have been configured here, and you can understand all these steps. Now for outside device, the configuration will be straightforward, and what we have discussed earlier, neighbor and the remote AS, that's it. All right, so final topic for this session is the peer group. Why you want to use a peer group? Again, to increase the performance of BGP, to reduce the number of line, to reduce or to optimize the processor and the memory uses. You can use peer group. So suppose I have 10 different neighbors and all those neighbors has 6 command that is common. So what commands will be common? So for example, remote AS, update source, Route-Reflector client. These things are common. And I have 10, for example, I have 10 devices. So 10 into 3, that means 30 configurational lines you can put inside the peer group. So next, what you have to do, you don't have to write all these codes. Rather than you can go and use a neighbor 1111, for example, peer group, my group. Neighbor 2222, peer group, my group. That's it. Neighbor 333, that's it. So you are saving a good amount of code, and apart from that, it is effective way to optimize the process and the CPU cycles. Okay, all right. So what I'm going to do in the next lab, that I will perform the task related to Route-Reflector, and again we can go ahead and we can add the peer group as well. There are very less number of people that we know that they are using Confederation. So, and even in this syllabus, it is not required that you do the lab or do the CLI configuration for Confederation. But just for understanding purpose, I have given this notes and you can refer this. Okay. Even in our CCNP course, it is not required to do the CLI configuration, at least for this section 3.2 for Route-Reflector. But for future perspective, to understand more about BGP and their coding and stuffs, we should understand the at least the route reflection and the peer group. Now we have the lab related to route reflector client and the peer group. Here you can see the topology diagram. We have R1 router and then switch 105, 101, 103. They are inside one AS. Already we have done the setup, like we have IGP as EIGRP running in AS200, and then we have eBGP relationship between AS200 and 100. So what I'll do here, that we have one loop back. You know that we have loop back here in AS100, and that loop back I will go and advertise. So for example, I can go to my BGP 100 and we have various methodology to advertise a network. One of the method is to use the network command and then give the exact mask. Now once we advertise this, I can go and verify this inside the peer router. So I can go and check show IP BGP, and here you can see that I am receiving this route. The next hop is 10.11111. The AS path is 100. Now let's see if you check the diagram. So 111 loop back is coming to this device, this switch actually 105. Then let's see that how it is reaching to 101 and 103. So the same command show IP BGP, that's the BGP table. I can go and check to 101. 101 again, it is coming via this next hop. It will show like this only because eBGP next hop are not getting changed automatically. We have to run a command, so they will change the next hop. Now finally 103. Again, you can see that next hop is this. Now one thing I want to highlight here is that when you go and check the output in 105, you can see that you have the asterisk and the greater than sign. This asterisk means that it's a valid, and this greater than sign is best. So it's a valid best route that it is coming to 105. But if we go and check 103, 1, so it is not telling that this is the best. Even if again further down the line, if you go to 103, it is telling that it's not the best route. That's the one thing. Second thing, that since we have created full mesh iBGP relationship, so if I go here and check show IP BGP summary, so we have the relationship with switch 105 as well. So what does it mean? If I go and check the BGP configuration, and if I go and remove this configuration, that is, I don't want the neighbor relationship form with the switch 105, and then obviously I should go and remove these subsequent lines. Now if we go and check the BGP, here it is. Now what I can do here, I can go and clear the BGP, since this is the lab, so I can use IPBGP star, but be very careful if you're running this command. There are chances that thousands of route will get refreshed. So that's the reason we are using keyword like soft. So this is soft to reconfig inbound and outbound, and inbound or outbound, like that we are using those keywords. All right. So now if I go and check show IP BGP summary, and we can see now that we have only one neighbor. And if we go and check the show IP BGP, that's the BGP table. So let me go and run that command, show IP BGP. I want to check the BGP table. Now you can see this BGP table is gone. Why? Because that's the nature that the BGP has. So the routes coming to this, because they are directly eBGP peers, and then he will advertise to this. But 101 will not advertise those routes to the other devices. Okay, and that's a loop prevention mechanism we have inside BGP, until unless they have in full mesh or route reflection or sub AS or this confederation. So now what we'll do, that will go ahead and make 101 as a route reflector. So let's go and do the configuration for 101. All right, so we'll go here to 101. We are inside 101. I can go to router BGP 100. Then what neighbor we have? The AS is 200 for 101. So we have neighbor. Let's check the neighbor. We have this command. We can go and check. So I have 103 and 105 as my neighbors. So I can go to the neighbor, and then we can go and use as a route reflection client. So both for 103 and 105, I want to make this as a route reflection client. So 103 I have made it. Now if I go to 103 and if I go and check show IP BGP, still you can see that they are not learning the route that is coming from 105. So what I can do, that again I will go and make this neighbor as a route reflection client. And now if you go here to 103, that's the bottom one, you will start getting the update from router number 1. So it will be like it is coming from here, and then it will go here. Since he is the route reflector client, he will reflect the route to 103. And same is true. If the routes are coming in this direction, he is getting the routes, then he will go and reflect the routes to 105. So both ways you will find that it is valid. All right, so let's see this. Because BGP updates, they are taking some time to get update. It's taking some time. Let me quickly see this. Do I have the relationship with 101? It's there. I'll go and do clear IP BGP star. Now it is showing idle because now it is up. So I have my table that is up. Now I told you one important thing, that whenever we are getting the routes, what is happening in case of iBGP. So you got the route, you know who's the next hop. He got the route, and his next hop should be this device, correct? From where I am getting the route. But if you see it, you will find that the next hop is still 10.1.1.1.1. That's the problem we have with the uh, iBGP relationship. So what we can do here, we can go to 101 and we can make, say, neighbor. So who is his neighbor? Say 103. So neighbor, before doing that, let me quickly show this if all the BGP configuration is correct. It's correct. So I can go to neighbor. Hey, this is the neighbor, and you know your next hop is me. Okay, and likewise this router, we can tell router BGP 200 neighbor 101, your next hop is me. So this guy, your next hop is me. Now if you do this thing, if you go to 101 and if you check show IP BGP, you will see that first of all I need the best route here. Okay, so here you can see that 105, he is telling 101 that next hop is me. Hey neighbor, this is my neighbor, your next hop is me. So that means if you go here and check, this should change. See, it's got changed. It took some time, but it got changed. Now if you go 103, now you are getting the updates. Even we don't need this command here to 101. If I go to 101 and if I remove this command 200, that is no neighbor 103, I'm your next hop self. Before pressing enter, if you go here to 103, who is his next hop? It is showing that its next hop is 105. That's okay for this point of time. So I can go to 101 and I can delete this. We can clear the routes as well, but ultimately we can see here that the target is achieved. So without having iBGP relationship, with help of Route-Reflector client, 103 is able to get the routes from the eBGP from other AS whose actual AS is 100. Great. Now the second thing that we have to do is to do the configuration related to BGP peer group. So if you go again and check the configuration, although I have one command, I have two commands, very less lines of configuration I have here. But if I go to 103 and if I go to 101, and 105. So if I go here, show run section BGP, I have more number of configurations, so that I can reduce. So how we can do? We can create the peer group. I can go to 200. I can make neighbor, and then you can see the name of the peer group, say BGP Peer Group, BPG. That's just the name. Then what I can do here, that I can go and give the peer group. That's it. Now next, what we can do, say neighbor BPG, and what's the remote, say remote AS 200. Actually, I'm making this just for the iBGP relationship, so that's why I'm using this. Then again, I can go to neighbor BPG, update source loopback 0. Then again, I can go and check the other commands. So let me quickly go and check show run section BGP. So I have taken this command. I have taken update source loopback command. Then I have one more command, that is Route-Reflector client. So for that also I can use it. So neighbor say BPG, and then Route-Reflector client. Alright, so once we have these commands, obviously I'll go ahead and I will remove these configuration. This is not required now. So once I have these, then I can do neighbor, say this, and peer group is BPG, then neighbor, say 105, and the peer group is BPG, correct? And if we go and check the so for that, if we go and check the configuration, where we are, I think I lose this. Run section BGP. All right, so here you can see that now I have the peer group, and then neighbors are mapped with the peer group, correct? Even I don't need this command. Say I should remove this, is not required, taken care by peer group, and this is not required, taken care by peer group. Now think that suppose if you have more number of iBGP table or relationship, still what will increase? Only this line, correct? So now you have template where at least your 3 configuration lines are constant. That will be recalled by all these peer groups, correct? So now what I can do, I can go ahead and check show run section BGP, and I have an iBGP command. So what I can do here, that I can copy and paste. So for example, these 4 lines here, and then my neighbor is this 103. Actually I don't want, because we have removed that, and this peer group is a BPG. But suppose if you have more number of peers or the neighbors, then you can go and do these commands, correct? Then obviously I can go and do no for this, and finally no for the neighbor command that we have with 101. We can go and check show run section BGP. We can go and check show IP BGP summary. Seems one is gone. Show run section BGP. So here you can see that I should have that neighbor command that is not showing here. So finally what I can do, I can go to neighbor, say 101, 101, 101, 101, and then the peer group is say BPG, and we can check to show run section BPG, that is BGP. Alright, so here you can see that you have the template, and then you're calling that template with this command, and our BGP is up and running. So this is the way that we can do the peer group. This is the way that we can go and do the configuration for the Route-Reflector as well. We have very important topic, BGP best path selection. We know that BGP has a long list of attributes, and with help of these attributes, BGP used to provide best path. So what are those? Let's understand those first, and then next we have series of lab, and we'll test all these attributes, at least the important path selection attributes in the lab section. So how BGP providing the best path selection criteria? BGP contains multiple routes to the same destination. It compares the routes in pair, starting with the newest entry and working towards the oldest. Now, if you see that how it is going to determine, so suppose if I have multiple paths to reach a certain destination, and then I'm going to check, means BGP is going to check criteria A, B, C, D, etc. in order to provide, okay, if this criteria, so I have to go via this path. If this criteria, I have to use this. If this criteria, I have to use this, like that. So this is in the order. First of all, it will go and check the highest weight. Then it will go and check the highest local preference. Now the weight and local preference we'll see in the lab section as well. We have following lab with that. You'll find that weight and local preference, at least local preference, is one of the attributes that is mostly used. Now both the weight and local preference, they are dictating the best outbound path. So what we are doing, we are applying the weight and local preference, say attribute values, or these values in the inward direction. So we are going to apply to the inward direction. That's the key actually. So where you're going to apply these, and to whom he is going to affect. So we are going to apply in the inward direction, inbound, and then they are going to dictate the outbound path. So that's the important thing that I want to cover. Now here you can see the order. So let me go back. Weight, local preference, locally originated route. We know that if it's local originated route, their next hop will be 0000. That means it's a self-originated route. Then the AS path. Now AS path and MED, the metric value, both are again important. So remember, weight plus local preference, both are very much similar. Then AS path and MED, these are the attributes that is used more and more in the production network. So AS path, we know that BGP is dealing with, or BGP is a distance vector protocol, and as per the AS, so you think that one autonomous system has a router for a moment. And then if you have to cross more number of A's or more number of hops or router, that means it is not preferred. So if I am reaching to certain destination with 3 A's versus 1 A's, that means that 1 A's means via the path I am reaching with 1 A's, that will be the preferred. So shorter A's will be preferred. Then the origin code in the number, so IGP over eGP over unknown. Then MED, again I told you that this AS path and lowest MED, both are very much similar, and even we have lab as well for these. Then BGP route type, eBGP over iBGP, eBGP will win. Then the age of the route, who is the oldest is preferred. Then the router ID, who has the lowest BGP router ID. Then the peer address, which router originate from the router with the lowest IP. So everywhere you will see that except weight and local preference where the criteria is high. Apart from that, AS, MED, then age, everything is lowest or the oldest. Correct? All right. So here you can see that weight and local preference are applied inbound, dictating the outbound. That's the key actually. So these 3-4 lines are the key. Inbound dictating outbound path, and AS and mid are applied outbound dictating inbound. So what does it mean? So at least in case of MED, and let me draw here. So suppose you have ISP1, ISP2, and then you have your local AS. Now in case of MED and AS path, if you want to prefer ISP1 versus ISP2, so then you will go and apply the either MED or the AS path, AS prepend. That's the key. Because you have to choose, because you are choosing the outbound, so you have one subnet XXXX and you want to prefer either ISP1 or 2, you can use this method. Now when we are going to use the local path, so in that case, say when you are going to dictate the outbound path, so suppose if you have 2 exit and you want to choose one exit via versus second exit, so that in that case you are going to apply the either weight or local preference. Obviously I'll go and clarify these terms in the upcoming lab, and we are going to check the scenarios as well. So here you can see that we have one situation, one scenario, that you have one route, say for example 192.1.1.0, that router D is also getting, router B is also getting. Now what I want that route should come or should preferred via router B. So in that case, what we can do, that we can go to router A, say router A, and then we can give neighbor and then the wait command. That's the one way. The other way, nice way, is that we can go and use the route map. So then what we can do, we can create one ACL or prefix list or access list, and then we can create the route map. We can match the prefix list, and then we can set the weight, and then we can go and apply to the neighbor. So here you can see the direction is in for the outbound traffic, correct? So to reach this network, I have applied weight to my neighbor, and that neighbor, so that means router A will prefer B to get these routes, correct? Again, you have the local preference. In local preference, the same thing, only the way that we are going to do the coding will change. And here you can see that we are going to apply now. Local preference has little bit difference with weight. What is that difference? So unlike weight attribute, local preference is passed on to iBGP peers and sending updates. Local preference inform iBGP router how to exit the AS if multiple path exist. So now what we can do, that local preference, even I can go and apply to these guys. So suppose local preference here, if I put 200 and if I put local preference 100 here, obviously this path will be preferred, correct? So that's the use of local preference. And here you can see that we have the example, but here we'll check the route map way of applying the local preference. Again, you can see here the direction is inbound. So here we are at router D, or maybe at router B also, there's no problem. So what we are doing for router B and D, here you can see that B and D, lower is better. So here if B is 200 and D is 300, obviously the traffic will come via this B, because his local preference is 200. Likewise, you can see here in the policy, we can create the policy for B and D as well in the upcoming lab section. So I have this route, same way we have created the route map and we have applied it. I'm matching this, and then I'm setting the local preference as so for example 300. Okay, and then I'm applying in. So here you can see that is 1.2, that's my neighbor. Then I'm applying in. Likewise, I will apply with local preference of 200 to router B. So obviously router B will prefer. Okay, so here you can see there's difference between wait and local preference. The local preference is passed on iBGP peers when sending the update. So that's actually the main reason you will not find use of wait more and more, because anyway the wait is Cisco proprietary as well. So mostly you will find the use case with local preference. The same thing we can do with wait with local preference, so better use local preference. And in the lab section, so we have the lab section. In the upcoming session, I will go and perform this task of wait and then local preference, and we'll see that how we are applying the in rule to affect the outbound traffic, correct? All right, so let's stop here. We'll start the lab now. Let us perform the lab task. In the lab, what we are going to do, first of all, I'm going to show you the entire setup that we have. Here you can see that we have 4 different autonomous systems, say AS50, then AS100, AS900, and AS200. Now from AS200, you can see the iOS, the router is router 7, for example. There I have one loopback, and that loopback is loopback 7777. 7.7.7.7, and that particular network I am advertising with BGP network command. So they will go and reach to AS 900, and then it will go and reach to AS 100. Inside AS 100, it will go and reach to router number 2. So before showing a complete path and how it is reaching, let me quickly go and show you the configuration that we have. So if I go here and check the configuration, show run section BGP, here you can see the configuration, and these IPs that you're seeing over the interface, these IP addresses you can refer the topology diagram as well. So router 1, here you can see the router 1 has very minimum configuration. It has one interface, and then we are advertising one of the network. Then router number 2, you can see the BGP configuration, where we are running Eigrp inside the AS, and then we have 2 neighbor peer command, router 3 and router 4, and obviously we have one eBGP with router 1. Likewise, the configuration, BGP configuration for router 3, So let me do this. So here you can see the configuration for router 3. Router 3 in the diagram, you can see that it has eBGP relationship as well. So on the top you can see eBGP relationship with AS900. Likewise, we have router 4 configuration for BGP. Then we have BGP configuration for router 5, and then you can see router 6 and 7 as well. This is router 6 configuration, and finally router 7. Now what we have done, you can see that inside router 7 we are advertising one of the loopback with the BGP network command, and then we are going and seeing that how it is reaching to router number 2. So if I go and check show IP BGP, first of all I'll show the BGP table. So clearly you can see this AS is getting prepended. So the originator for that is AS200. So here you can see this 777. So the originator, then next is 900, and then it is reaching to AS100. Now here you can see that you have valid and best path, and who is the valid and best path? So it is telling 172.1.7. Now if you go here and check 172.1.7, so this is the best path. Via this it is going and reaching here, although you have the alternate path as well, that is 172.1.6. So 172.1.6, that's only the star we have, and the star means valid. So that means if I go and check show IP route for this particular network, and let's see. So here you can see that it is coming via 172.171.2, and they have learned this is the router tag and how many hops, etc. Correct? So it is learning via this. So what I want at this point of time, that it should go and learn via this particular neighbor, not via this neighbor. Other thing that we can see here, that is this changing the next hop? So if I go here and check the diagram, so obviously whenever it will go and move to the eBGP, then it will change the next hop, correct? So from here, either from router 3 or router 4, it will go and reach to router number 2. But suppose behind router 2 you have one other router in the same AS, so at that point of time you can see some differences. So you have to do some next hop self command, correct? So suppose if I go to router number 1, and if I check show IP BGP, now since this is the eBGP relationship, so for this route, who is the next hop? So he is saying that his next hop is changing, that's okay. But if router 1 will be also inside AS100, then it will be the problem. Anyway, so what is our target here? We want to have, or we want to learn this particular route from this next hop, or from this peer. So let's use the wait attribute. Before that, I want to create IP prefix list. So IP prefix list, say loopback 777 is the name of my network. Even I can go and give the a sequence number, and then I can use this if I want. So sequence 10, and then permit 7777/32. Alright, then I'll go and create one route map. Say my wait permit 10. What I want here, I want to match. So let's see, match the, let's see what is the option we have. So match the IP address, and that is the prefix list. What is the prefix list we have created? This loop 777. All right. Now what I want to do with this, I want to set the weight, say for example 8989. Then I will give one default statement for route map where I will not match anything, say for example 100. You can go and check the route map configuration. Say route map. So what we have done, that we created one IP prefix list. We have matched with the route map. Then we have set the width for that. Now we should go and apply this to the neighbor. And which neighbor you want to apply? So you want to apply this with 172.161. Sorry, we want to apply with this neighbor, that is 10.1.1.2. So I'll go and apply with say 10.1.1.2. And what's the route map we have? The route map name is my TT. Because this is weight, so I want to apply in the in direction. So here you can see that it is telling that okay, so this is not the configuration that we have done. If you go and check, we have created the neighbor with the loopback, correct? So we should apply the loopback statement. So here you can see, so I should go neighbor, and the neighbor is router number 4, that is 444, and then the route map, and that will be in the my weight in the in direction. All right, now if you go and check show IP BGP, now clearly you can see that the next hop is not get changed. So for example, that's a problem actually with iBGP, and that's just to prevent from the loop. So that's a loop prevention mechanism. So what does it mean? That here you can see when the routes are coming, say 77777, and when it is entering to this AS, they are putting their IP as a next hop. When it reaches here, it should put these IPs as a next hop first of all, correct? So we should go and do a small changes in the configuration. So let me go and do the small change in the configuration. So let's do this. I can go to router number 3, say router BGP 100. I can tell neighbor 2222222, next hop self, and likewise we can go to router number 4 as well, and then we can tell router BGP 100 neighbor is next hop self. Now if you go here and check show IP BGP, you will see that next hop will get changed. Otherwise I'll force this BGP to converge. Here you can see at least next hop is not get changed, but the priority, I can see that weight update has been done and it is going via the bottom router. So here you can see that weight has done his effect, but it should change the next hop as well. And now you can see that they have changed the next hop. That's the correct actually. Weight has been changed, next hop has been changed. So this is the way, this is the use case with the weight. Now what we want here, that instead of wait, the same thing I want to do with the local preference. So first of all, I'll go to router BGP 100 and I'll remove this command. I don't want this wait, for example. So we don't need this wait. And next, what we want to use the local preference. So for local preference, let's go and check the route map as well. Route map, because now for local preference I want to create one route map as well. Now this time I don't want to apply this policy to R2. Rather than I want to apply this policy to R3 and R4. So how the local preference is working, that they are much more intuitive than wait, and their attributes can flow inside the AS. That's the key we have. So what we can do here, first of all, we'll see that how the 777 is getting reached to router number 2. Then here over router 3, I will set the local preference as 300, and router number 4, I'll set the local preference as 150, because I want that it should go and prefer this direction. Or suppose what we can do, that I'll go and create one more network here. So for example 88888 as well. Already we have 7777. I'll create one more 8888. So 77777, for example, should go in this direction, and 888888 should go in this direction. So how we can do that? Okay, so let's think that and let's try to perform that task. All right, so the target here is that 7 should go via router 3 and 8888 should go via router 4. So primary, secondary, secondary, primary, like that. So what I try to explain here, let me go and show you here. First of all, I go to router number 7 and I'll create one more loopback and I'll advertise that as well. So I can go here and create say loopback 8, IP address 88888, and then let's go to router BGP 200, and then we have the network 888 with the mask of 255. Now if I go here and check this same BGP route here, so now you can see that 8 is also coming and getting here. Now it is coming 3 and 3. So both the update, they are coming via router 3 that we don't want. For 7, so for example, I want that it should come via router 3, backup will be router 4, but 8 should come via 4 and 3. Okay, so primary, secondary, and secondary, primary, like that we want to use. What we can do here, that we can go to now to router number 3 and we can create the prefix list first. So I'll go and create IP prefix list, say loop 7777, sequence say 10, permit 777732, and then I want to create one more loopback, because the deterministic criteria, I want to put some condition inside the route map. So I can go and create the network statements like this. Okay, so I have two different IP prefix list, and even I can copy and paste the same configuration to 4 as well, just to save our bandwidth. Alright, so once we are here, then we should go and create the route map. Say local pref, what I want to this route map. Say permit 10, match IP address, and that is the prefix list 777. For this, I want to set the local preference, say for example 8888. Okay, then I'll go to the other statement, that is say for example 20, and then I'll go and match the address, that is this guy here, and then I want to set the local preference a little less, so for example 88. Okay, and then I have another default route map like this. Alright, so here you can see the strategy for 777. We have the higher local preference. Likewise, I'll go and I'll create one more route map here to router number 4, where I want to match the 888. So statement number 1, I'll go and match the IP address, that is 888, and then I'll set the local preference, say for example 9999, that is very high, and then I can go to the other statement where I want to match the address, that is this guy, and then I can set the local preference 99. So the idea behind this is that for one of the prefix lists, say for example for 888, what is the local preference? Very high. And here for 888, what is the local preference? Very low. So just the condition. For 7 we have high, for 777 we have high local preference, for 8888 we have low local preference, here the reverse. Correct? Now we should go and apply this to the neighbor. So let me see that who is the neighbor. It's a neighbor IP, router BGP 100. My neighbor is this guy here, and then the route map is local preference in direction. Correct? Now here also I can go and check router BGP 100. My neighbor is this guy, and the route map that we are going to use is the local pref is the name, and then the inward direction. Alright, now if I go here, so for 888 the 4444 should be the best path. So here you can see, now we can see clearly that they are losing the backup. So here you can see that now the routes are converging and they are getting set with the correct local preference. But still, if you want to clear the IP BGP star, you can go and do that, and then you can go and check show IP BGP. So it will take some time, but it will build the route, and clearly whatever our target was, we are able to achieve that target. Correct? So this is the way that we can go and apply the local preference. So likewise, we can go and testify AS path prepend and MED. Now the difference between AS path prepend, MED and the local preference and the wait is that the rules for prepend and MED we are going to apply in the outbound routes that will dictate the best inbound path. This is just the reverse that what we have studied and what we have done. So now in this case, suppose if we have route 10511 and you want to select B versus D, means how it is going to reach to router C and router E. So in that case, what we can do, say for example, in case of AS path prepend, we know that AS path again is like number of hop count. So if number of A's are less, that will be preferred. So suppose if I go in router B and if I add A's prepend 100, 100, 100, 3, 4 times. So that means the same route that C will get from D, E and C, that will be AS 100 and AS its own AS 900, like that, rather than it will go and get the route with AS 100, 100, 100, 100s multiple times. So obviously it will go and prefer and learn the route from D. So here you can see that same way we can create the access list or prefix list, we can create the route map, and then inside the route map we can go and set the AS path prepend. We can use any number, so for example 200, 200, and then we can go and apply to the neighbor that we have applied for example wait, and we have seen for the local preference as well. 172.161.2, so we are applying to this neighbor. That means we are making the path B to C as a worse. So obviously you will see that the traffic will be preferred from 172.171.1, and here you can see in the output that yes, we have the valid and best route via 172.171.1 rather than 172.161.1. Now the same methodology can be used and same thing can be achieved actually with the MED as well. MED is nothing but multi-exit discriminator. By default it will be 0. We know that metric values are lower is better. So suppose if you go to router B and if you set higher MED value, so the router D to E to C path will be preferred. Again, the same way you can create the ACL, you can go and create the route map, you can match the access list or the prefix list, and then you can set the MED value, metric value, for example 200 here. That is much more better than bigger than 0. So that's the reason here again you can see that 0 is better or lower than 200, and that's why the traffic is preferred over A to D to E. So same thing we can achieve with AS prepend, and same thing we can achieve with MED as well. Alright, so let's stop here. In 3.3, we have to learn and understand about wireless technology, basics of wireless, the AP, how the APs are going to join the WLC or the control plane, how we can do the baseline troubleshooting. So let's start with the basics of wireless. Now, wireless is very different than wired technology. We know that in wired technology, you have routers, you have switches, you have cables, modem, endpoint systems where you have the NIC card, you are connecting the interfaces, and this is the way that network infra built. Apart from that, wireless technology is free from media. That is not 100% true. Free from medium is still in wireless technology. You have air as a media, or you have some sort of transport, but not the physical transport. So maybe air, maybe wire. Inside wire also, the wireless waves can go from one place to other place, but that is again not the exact use case we have. We'll see later on in this course that we have different type of frequency range or different type of wavelength for different wireless frequency, and which particular range we are going to use in the LAN. So it's actually broad thing, and in that broad we are using one small spectrum or one small slice of that wavelength for our wireless networking or for our wireless use. So let's start with a very basic, and then slowly we'll add things in this. We'll add some more and more concept in this. So here you can see in the diagram that you have sender, you have receiver. That's the uh, normal way of communication. So if there is receiver, if there is sender, if they are connected, then only the communication will happen, correct? Now in case of wireless, here it is showing that you have a rope in between sender and receiver, but you have invisible media, say for example in wireless, but you have the waves. So for example, I'll use the term wave. So here you can see that you have the electric and magnetic field in the diagram. You have E and M, and they are propagating inside the air. So air is the media where it is propagating. Now, if this wave is not constant, so suppose you start one pulse and stop, so that will not reach to the receiver. So that means your wave should be constant. So it should have constant height and down. So here you can see you have up and down, means the flow of the wave you should have to reach to the destination. So at this point of time, with this slide, you'll understand, okay, we have media air, and then we have the wave. That construction of wave is with electric and magnetic. So we have electromagnetic wave. Now again, you can see that you have one sender who will send, and then you have a receiver who will receive. So at this point of time, I assume that everyone knows that we have the access point. We know that you have access point nowadays in all the networks. So you have access point who will send the wireless say waves, and then you have, for example, you have laptop where you have the receiver, so he is receiving, and the access point who is sending. Okay, so in that the communication will happen. Your receiver should have capability to receive, and the sender, now the sender can send in all the direction. Later on we'll study about antennas and all, and we'll see that what is the use case of the direction of sending the frequencies or sending the wavelength or sending the signals. Okay, so you have sender, you have receiver. All right, then what is frequency? Frequency is the up and down cycle in 1 second. Okay, so let me show you the definition. I have taken the definition as well. So here you can see that frequency, the number of times the signal makes one complete up and down cycle. So when you go up and down in 1 second, so suppose if you are making 4 up and down in 1 second, so that's 1 second your frequency is 4 hertz. Now again, what is hertz? Obviously, Hertz, this is one of the scientists who has done research and developed or given his thesis and paper related to electromagnetic wave, and wrote so many books. All right, so Hertz is the most commonly used frequency unit and is nothing other than 1 cycle per second. So now you are sending the wave. Remember, you have rope and you are sending. So you are sending the wave, and in 1 second, how many up and down you have? That is 1 hertz. And suppose if you have 1,000, or if you have tens of thousands or hundreds of thousands, etc., thousands of thousands, so that will be determined as a hertz, kilohertz, megahertz, and gigahertz. We are very much specific about gigahertz in our wireless LAN network. That will go and discuss. So now this is the thing I told you, that we have wide range of a spectrum. So we have cosmic rays, gamma rays, X-rays. We know that some of things are coming from sun. Some of the rays are spreaded in the space. Some of the rays we are using for medical healthcare as well. Ultraviolet light, microwaves, we know all these things. But what we are going to use, here you can see in terms of gigahertz. So if you see the spectrum is starting from 0, I am focusing upon, or I'm focusing here, let me focus the spotlight, 1 gig to 10 gig. Okay, so 1 gig to 10 gig slice that we have. So in that we have 2.4 gig wireless and 5 gigahertz wireless, and then again you have the bands for that. So we are going to focus on these spectrum, and these frequency actually we are going to use inside our wireless network. Okay, so for example, for 5 gigahertz, you can see it's starting with 515 and going to 5.825. Remember, this is in gigahertz. Now, if you convert this into mega, so that means that 100,000 megahertz, and let's make this easy. So, say for example, you have 10, then 10 3, then 10 6, and let me make this as 10 9 if I'm not wrong. So 10 6 is your mega, 10 3 is your kilo. So this is your kilo, this is your mega, and this is your gigahertz. Okay, now suppose this is the range you have. So for example, 5.15 to 5.250. So what is the difference? So difference is actually 100.100 gigahertz. And now if you convert this into meg, so what will happen? Maybe 1 megahertz, because then you have to multiply this with 1, 2, and 3. So that means I think 10 megahertz. 10 megahertz is 0.1 gigahertz, correct? All right. So that's the difference of 10 actually we have. So everywhere you will see that here you have 10 meg difference. Again, if you go and see this, so 0.100, 10 megahertz, etc., etc. Means that's the band we have. Let me show you in the next slide. We have some examples related to that. So here you can see that all these spectrum range that it is shown here, and the same thing, there's a difference in between the spectrum, and that is defined as a channel. So suppose for this particular range, that is 2.4 gigahertz, starting with 2.412 gigahertz, reaching to 2.484 gigahertz, we have 14 channels. Now for one channel, what will be the difference? So this difference will be, say for example, 2.417, although it looks very small, but the value is big. 412, that is 500. This is in gigahertz. That means that you have 5 megahertz. So again, if you multiply with 1000, you will get 5 megahertz. Okay, so these are the calculation we should know. Again, it's very much mathematical, and little bit physics is also involved. So what about the channels? Here you can see the channels and the difference in between that. Let's continue. So here you can see that you have 14 channel, and in between that gap is 5 megahertz. Now again, if you see the overlapping and non-overlapping channel, you'll find that there is one condition. So if the signal bandwidth less than, or it should be less than, the channel width. So here you can see the signal bandwidth and the channel width. If signal bandwidth is less, there is no overlapping. But if you can see that signal bandwidth is more than the channel, so in between 1, 2, 3, 4, you have a small channel width. So in that case, you have the overlapping. Okay, so these things should be considered. Again, what's the concept of phase? Phase means how much shift there in the actual cycle. So suppose in the first diagram, you can see that there is 0% shift or 0 degree of shift. So that's how the two line is showing in parallel. But suppose if you have shift of 30° or 60° or 180°, then you can check the phase shift. Okay, so again, these are purely terms related to physics, some sort of electrical and magnetic signals. Again, we are studying in the networking. All right. So what are the terms that we are going to use more and more and more? So you will find that frequency, the hertz, then the wavelength, then the channel width, etc. So one of the key term we have is the wavelength. Now what is the wavelength? Wavelength is the length for one cycle. So the wavelength measured of the physical distance that a wave travel over a complete cycle, and that will be represented by lambda. So lambda define the wavelength. For 2.4 gigahertz signal, the wavelength is 4.92 inch. For 5 gigahertz signal, the wavelength is 2.36. Okay, so again, this is the mathematical calculation, the length for one cycle, that's the wavelength. Likewise, how we are going to measure the power. So here you can see that RF power, and that is in dB, decibel. If you see the diagram, you'll find that the power is defined, or this amplitude is defined in between two two peak. One is in the positive direction, for example, one is in the negative direction. So the maximum length in between two peak, that will give you the amplitude. And this amplitude we are going to measure, or it will be measured in either watts or milliwatt. So again, you can see a new term, and terms are coming more and more. So when power is measured in watts or milliwatts, it is considered to be absolute measure. Again, we have one mathematical formula. We're going to discuss about that. But important thing here is that for wireless LAN, the power will lie in between 100 milliwatt to 1 milliwatt, and if you convert in watt, that is 1.1 watt to 0.001 watt. So better will go and measure in milliwatt. So power will be in between 100 to 1 milliwatt for wireless LAN. But for other services, you can see that for AM radio station broadcast, this is 50,000 watt. So you can see how much power it is. So for example, 16,000 watt for FM radio. This is huge power, correct? All right, so let's focus only on the LAN side, on the wireless LAN side, and let's try to understand the mathematics behind that. So suppose if we have three transmitter 1, 2, 3 in the diagram below, and you want to check the relative power between 1 to 3, so you can see now we have one mathematics. Better we'll go and check the mathematical formula. So what will be the power difference between T1, T2, T3? For that, it will be measured in decibel, and decibel is a mathematical formula in the logarithmic function. Now if you just completed your graduation in mathematics or BCA or maybe engineering, then it's very easy and convenient for you to check this formula in dB. So when we have, say, 10 base 10 P2 by P1, that means that this is 10 log 10 P2. Actually, divide means P2 minus P1. So you can think like this. It's not the exact, say, 10. I can take 10 as outside because 10 is common. So this means log 10 P2 minus log 10 P1. And suppose if we have some formula, so for example P1 into P2, so that means plus. That's the log function we have. Suppose if you have formula something like this, log P2 into P1, so that means we can take 10 outside. This means log 10 P2 plus log 10 P1. Okay, and absolute means that either it's a plus and minus, you are taking the magnitude of that or the module of that. All right, so now let's try to understand. I'll come back and resolve this, that if we have power 1 and power 10, so what will be the difference? Now we are not going to do the difference of power, rather than what we can do, that will go and measure the dB. Okay, so dB means, so for example T2 by T1, and then you have log 10, and then you have 10, that means that will be 10 log 10 to the 10, that means this will be 1 as per mathematics, so the difference is 10. Okay, I'll come back to this. We'll discuss more on this later on after 1 or 2 slides. So let me go and complete the slides first. So then we have three different law for 0. Suppose if we have same power, so the relative power difference will be 0, because if, for example, 10 by 10 will give you 1, and log 10, um, this is the base, so 1 base 10 is 0. Suppose, what is the law of 3? Suppose if you have a difference of 2, so if you are getting the value log 10 base 2, this, that will be 3 dB. And if you have 1 by 2 minus 3 dB. Okay, so what does it mean? It means, suppose 10 by 5 and log 10, and again you have 10, that means you have 10 base 10, and this will be log 10 2 here. Finally it will come to 3 dB. This is again the formula. No need to mug up at this point of time, but if you want, you can take the reference. You can check any mathematical book related to uh, decibel. Okay, all right, so say what is happening actually here. So this, what at this point of time we can mark this thing, that this value is 3. Okay, and 1 by 2 means minus, so this value will minus 3. Later in this same section, after one slide, I'll discuss more about that. Then we have law of 10. What does it mean? So if we have 10 base 10, that will be 1. Okay, so 1 into 10, obviously 10. 1 by 10 means minus, so then you have minus 10. Okay, great. So now we understand the law of 0, law of 3, and law of 10. Let's try to solve some of the questions. So here you can see, first of all, we have the summary table. So if difference is 2, then the power difference will be 3 dB. If it is 1 by 2 minus 3 into 10 plus 10 dB divided by 10 minus 10 dB. But again, what does it mean? So from this example, it will be 100% clear. So you can see in the bottom that A, B, and C, their power consumption in milliwatt, 4, 8, and 16. Now B is how much more than A plus? Okay, so let's try to understand. Now if you go and do B by A, you will find 8 by 4, that will be 2. As per the formula, we know that log 10 2 is 3 dB, correct? So that means B is equal to A plus 3 dB. Now what will be C? So C, again, you can see 16 by 8, that means 2. C will be B plus 3 dB. And what is B? B is A plus 3 dB plus 3 dB. That means A plus 6 dB. Okay, so this is the way that we can go and calculate. Now we can think that, oh, it's a very easy example if I have some complex calculation. So for example, in this diagram, you can see that you have 5 and 200. Okay, so how I can resolve this 5 and 200? So what we can do in this, that you can go and check, sorry, you can go and check like 200 and divided by 5, so that will be how much? 40. Now this 40 will be, the calculation will be 2 into 2 into 10, correct? So 2 means 3 dB plus 3 dB plus 10 dB, correct? So that means that E equal to 6 plus 10, so E equal to D plus 16 dB. So a little bit of mathematical calculation if you do, then you can go and check the relative power between two of the transmitters or two of the antenna. Right, so these basic knowledge are required when we are going to learn some other wireless technology. So what is dB, what is hertz, what is amplitude, what is wavelength, etc. All right, so we have three modulation technique that will come under 3 spectrum. So we have FHSS, frequency hopping spread spectrum, DSSS, direct sequence spread spectrum, and OFDM, orthogonal frequency division multiplexing. Now you can see that name itself is big, and we are going to discuss about exactly where they fit in the wireless LAN and which standard match which particular spectrum, correct? So if you go and check the technical detail like the physics and the electronics behind that, you'll find that there are so many things to understand one spectrum. So behind the scene, it's a complex mathematical and physical structure. Uh, so those things we are taking inside our digital world, in our networking world, and we are using it. So let's see that what exactly we are using. Although most of the engineers are using wireless technology, but we are not aware that behind the scene which particular spectrum or the modulation technology we are using with which particular standard, IEEE standard. So first of all, we have the FHSS, that is the early ones, means with the evolution or with the beginning of wireless LAN technology, we have this methodology, we have this modulation technique, we have this spectrum. So here you can see that it has a 79 channel, and you have problem as well, and we have some benefit as well. So what is the problem? Here you can see that the frequency hopping will follow this rule. So channel 2 will move to 25, then 64, then 10, then 45, like that it will jump. Now here in the diagram you can see that first of all it is supporting 2.4 gigahertz spectrum, and then you can see in the diagram that 2, then it is going to 25, then 45, then 64, returning back to 10, and vice versa. Now what is the problem? The problem here is that they are limited to 1 or 2 Mbps speed. Okay, that's one of the big problem, because nowadays we are looking for speed, and this is one of the biggest problem. Now what is good thing is that whenever we are talking about first evolved technology, it's actually easy to set up and use, etc. Now all other technologies, modulation technologies, are also easy to set up and use, but behind the scene, the circuit, the chip, the coder, encoder, etc., it's a little bit complex, and because it is evolved from one technology to other technology. So what is the solution? So then we have the next approach, a spectrum approach, that is DSSS, direct sequence spread spectrum. It can give you higher throughput. So for example, we have one summary slide by the end of this slide, so we'll see that. So it is going to give you, say for example, 11 Mbps of speed. That is still not enough, correct? And this is also falling into 2.4 gigahertz band. So here you can see FHSS and DSSS, both are falling in the same spectrum band. Their speed, overall throughput is, although 11 Mbps is good, but it's still, nowadays we are working in digital workplace and all, still it's less. The other disadvantage it has, that because their channels are overlapping, so they have only 3 non-overlapping channel 1, 6 and 11. Now what is the technology behind? So let's try to understand. Here you can see this technology, this diagram, that how the bits are coming, they are getting coded, means they are getting arranged, again they are getting packed inside the block, and then it is getting modulated, and then it is going outside as a signal. So how it is? So first of all, we have the scrambler. What it is doing, the data waiting to be sent in first scrambler, means whenever any request is coming, it's up to a scrambler. It will do some scrambling, and then how the data will go. Now next is the coder, and it's important what coder is doing, that they are converting data into multiple bits. So coder use is to convert the data, whatever it is coming from the scrambler. So you can see that data bit is coming, and then coder is converting that data into multiple bits. Each of new coded bits are called a chip. So here you can see in the diagram, all these bits are called as a chip. Now here we have DSSS uses 2 encoding technology. So maybe somewhere you have seen this short form. We have Barker codes and we have complementary code keying, CCK. That's a coding methodology. Now next we have the interleaver. What interleaver is doing? Again, it's important that whatever input you are getting, so obviously the data bits that you are getting from coder, the interleaver will spread this into separate block. So you have data, then you have bit, and then you have block. Data, bit, block. Finally, we have the modulation. Once the modulation will happen, then it will flow in the air as a RF signal. Okay. Now, more or less, the DSSS and the next technology, that is the OFDM, both are using same technology behind the scene, but in OFDM, you can think that you have parallel processing. So suppose that DSSS or DSSS, that they have this modulation technique for one stream of data. Now, if you do 64 parallel processing, or for example 48 plus 4 parallel processing, obviously your overall throughput will increase. So now suppose if you have 11 Mbps, you can multiply 11 Mbps by, say for example 52. So that much throughput you can get in terms of Mbps. So next technology we have, because we are looking for higher throughput and speed. So we have the OFDM modulation technique. What OFDM is doing, that it helps in parallel processing. That's the main thing. So here you can see that in contrast with OFDM sends data bits in parallel, that's the key, over multiple frequencies, all contained in a single 20 megahertz channel. Now there are technology, so they have guard for 12 subcategory, pilot for 4 subcategory, and data for 48 subcategory. Now guard will be there, but this pilot and 48 subcategory for data is going to be used, and you can think that you have that much parallel processing, or that much parallel signals in a row you have. So here you can see that you have 48 subcategory, and that's huge, correct? Great. So now sometimes you might see that OFDM, and again these are the theoretical things, having 52 subcategories, 48 for data and 4 for palette. This is because 12 guard frequencies are not actually transmitted, but they are silent in the channel spacing. So that's why we have the modulation for each data into 52 times. So you have 52 times subcategory. Now let me go and show in the diagram. So here you can see in the diagram that you have coded data, then you have 48 subcategory, and inside subcategory you can see, and then you have the channel. So you have 20 megahertz channel, and it is a spread across 48 subcategory. Now OFDM, obviously they have to use a scrambling coding, interleaving, and modulation, but for all subcategory, and that's why it's a parallel processing. So whatever we have studied in DSSS, the same thing is happening, say for example, 48 times parallelly. Okay, we have IEEE standard. So let's see that what a standard we have. First of all, this 802.11 was introduced on 1997, and then after 2 years, 802.11b has been introduced. Here you can see that it is supporting 2.4 gigahertz band. The modulation is DSSS, and the data rate support is up to 11 Mbps. Now, 11 Mbps is not a big speed nowadays in the digital world. So that's why we need some higher throughput. So next we have 802.11g, where they are also in the band of 2.4 gigahertz, but here you can see that the data rate start from 6 Mbps going to 54 Mbps. So it is giving much more throughput with compared to 802.11b was introduced in 2003. Now still the problem here in this 802.11g, here you can see that although you have the bands, different bands, so we have a note here that G and B use complete different transmission types. One is using DSSS, one is using OFDM, and these technical details we have discussed in the previous section. So that means the devices who are supporting these transmission types, they will not communicate because they have the different communication channel, they have different signals. Okay, and the other thing that they have very less non-overlapping channel as well. So that's why we have 802.11a. Although this will also support 54 Mbps, but it is using different channel. It is using actually different band, 5 gigahertz band, but it has long range of non-overlapping channels. So here you can see that band is different for 802.11a, that is 5 gig band, and they speed from 6 Mbps up to 54 Mbps. Now at this point of time, still we can see that 54 Mbps is not that digital workplace actually looking for, because now we have say 100 of Mbps of LAN speed. We need fast throughput. We have different type of devices in the workplace. We have IoT based devices. We have so many mobile devices. We need fast speed. So that's the evolution or the introduction of 802.11n. That is supporting 600 Mbps. That is the theoretical maximum, but it is supporting a huge bandwidth. The data rate is huge, and they also have very much non-overlapping channels. The good thing about 802.11n is that here you can see in the summary that they are supporting both the band 2.4 and 5. So in this list, we can see that 1997 we have 802.11, where we have both DSSS and FHSS. We have a study about this in our previous section. The speed was 2 Mbps. After 2 years, 11.b came into the picture, whose modulation is D SSS, which is supporting 11 Mbps. Then we have 11A, which is using OFDM, 54 Mbps, but you can see the band is different. So 11A and 11G, you can see the band is different, but they can have the same modulation technique, and their overall throughput is 54 Mbps. Now again in 2009 we have 802.11n, where they are supporting both the bands. Their bandwidth, you can see their modulation is OFDM, but the throughput can be theoretically 600 Mbps. All right, so let's just stop here. Next topic, we have interference and effect of physical object. Now interference is nothing but the noise, and this noise, that means that you are sending some signal and it has some overlap. Now here you can see that overlap maybe with the same channel, so different transmitter having same channel and they are overlapping. Now in real world, this co-channel interference is often a necessary evil. It's too bad. Means your signal will get degraded as much as. So we should plan it. We should put the access point in a proper manner. So there should be less interference or no interference. Now that's the one thing. So here you can see that two nearby transmitters should never be placed in the same channel because their strong signal would be more likely to interface. That's the one case. The second case we have that if we have the neighboring channel interference, so what is happening that now I have transmitter A with channel 6 and transmitter B with channel 7 and they have the overlap. Even in the 5 gigahertz band, still we know that it has a long list of channels. Means it has so many different channels that the way or the chances that they can overlap is less. Still, the best practice suggests that you should avoid placing a neighboring access point on nearby, even it is a 5 gigahertz. So if you think that still there is less chance of doing the interference, but still we should plan the placement of the access point in a way that they should not object or interference the signal of each neighboring access point or the channels or bands. All right. Next topic we have the effect of physical object. So what is happening? Say you place your access point and then it is in contact with a surface who is reflecting the wave. It's very much like light. We know that how the light wave are reacting. If you put light wave in front of mirror and if you put that in a certain angle, it will reflect. Even if your surface is smooth, in that case, the signals, RF signals will also reflected or get reflect. Now, you can see in this diagram that, okay, there may be chance that the receiver is MIMO, multiple input, multiple output. So here you can see in the diagram that the sender is sending the signal with 3 different direction and receiver, because he know that how to get from the multipath, he can get it. Still this situation is okay, but suppose if you have single uh, radio chain, or the receiver has only single radio chain capability, means they can take the signal just from one source. So in that case it will become worse. Obviously you can see the signal will get degraded, say in case of A and C, if we have one A, B, C, like that. Okay, so second thing we have the absorption. What will happen in absorption is that the signal will get reduced. So you have some dense media and behind that dense media you have put your access point. So in that case the signal will get reduced. We should not place our access point in a way that it will get reduced. Then we have the scattering. If you have some sharp surface, so at that point of time, if the signal will land, it will get reflected. Obviously the distortion of the signal will be there. Then we have refraction. Refraction means that again your signal will get distracted. The actual physical meaning, or if you go and check the physics book, you'll find that when RF signal meet the boundary between media of two different density. So if one place you have higher density, other place you have some lower density. Say for example, air and water. So air has low density, water has higher density, and if the signal will travel on those media, obviously it will get refracted. Okay, so these are the evils we have here. You can see that you have reflection, you have absorption, you have a scattering, refraction, and then finally we have the diffraction as well. So suppose on a line of signal, if you have some opaque or if you have some void in between that, so in that case the signal will get distorted, it will get refracted, diffracted. So suppose an RF signal approaches an opaque object or one that is able to absorb the energy. So that's the case, you have the diffraction. Obviously, the signal will get degraded. One of the important concepts we have in this is the Fresnel zone. What is this Fresnel zone? Before going to that, you can see one of the example of diffraction, that you have the obstacle, you're sending the media, you're sending the frequency, the waves, and you have the media in between who is diffracting the signals. Obviously the signal is getting diffracted, that's the one thing. So what is the solution for that? That you can use line of sight wireless signal. So two big towers, in between that there is nothing. So there is nothing means there is no object or uh, abstraction in between that. So here you can see you don't have big tower in between that, in between two buildings. So your signal can transmit it from here, receive from here. That is one of the solution. But again, what Fresnel law is telling is, according to Fresnel, the rule is even narrow line of sight signal can be affected by diffraction even if an object does not directly block the signal. There is elliptical shaped volume around the line of sight that must also remain free of obstruction. So what is mean? And that's called the Fresnel rule. You can see here that I have transmitter and receiver in the diagram, but when you send the light, or when you send the signal, not light but our radio frequency signal, so when you send the radio waves, at that time what will happen, that it will create some sort of cylindrical volume across it, because still you have air in between, still you have the gravitational force, still you have some invisible, you can say, abstraction in between that. Maybe in some places we have um, so much pollution, so maybe the heavy particle they can um, collide, and there are so many factors for that. So in that case what will happen, they will form this cylindrical type of structure. In between that again you can see that you have a small building in between that, so it still is going to degrade the quality of signal. Okay, and then you can see that this curve is showing that you should not have any abstraction in this curve, and that's again coming from one of the formula. Okay, so these are the things related to the interference and related to the objects, physical objects in between. And again, if you go and check more and more about the reflection, refraction, absorption, and all these things, very much taken from the physics. We have learned a lot in our maybe 12th or in our graduation about all these theorems and theory related to various diffraction and the transmission of signals. All right, so let's stop here. Next basic topic we have is the antenna and type of antennas. So let's understand about antennas as well. Now here you can see that we have different type of antenna, and actually different type of requirement is there, and that's why we have different type of antenna. So sometimes we need focused beam, sometimes we need smooth and surrounded or equal spaced RF frequencies or beam. Sometimes we want long range radio frequencies. Sometimes we need short range radio frequencies that will be inside the room. So that's the main reason you can see here that we have different type of antennas, because the requirements are also different. According to that, we'll go and check that what type of antennas are available and what is the frequency range they are available with. Before that, let's try to understand a few of the basic things. So first of all, here you can see that we have the isotropic antenna, where we have, say, example, here in the diagram you can see that you have X, Y, and Z direction. So at this point of time, suppose if I have two sections, one section I have in X direction, that is the horizontal, and one section is in, say for example, Y direction, X and Y direction. Y direction is vertical. And suppose the requirement is that I need equi-space type of radio frequency. So what does it mean? That it simply means that you put the access point in the center, and then from that access point going forward in a circular manner, you have the radio frequencies. So whatever object that is coming in that circular radius in that particular premises, they will get the radio frequency equally. That's the whole idea behind that about the isotropic antennas. But the problem here is that to make isotropic antennas, and that isotropic antenna will fit with all the requirement, is actually not possible. So that's the reason we have a different types of antenna categories. Now here you can see in the diagram that you have horizontal direction, that is azimuthal, and then we have the elevation plane as well, that is the E plane. So we have two plane basically, H plane and E plane. And according to that, if you go and do the cross section, so if you go and do the section here in the diagram bottom, let me try to highlight. So here you can see that how the frequencies in terms of dB, that is increasing as we are going outside to the circle. So here you can see that the outermost circle usually represents the strongest signal strength, and the inner circle represents weaker signal strength, because they are in the minus. So minus 30 is less than minus 5. Minus 5 is obviously bigger than minus 10, and etc. Correct? So outer circles representing higher signal, and that's one of the important point that we should know. So now we understand about the isotropic antenna, and that's actually not possible to build. We have different type of antennas. Then we have the azimuthal and the E plane. Then we know this point that okay, while going forward, your signal strength will increase as per this section, as per E and H or E section. Then what is gain? Now gain is nothing but it's the focus. So suppose if you have antenna, and that antenna, what is the focus, what is the focal? So that's the gain. So again, what does it mean? It simply means, you can think like this. We know at this point of time that we have seen the antenna. So suppose if you have parabolic antenna, and then in center you have the central knob, or you have the center in between, means you are focused on something. So your frequency where you are putting the focus on, that's actually termed as a gain, and we'll see that different antenna, what gain, what capability they have. Okay, all right, so here you can see in the diagram that different type of antenna, either isotropic, omnidirectional, directional. You can see the gain, because the focus is changing, and that's why the gain of the antenna is changing. Again, the new term we have is the beam width. So what is the beam width? Many manufacturer list the beam width of antenna as a measure of antenna focus. Okay, so again, two term. Gain is a measure of how effectively it can focus RF energy in a certain direction. So that's the gain. You focus in certain direction, or your energy in certain direction. And then the beam width. Beam width is nothing but the focus. So your focus and energy in that particular focus. So your focus is your beam width, and energy RF signal in that particular focus is nothing but the gain. All right, so understanding these many terms, now what we can do, that now we can understand the types of antenna. We know that we have the polarization, so that electromagnetic wave is nothing but the polarization. Earlier we have discussed that we have the electromagnetic wave and the magnetic wave. So we have electromagnetic wave, magnetic wave, they are in the 90 direction. So in between, the angle between these waves is 90 degree. All right, so knowing these many facts, now what we can do, we can go and learn about the antenna. Again, if the electromagnetic wave is in the horizontal direction, that is horizontal polarization. If it is in the vertical direction, that will be the vertical polarization. Okay, and that is shown here in the diagram. So if vertically, if signal is going vertically, you can see the signal received. This is vertical direction, or it can be in horizontal direction. Great. So now let's focus on antenna. We have two types of antenna. I will see that subcategories inside these types. So we have omnidirectional and the directional. Now omnidirectional, as name suggests, that it will be equidistance, correct? So let me quickly show you one of the example for omnidirectional, that is the dipole antenna. Dipole antenna, again you can see in the diagram that from the center they are in the equal distance, and their gain is around, again we know what is the gain. So the gain is around +2 to 5 dB. Okay, again you can see the E and H. The horizontal is azimuthal and the E elevation plane, and the cross section here in the diagram. Now again in omnidirectional, so here you can see that omnidirectional, one example for that is a dipole, and again in omnidirection the other example is the monopole. Okay, one of the Cisco is a big vendor for the networking, and one of the AP inside Cisco, they have 6 tiny antennas, 6 tiny monopole antennas in their access point. Uh, by the end of this section, we have this summary of whatever we are going to discuss here. So in the summary section, we'll learn more about that. Now, what is happening in the, say for example, in monopole antenna? So let me quickly show you the summary I have. So here you can see the summary. In omnidirectional, we have dipole, monopole, and integrated. Dipole, we have discussed that the gain is 2.2 up to 3.5. Monopole, you can see that 2.2, 2.2. So we have two spectrum, 2.4 and 5 gigahertz. Obviously, in 5 gigahertz, you will find much more signal strength. 2.4, you have less signal strength, but there are vendor made access point, maybe Cisco or any other vendor who is making this access point. Those access point, they are supporting both the standard 2.4 and 5 gigahertz. Okay, all right. So then you have the monopole. After that, we have the directional antenna. Why we have the directional antenna? Because in certain direction we need much more gain. So here you can see that we have the Cisco patch antenna, and the gain for that Cisco patch antenna is 6 to 8 dB. Okay, this is supporting 2.4 gigahertz. The gain is 6 to 8. In 5 gigahertz, they have 7 to 10 dB support. And here you can see the diagram. In this diagram, clearly you can see that focus is in one direction. Correct. If you go and see the other direction, you can see they are equidistant. Mostly they are equidistant, say in case of omnidirectional. Again, if I go back, mostly they are equidistant. But if you go and check the directional antenna, you'll find that the focus is in one direction. So for this antenna, that is the patch antenna, you can see the gain. Next, we have the Yagi antenna. Again, the name of the inventor is the Yagi, so that's why this is the Yagi antenna. In Yagi, again, you can see this is very much focused on one direction, and the gain for these antennas are 10 to 14 for 2.4, and we can see the list as well. Cisco does not support or offer 5 gigahertz Yagi. Cisco is not supporting 5 gigahertz Yagi, so that's why it is not there for 5 gigahertz, but here you can see that's 10 to 14 for Yagi. And if I go and check the list, so you can see, so 5 gigahertz Cisco is not supporting, so it is not listed here. All right, then finally we have the parabolic dish antennas. Again, the gain will increase because the focus will increase in certain direction. So in this case, you can see the linear type of azimuthal and the elevation plane, the horizontal and the E plane, elevation plane. Now the focus, it's quite linear, but again you can see on other hand what gain we have. The gain is 20 to 30 dB, and that's a big. Now again in this summary slide, you can see the directional antenna, the parabolic for 2.4 gig, they have 20 to 30, and 5 gig also they have 20 to 30 gain in this range. Okay, so you can take this particular chart as a reference, and we have discussed about, first of all, the term used inside the antenna, like what is beam width, what is gain, what is polarization, what is azimuthal, what is e-plane, etc., etc. Then we have gone through and checked the types of antenna. In omnidirection, we have dipole, monopole, integrated. In directional, we have patch, Yagi, and parabolic antennas. So what type of wireless network we have? Let's understand different type of wireless network, and then we'll focus on wireless LAN. So here in the diagram, you can see starting from a small WPAN, and then wireless LAN, then WMAN, and then WWAN as well. You have the personal area network. Example is Bluetooth. The distance is from 20 to 30 feet or 7 to 10 meters. Then we have wireless LAN that we are going to study in this particular course. That range is 100 meter, and we know that we have band 2.5 and 5 gigahertz band. Apart from that, we have the metropolitan area network as well. WiMAX is one of the example for that. Obviously, it is for wider range. And then we have the wide area wireless network as well. That is again is for broader area. Example is the mobile services, mobile towers, etc. Okay, so let us focus on wireless local area network. Now we know that we have transmitter, we have a receiver, correct? A transmitter, they are going to send their electromagnetic wave. Receiver, they have to be in the line to receive those signals. If in between there is any interference, any obstacle, any problem, any type of object, then the signal will be degraded, the frequency will be degraded, and the overall performance will be degraded, correct? Now we may have one-way communication, we may have two-way communication, and suppose if we have more number of devices in a group, in a particular wireless area, LAN group, then there is so much interference and the problem. So just to mitigate from this particular problem that we have, we need one central device that can work on behalf of all the devices, correct? And that central device name is access point. Now here in the diagram, you can see that all the devices, all the wireless devices or endpoint, they are going to associate with access point. Now there are so many different terms, and we should understand at this point of time. So in the diagram, you can see that first of all, you have one circle, and that circle is nothing but the, so for example, this point of time, this is the uh, wireless area. Like in Ospf, you have area. At this point of time, just think that this is one of the area set. This is one of the area, for example, area 0. Inside area 0, you have different endpoints and you have the AP. So this AP, the BSSID is nothing but the MAC address of the access point. And obviously MAC addresses are unique for the physical devices. So the physical ID that this device has is the BSSID. Here you can see that you have the basic service set. So complete area 0, you can think that the standard inside complete area 0 is basic service set. So we have the basic service set, we have the access point, we have BSSID. Now what is happening and what is important here is, like routers, what routers are doing, they are advertising their network. Same way, what access point will do, he will advertise his network. And his network identification is nothing but SSID. So SSID, he is advertising. Whoever endpoint will associate that particular SSID, that will become part of that group, part of that set, correct? And that's actually the truth. So here you can see that you have the basic service set, BSS, Inside BSS, you have the BSS ID, that's the AP ID, and this AP is advertising its network, and all the endpoints, they are going and connecting with that particular network. Okay, and that network is nothing but the service set identifier. Again, the endpoints, that's the member, they will go and associate with that particular network. Obviously they will do some sort of negotiation in between that, and then they have to associate with that particular network. Now from AP, if you want to do some sort of access control, that we can do. So here in the diagram you can see that certain group of devices can communicate, or certain members can communicate to each other, certain members will not communicate with each other. Later on we'll discuss more about the packet type and communication, etc. Alright, so far we understand that what is AP, what is members, what is SSID, what is BSSID, what is BSS. Now very important thing here is that for each and every wireless network you should have the core, and that core is nothing but wired network. So behind every wireless network we have the backbone wired network, and that backbone wired network is termed as a distribution system, DS. So here you can see in the diagram that you have DS, and again behind that you have router, switches, firewall, etc, etc. So how the connection is, we have BSS that is connecting with DS, that may be any L2 or L3 switch. And suppose if we have multiple VLANs, so suppose one VLAN representing one of the SSID, other VLAN representing other SSID, or maybe you have multiple VLANs across your SSID, depends upon what design you have. Now in that case also the BSS and DS should have trunk link in between that. So we know this concept from our VLAN concept, that if you have multiple VLAN, so there should be trunk in between to allow those VLAN frames. Okay, so that's the concept of DS and the connection with BSS. Now the next concept we have is the extended service set. So what does it mean? Now if you see the diagram you'll understand. So for example, you have two BSS, BSS1, obviously BSS means BSS having BSS ID. So that means they have their unique MAC addresses. In very easy term, that you have two different access point, and these access point having same network. So their network is nothing but SSID, SSID. So SSID is same, and they are connected with the DS, distribution system, or a switch. So now the BSS, so collection of BSS, you can think as an extended service set. So BSS or N into BSS is equal to ESS, extended services. Now if I have one user here who is associating with one of the AP, and then he is going to the other AP, and he is associating with other AP, so at that time the concept is termed as a roaming. So user is roaming uh, across the network, but we can say that throughout you, it may have different AP, correct? You can see that it has different AP, but they are part of same network. So that concept is nothing but the roaming. All right, so let's stop here. We have covered the basics of the wireless LAN so far. Next, we have 802.11 frame format. Although we know that how 802.3, that is the IEEE MAC based format, how it is working and how it look like. So here you can see that you have preamble, the source destination address, and then you have the data field plus FCS. Switch used to learn all these end host machines, and then depending that do we have L3 communication or L2 communication. For L3 communication, again if you are crossing the boundary, then the router will come into the picture, but that's the way that the LAN and the broadcast network used to work. In wireless networking, the communication is very different. Why? Because we know that all these end system, first of all they have to learn the SSID. SSID is nothing but the advertised network from the access point. So they have to learn and associate and authenticate this SSID. After that, they will start the communication. Because we have SSID into the picture, because we have different type of wireless client or different type of end systems, they are part of wireless network, and they can communicate to each other as well, or they can communicate to the machine that is behind the wireless. So wireless will connect with wire, and then wire is connected with some other host machine. So the bottom line is that you may have various mode of communication, and depending upon what type of communication you are doing, that's why we have different type of addresses. So here you can see that you have 4 different address 1 2 3 4. Then you have the duration ID. Why it is? Because this technology based upon congestion avoidance. See, the Ethernet LAN is something like collision detection, and this is actually a collision avoidance, not congestion, collision avoidance. Now, in case of collision avoidance, what is happening? That you wait, you have some timer, you have some back off algorithm, and you will see. So if it is clear to send, I will send. If the media path is not clear, I will wait till that particular point of time. So that's why it's the collision avoidance mechanism. Now here you can see that you may have end system. Uh, those are the wireless client where you are doing the communication, or you are doing the communication with the machine that is behind the behind this AP, that is in the wired. So wired versus wireless, and that's why we have this DS bit set. So either 0 or 1. So if you have 2 bit, then you can have 4 condition. Say a 0 1, a 0 0, 0 1, 1 0, and 1 1. Now this 0 0 means that 2 hosts are doing the communication. They are purely part of wireless network. Now this 1 0, you can see that you are doing the communication from wireless to wired network. Then you have this 0 1, that means the bits are coming, the frame is coming from host, from the wired network to the wireless. And finally, if you have access point A and access point B, and if they have some communication, that will be 1 1. Okay, so let's try to understand what about these so many addresses types. Yes, we have 4 different type of address type. Here you can see that first of all, they must have TA, transmitter address and receiver address. Now this address one field always contains RA, that is receive address, though its exact contents may vary depending on where the frame is headed. Likewise, address 2 is always contains TA. So 2 addresses fixed, address 1 is receive, address 2 is transmit. Correct. Apart from that, obviously when you are sending the frame, then you should have the actual source address, you should have the actual destination address, etc. So let me try to explain this in a diagram. Here in the diagram you can see, and we are going to understand all the address types, address 1 2 3 and 4. Remember, in this diagram I don't have AP to AP communication, so that's why address 4 is blank. Okay. Now we have one case that host 1 wants to communicate to host 2. So what will be the source and what will be the destination? So here you can see the source address is uh, the transmission address is this, and the destination address is this. So actual source, actual destination. Now who is the receiver? At this point of time, the access point is the receiver, so that's why his MAC address. Okay, so clearly you can see first of all the addresses, and second the bits. So since you are sending 1 to 0 means wireless to wired, so that's why you can see here that this is going to hit. Okay, and here you can see the address 1 is BSSID, address 2 is the TA, and then the address 3 is the destination. Okay, now then the host 2 will respond. When host 2 will respond, then source and destination address will get changed. So now who is the source? He is the source. Who is the destination? This guy is destination with respect to host 2. Now what about the MAC address of the BSSID or the AP? That will be the transmit address. So he has received the address and then he is transmitting. You can think the logic like this. That is the transmit address, rest the receive address and the source address, they are going to be changed. Now which is the use case? This one. So here you can see address 1 is RA, who is going to receive. Address 2 is BSSID, who is going to transmit, and the address 3 is the source address, correct? And who is the source? So this guy is the source. Although this is a bit of tricky, so you can pause the recording, you can take snapshot, and you can do your mapping. But this is the way that the frame format look like, and the fields inside the frame format representing these addresses and these DS bits. Let us understand the 802.11 frame types. As we know that we have three different type of plane, normally in SD-WAN also or in routers also. So we have the control plane. We have, as you can think that for frames also we have management frame, control frame, and data frame. Now, what is the use of management frame and why it is important? So let's try to understand all these options that we have. First of all, starting with management frame. Now, this management frame is there to advertise the BSS and its capability to the clients. Now, what are those? So first of all, you can see that you have beacon, and beacon is something that will be sent via the AP. At this point of time, you can think that okay, beacon AP is sending the beacon to all of the clients, and if client will go and open and check their wireless network, they can receive those beacons. Now it's up to client that they want to join or not, correct? So if I go to my laptop and if I go and check my wireless connectivity, I can see a range of SSID or BSSID. Generally those are SSID, not BSSID, but I can see all those SSID. SSIDs are nothing but the network advertised by the AP or the wireless network. So that's nothing but the beacon. That's the one of the management frame. Then probe. What is probe? Probe is something, suppose you want to join to the AP and then you are sending the request to the AP that hey, AP, I want to join. That will be the probe, and that's why this is the passive. So beacon is a passive scanning and probe is active scanning. Okay, next we have the authentication and deauthentication. Now in wireless networking, we have this authentication option that the clients can authenticate with the AP, and even they can do the deauthentication as well. So the first stage you can see on your laptop that you can see n number of SSID or so many SSID. Now next thing, if you go and click there, it will ask you some password. What is the password? If you put that correct password, it will get authenticated. If you do not put, it will not get authenticated, correct? So those frames are actually the management frame. Then we have important terms: association, deassociation, reassociation. So suppose once you are able to discover the network, then you are able to do the authentication, then you are going to do the association with the AP. Now in this association phase, the access point, they are sending a unique association identifier, AID, to the clients who are going to do the association. Suppose if you want to leave, you can do the deassociation. If you want to change one AP to other AP, you can do the reassociation. So different terms are there related to association. Now we have the action frame as well. Suppose you want to roam or you want to extend the wireless capabilities. So at that time, this action frame will come into the picture. So here you can see that you have this management frame. Then we have the control frames, although there are 9 control frames, but these 4 are important. So control frame are, again, it's not the payload, it's not the data, it's the control mechanism. Uh, so for every frame, we are getting the acknowledgements, and that will provide you, so for example, reliability in the channel. We are getting the acknowledgement for block of data as well. Okay. Then we have this power power save poll. So what does it mean? That a frame sent from client to AP to request the next frame that was buffered while client's radio was power on is something like a power saving mode. Then finally, and the important one, we have the RTS and CTS. RTS and CTS is something like a timer. So it's something like request to send or clear to send. These are the terms. And why these terms are become important? Because request to send and clear to send, RTS, CTS, they are not only providing the timer to send the frames, but they are used for collision avoidance as well. Okay, so the RTS, CTS are a mechanism to do some sort of collision avoidance in the channel as well. So finally, once you have your management done, once your control done, the next thing is to send or receive the data. For that reason, the data frame will come into the picture. At this point of time, we know from our previous lessons that we have 4 different type of address field. So the source address, the destination address, the AP address, and then you have the destination behind the wireless, that is in the wired network. So you have these 4 addresses, and then the actual communication of data can be happen. Let's understand the client scans for AP and roaming feature. We have already discussed about beacon and probe. We know what does it mean by passive scan. So passive scan means the access point. Here you can see that they are sending their beacon to the host with some time duration that they are offering their network to the host. Now it's up to host that he can go select that network and then do the authentication and association. That's the passive scan. Now this passive scan is good, but still the drawback there is that the host, they have to wait for certain time duration to get the network or to get the advertised network from the access point. Next, we have the active scan. In that, the client itself is sending the probe. And he's asking that, say, who has this network? And then the access point, they are responding, okay, I am there. You want to authenticate, you want to associate. If you associate, you will get the unique association ID, AID. Now, how the host will go and join a particular AP. So here you can see that we have several steps. Step number 1 to 5. That's first of all, the host will do the authentication request. Then he will get the response. Then he will do the association request. He will get the association response and unique AID, association identifier. And then finally, he will go and join that. Okay, and all these steps are listed here. So for example, point number 5 is the response also contains the AID that uniquely identify host 1 as an associated client in effect to AID is host membership, etc. So these are the steps: authentication, obviously request response, association, request response, and then finally they will get the unique AID. Now, if a host or client want to leave it, so he can do the deassociation. Remember here that deauthentication and deassociation are different things. So if you are deassociating, doesn't means that you're deauthenticating or you have to authenticate again next time. You can be deassociated, but you're still authenticated. Correct? Now, next very important topic is roaming. So far, we have studied that suppose if you are moving from one BSS or one area cell to other area cell, that means you are roaming. And suppose different AP having same SSID, so you can roam from one place to other place as per the signal capability. You will go and get the you will go and associate the access point. That's the technical term, association. Now here you can see all the listed steps, what is happening in the roaming. First of all, say your signal strength is getting weak, your signal to noise ratio is getting weak, it's time to roam. If you're not getting proper signal, here you can see the client is there on the edge and he's away from the AP, but he's near to the other AP, or if you roam, he can get near to the AP and you want to go and associate with a new high bandwidth, or he want to get some high frequency signals. So that's why he want to roam and go to the other SSID. Now in this case, what is happening, that the client will send the probe. Now he will get the probe response. Then here you can see that the association request will initiate. Okay, association request will get initiate, and I want to highlight this point number 5 here, and it's important here. Now in this case, when two device, in this case when client is doing the uh, roaming across the AP or across the wireless network. So at that time, point number 5 is important. So whatever buffer, whatever information that AP1 has, he will go and pass the information to AP2, and then he will use the DS, distribution system. He will go and use the wired media to bypass or to relay the buffer information, and then finally this client number 1 will get associated with AP2. Okay, so you can see all these steps. If you have single access point, we know what are the steps. You will do the authentication, means you will do authentication request response, association request response, and you will be the part of the network or SSID. In case of roaming, when you are getting some issues, you roamed, then you do the probing, and then again you will do the association. Then this APs, they will sync their buffer data, and finally you will be the part of the new access point network, correct? All right. Let's try to understand this wireless architecture. Inside wireless architecture, you'll find that we have several type of architecture, and what is suitable for enterprise level we can discuss. We have some popular one like cloud-based architecture or the split MAC. So let's understand all different type of architecture. So first of all, here you can see in the diagram that we have autonomous architecture. Autonomous architecture means that you have access point that is working independently. Okay, so here in the diagram you can see that you have access point connected with the distribution system or connected with the switch. The problem with this design is that although you can manage the SSID, but suppose for all these access point you have to manage their own management IP. So there is no central authority from where you can manage the common work, or you can manage the common security framework, you can manage the management IPs, etc. So if the network will grow in this case, in this fashion, you'll find that it's difficult to manage, and it's not a good design for a big enterprise network, or even when your AP's number of AP will grow more than, say, for example, 30 to 75 or 100 or 200, etc. It is okay, although for very small type of infrastructure where you have less number of endpoints, where you don't want any third party or any controller type of device that can manage all these access point. So for that reason, it's okay. So this is the first, that is the autonomous architecture. And then next, to reduce the complexity, we have cloud-based architecture. One of the popular cloud-based architecture we have is Cisco Meraki, where you have the cloud-hosted controller, and then you have your Meraki-based access point situated in the branches in the LAN area network, etc. So here you can see that you are responsible, means the APs are responsible for the data plane traffic, but they are getting all the control information from the dashboard that is hosted in the cloud, or we have the cloud hosted control plane. Although the good thing about this that manageability is easy, we can easily manage our infrastructure even from one single place. We can go and log in and check various reports, various configuration, etc. from one central place. That's the key we have with the cloud hosted control plane. Again, when we are talking about cloud based controller, we have the control plane hosted in the cloud, and with the control plane we can do various operation, like we can configure, manage, monitor, create the reports. Even we have some visual representation. We can do the troubleshooting as well. So we have long lists that we can do from the control plane. And again, the data plane is there that is responsible to pass the data. Okay, so now you can see that we have autonomous architecture that evolved to cloud-based architecture, and finally that is our interest for this particular course, is the split MAC architecture, where we have the wireless LAN controller, WLC. Okay, so now here in the diagram you can see that you have two access point. One is the autonomous, that evolved from autonomous architecture, and then we have lightweight access point where they have given their brain to the central location, that is the WLC. So from WLC, what are the things we can do? We can go and we can do the RF management. We have the association and roaming management, client authentication, security management, QoS, etc. There are so many things that you can go and check from the WLC, and you can manage n number of access point or the data plane devices. Again, it depends that which version of WLC controller or LAN controller we are using. According to that capability, we can manage the number of lightweight access point. Now, what data plane device is doing? That they are doing the RF transmit, receive, MAC management, encryption, etc. So now I have one comparison chart. Here you can see that autonomous WLAN and lightweight. Autonomous, just name suggests that they are autonomous access point, configuration of each access point, independent operation, managed via Cisco Works, LSE, WDS, access point redundancy. These are the independent things. Then managed from the WLC. So they are the lightweight access point configured via Cisco LAN controllers, dependent on Cisco LAN controller, management via Cisco WLC, Cisco wireless LAN controller redundancy. So in this case, in this architecture, we may have primary, secondary, tertiary WLC as per the failure scenario. All right. So here you can see that in this case, the APs, we are telling them as a lightweight access point, and they have to go and register with the central authority, that is the WLC. Now, still the question arises that how the lightweight access point will go and registered with WLC. What about the traffic? How the traffic will move uh, from one client to other client in case both are registered with WLC. So all those things and the protocol between the LAP and the WLC, we will go and discuss in the next recording. We have discussed that the access point and the controller, they have to communicate. So how they are going to communicate is, so they are going to build the CAP-WAP tunnel. Now you can see the full form of CAP-WAP is control and provisioning of wireless access points. And there are so many RFCs that you can go and refer. So here you can see that CAP-WAP is defined in these RFC 5415, 16, 17, and 18, where you can go and learn more about this CAP-WAP tunnel. So let's read this as a CAP-WAP as a short, but you can see the full form as well. Now, when the lightweight access point and the WLC, they are forming the tunnel in between, At that time, we have two different type of tunnel. We have tunnel for control messages or control plane, and then we have the tunnel for data plane as well. Now, if you correlate this with the SD-WAN, and we are thinking now that now we are using SDN and SD-WAN and SD-LAN solution, but this WLC is quite a bit old technology which is using the concept of SDN. Even for example, Cisco Prime, then WLC and other mechanism also was there to manage the infrastructure. In terms of that, we have some central authority who is managing the infrastructure like SDN or SD-WAN, etc. If we go and learn more about the CAPBAP information, we'll find that, yeah, truly the tunnel that is building between the WLC and rest of the APs, they have exactly same type of certification process that we have, say, in case of VSmart, that's the control plane, and vEdge, that is the data plane device. So here you can see that CAPBAP, they are using UDP port number 5246. They are using secure authenticated DTLS tunnel, because we know, say in case of SD-WAN, we have both the option. Either we can use TCP or we can use UDP. Most of the other SD-WAN technology, they are using UDP based IPsec tunnels or UDP based tunnels. In our WLC, we are using UDP based control tunnel and data tunnel. Now for data tunnel, the DTLS is optional, means the secure tunnel is optional, means this, at least the encryption is optional. If we want, we can use. If we want, we do not use. So here you can see that, but are not encrypted by default. So tunnel in between them. So tunnel is there, but the encryption is optional. If you want, you can use it. Now here you can see that we have two tunnel. We have the data tunnel, we have the control tunnel, and in this manner, the access points, they will go and communicate the WLC. That's the one part. Now what will happen in this case? In this case, uh, behind the scene, what is happening? So these tunnels that you are seeing in between the WLC and the access point, they are using IP address. So that means they are IP based tunnels. Since they are IP based tunnels, so what they can do, and there are two things. First thing, that the VLAN. So whatever VLAN I have in the distribution system, obviously this WLC is connected with switch. So those VLANs information will get passed under the tunnel to the AP's access point, and these SSID information again will go and pass to the distribution system to the switches. Okay, so in that way the communication will happen. So you don't need trunk link here. So that's why you can see that I have the access link. So I don't need trunk link, and then I have to do encapsulation dot 1q, etc., etc. But that's the enhancement, because you're creating the tunnel. So obviously it will send and receive the packet depending upon the tunnel source and destination. In this case, the tunnel source and destination is the IP addresses of AP and the WLC. So suppose if you have more number of tunnels, in other words, you can think that if you have more number of access point, then you have more number of CAPBAP tunnels, and then the communication will happen like this. So this is the communication channel that we have. Okay. So now once you have the WLC, so what are the role, what are the activity that WLC can do? So WLC can go and do the dynamic channel assignment, transmit power optimization, self-healing wireless coverage, flexible client roaming, dynamic client load balancing, RF monitoring, security parameters, QoS parameters, etc., etc. So whatnot means we can do n number of things from WLC, because that is the brain I have, that is the central mechanism to manage all the lightweight access points. Correct. Even you can see that we can do the wireless intrusion protection system as well. So this is the usability and use case of the CAPBAP tunnel that we have, and this is the mechanism by which the WLC is talking to the access points. Let us continue our discussion and learn about the centralized wireless network architecture and Flex Connect architecture. Now we know at this point of time that the WLC and the AP, they are going to have the cap wrap tunnel in between them, and then the communication will happen. Now before moving further, you can go and check the comparative chart from different type of WLCs that we have in Cisco. Uh, so for example, I have taken snapshot from one of the link from Cisco. Here we can clearly see that we have different type of WLC for different type of purpose. Although we have virtual controller as well, we have controller for ISR G2 starting from 250036505500 going to 8500 and 9. Now we have the 9800 WLCs as well. If we have more number of users, if we want to manage more number of lightweight access point, then obviously we have to move and we have to go to the higher end of WLCs. So it's just the evolution of WLC, how much clients we have, how much APs we have, what security feature, Flex Connect, QoS, etc. Depending upon that, we can go and choose one of the WLC for our organization. Now, once we are done with that, then we can go and deploy the WLC and we can connect the APs with WLC. That's the overall idea, and then the traffic will start flowing. Now, we have this centralized solution that all these devices will go and connect or create the tunnel with WLC. Very much at this point of time, we can think that this is hub and a spoke type of topology, where you have your hub as WLC, and then you have the spokes. So spokes, they are making the tunnel with the hub. Now there is one problem with this particular architecture. We'll discuss about that problem and the solution as well. Before coming to the problem, you can see that since you have your central authority to manage each and everything related to access points, so that's why the user identity means, again, the WLC is connected with the ICE and they are talking with each other related to users and profile and roaming profiles as well. Now, user identity or a user services or a user. So what are the user and its roaming capability? That can be managed from one place because everything is managed from one place. So that's the power we have. We have the centralized authority to manage each and everything. Next, in this diagram, you can see although the physical architecture, although the movement of data in the physical path is different. So here you can see that the actual movement of the data will be from switch 1 to 2 and 3. In short, that in between you may have a number of switches. On top of that, you have created the cap web tunnel. So again, you can see that from access point to the distribution system or the core layer switch, I have the cap web tunnel and then the traffic can go, but the physical movement or the data traffic movement via the link will be different. So that's one interesting thing we have, although we are not concerned about what are the configuration, what are the trunk VLAN passing to the intermediate devices, correct? Because those are, we can think that's as transient devices. On top of that, I have my tunnel. So you can see that you have the benefit. Now what is the disadvantage? What disadvantage we have? Now if you see this diagram, you'll find that although I am local to this access point highlighted, so let me quickly highlight that. So I am local to this particular access point and I should not go to my hub and then I should come back, or I should not go to my central location and come back, although I can do this local movement of the traffic or movement of a traffic locally, right? So that's the problem we have, that if you do not give the local intelligence, so all the time the traffic will go, they will go and traverse this cap web tunnel, they will go to the central authority and then they will return back. Now, what's the solution? The solution is the Flex Connect wireless architecture. Now, what will happen in Flex Connect that we can understand from the diagram as well. So we have two type of architecture. First is the split MAC. Split MAC means you have your central authority WLC. You can go to WLC and come back. Again, you can see that you have cap web tunnel, and um, again the same thing you can see in the other diagram as well. So you can go to the WLC, and then suppose if you have local printer to the switch system, you are going there. Although if you go and use the Flex Connect feature, what it will do, that it will give the device as a local intelligence. So what does it mean? It simply mean that for local transmission, you will not go and use the cap web tunnel, although you can go and directly use a printer, because to reach to this path, it's easy. Okay, so here you can see in the diagram that the traffic path during Flex Connect local switching, you are doing things locally. That's the power we have with the Flex Connect. We have a small tip here that Flex Connect was previously known as Hybrid Remote Edge Access Point HRIP feature. To maintain connectivity between WLC and branch side LAP, the WAN link should have a round trip latency less than 300 milliseconds for a normal data and less than 100 for the real-time traffic. Okay, so the concept, the idea behind is that when we are doing the Flex Connect architecture, so at that time we can do the local switching. Next, we have to learn about how we can do the implement the controller. Before that, we should understand that what type of interfaces and port available inside the WLC, and what will be the connectivity from the WLC to the switches. We have four different type of port. We have service port, distribution system port, console port, redundancy port. Now the service port will be used for out of band management, system recovery, initial boot. This will always connect as the access port. So we are going to use this as a UB, out of band management. Then we have the most important port, that is the distribution system port. We know this thing that distribution system port means that the WLC you are connecting with the switch. Now we have the capability, or we have the feature that we can do the aggregation. We can use link aggregation protocol, and we can group those interfaces and connect with the switch. Now these ports are always 802.1q, because again we are going to pass multiple VLANs information via the WLC. Then we have the console port, where we can connect the console port for recovery, initial boot, etc. And finally, in case we need multiple WLC for redundancy, for that we have the redundancy port. Now here in the diagram, you can see that we have the distribution system. Obviously, the WLC is connected with the switch, and that's why you have the distribution port. We can have the link aggregation group. Service port is for outer band management. You have the console port, and if you want to have multiple WLC, so we can use the redundant port as well. Then from WLC to AP, we have the cap web tunnel, and then the information will go and get exchanged. Now these are the port, or these are one type of port we have. Again, we'll discuss more about other port analogy as well. At this point of time, we know that the AP and the WLC, they will go and form the cap web tunnel, and the distribution port, they have the we should enable the 802.1q, and we should do the link aggregation protocol, or link aggregation as well, in between the WLC and the distribution switch. All right, so as for the model, you can see that which model have the distribution port and service port listed here in the table. Again, if we want if we have more number of APs, then we should go and check the higher end of the controller, and the capability increase, the throughput will increase, the overall performance will increase, but again the cost will also get increased. Now what is happening? So these are the ports we have. We have service port, distribution system, console, and the redundancy port. But internally, the controller must somehow map these ports to the equivalent logical port. So inside the controller, we have the equivalent logical port. So for example, we have the management interface. Now, what is use of management interface? Obviously for the management related traffic like radius, authentication, WLC to WLC communication, web-based SSH session, SNMP, NTP, syslog, etc. Okay. Now in this diagram, you'll find the clear picture about what we are talking. So here you can see that first we have the management interface, then we have the AP manager interface as well. We have the service port. We have discussed just now that service port will do OOB and various tasks related to service port. We have the dynamic interfaces as well. So what is happening here that these VLANs that is coming from the switch side, they are going to map with the AP. And then again, this AP somehow has to associate with the access points as well. This AP is the WLC. So let me again read you this. Switch will go and connect with the WLC, and WLC has a connectivity with the AP. In between WLC and AP, we have the cap app tunnel. All right, so what is the use of AP manager interface? They are the dynamic interface used to terminate the cap wap tunnel between the controller and AP. So here you're seeing this AP manager, actually the use of this to terminate the cap wap tunnel in between the AP and WLC. Then we have the virtual interfaces. Again, virtual interfaces are they have just the use case. So what use case these virtual interfaces have is that IP address facing wireless client. When the controller is relaying client DHCP requests, performing client web authentication and supporting client mobility. It is used in client mobility. It is used in a way that the WLC can relay the DHCP information to the IP address facing wireless client. Okay. And again, this interface will be less of use, but we have the interface. Then we have service port interface. We have a study about this, that this is used for the out of band management. Then finally, you can see that you have the dynamic interfaces as well. These dynamic interfaces are, they have to connect VLAN to WLAN. That's the usability. Correct. So we have discussed about management interface. They are there for management traffic, different type of management traffic like HTTPS, SSH, SNMP, NTP, etc. And then you can see that management interface is actually important. So that's the one of the use. And then suppose the other use of this management interface is in case of AP manager interface is not available. So that performance or that task will be performed by the manager interface instead of. Okay, so that's the other use we have with the management interface. All right, so these are the interfaces. Here you can see that these are the ports, and here you can see that these are the interfaces we have in the WLC. So now let's stop here and let's go and do the initial setup. Next we have to perform the lab, and in this we are going to do the initial setup for WLC. I am using the virtual WLC here, and once you are in the first page, then you can give the username and the password, and then you click start. Once you go and click start, the next page that you will get, this will be like this. So let's do and complete this. I'll go and give the name, say for example virtual WLC 1, and the country I can go and select anyone. So let me go and select, say for example, any of the nearby countries, say for example, just an example and testing. So I can go and say select London. Then the time, I can see the time zone, and then I can go and give the NTP server. Then we can go and give the management IP. So that's the management IP in my case. Then the subnet mask for the management IP. Then the default gateway I have in my case. So that is say 19.1.1 or 11.1. Yep. Then the management VLAN ID. At this point of time, we can leave this as default. All right. So now we can go and click next. So I will go here and click next. Next, you can see that we have to create the wireless network, and then we have some of the advanced setting. Let me give the correct default gateway and click next. So what is the network name I have? So I can go and give cloud demo. Then what key? I'll leave this as default, but we have WPA personal and enterprise. Then the passphrase, I'll go and give the passphrase. Let me confirm that. Then what is the management VLAN? We'll leave this as management VLAN. If I have any DHCP server, I can go and give, and then we are very much done with this step. So now you can see that how easy is to do the setup. Now I will go next and we'll verify the advanced setting as well. So we'll go next. Here you can see the virtual IP address, the local mobility group, the service port interface, and these things we have discussed. Now the virtual IP address, it should be say some of the private address, because those private address will be used uh, locally. Suppose if I use any of the address which is not private, and that may be conflict, there may be chances to for the confliction. All right, so here you can see that we are giving the virtual IP address, and then the service port, we are leaving this as default. Now let me scroll up if we have some other parameters. So here you can see, you can go and this is disable RF parameter optimization. You can go and enable it, and then you can see that client density low, typical high, traffic type is data. I can go and use at this point of time the traffic type is data only. All right, so here you can see that please confirm the setting and apply. So this is the setting that we have given: the management IP, the management gateway, the network name, security, passphrase, etc. So once we are okay with this particular summary, we can go and click next, and then we can go and apply as well. So this is the final page. Yes, okay, I want to apply this, and then we can wait. So once the setting apply, then we can go and log in with the management IP. So I logged in here with the management IP, and then you will get this first page. So now you can go and log in here. You can see the management IP 11.10, and then I can go and give the username and the password. So let me go and give username and password. Then we'll get the first page. So this is the first page that we have, and here you will see the monitoring rogues interface, wireless dashboard, etc., etc. Interestingly, in this first page, you'll find that we have the best practices as well. So suppose if you want to check the best practices, you can go and verify that. In this page, in this first page, because we don't have any API association, we don't have any live traffic, so everything is showing blank. But if you go and click to advanced, you will get this page that we are very much familiar of. Generally, we are using this advanced tab to check each and everything related to the WLC. So in advanced page, you can see that you have the management IP, then you have the service port 00 software version, you can see 8.7, the name, the uptime, rest of the thing. Then the access point summary, you can see nothing is there, so that's why everything, all the counters are 0. But on the top, you can see that you have monitor WLAN. So suppose if you want to create WLANs, you have to go to this section, and then you have to create the wireless WLAN. Again, once you go and create there, then you will get multiple options related to the WLAN. We can go and check this later on. Then the information about the WLC. So here you can see the long list of information that we have, and you can go and click and check each and individual tabs that you have. You have management interface, you have service port, you have virtual port. We have discussed about this, correct? And then we can go to the wireless. At the moment, everything is blank. We can go and check the security. Again, you can see the long list of security we have. Management, then if you want to run any command, we have some of the command support that we have. So the page will look like this. Okay, so this is the initial setup for the WLC, and we should go and check the best practices that we have. So if we go and check the best practices, then we can see that what are the Cisco recommendations. So let me quickly show you that. You can go and click on top home here. Once you go and click to the home, you'll go back to the first page that we have opened, and then here you can see the best practices. So best practices related to infrastructure, security, RF management, Apple devices, ICE radius. Okay, and you can go and you can scroll and you can check all these best practices that we have. Okay, so this was the initial baseline setting that we have with the WLC. Let us understand that the discovery of the controllers. We have the document, and we'll understand with that document that what are the steps that AP is going to discover the controller, and then how the AP will go and select a certain WLC, that's the controller. So what is happening that we are going to boot the AP. So the first step is that you will go and boot the AP. So AP boot will happen, and obviously it will go and contact the DHCP server to get the IP. And suppose there are options that we can have the static IP assignment as well, but we have the option for DHCP server as well. Once it get the IP, then it will try to discover the WLC. Now for WLC discovery, again, we will see this. I have separate slides for that in detail, that how WLC discovery happens. But the next step is that the AP will try to build the CAPBAP tunnel with the WLC, and inside that CAPBAP tunnel, obviously we have CAPBAP control tunnel where we have the AP WLC control messages. Now the next step is that the AP will go and send the CAPBAP join request. Now for that request, obviously the WLC will reply for CAPBAP as a CAPBAP join response. So once we have the CAPBAP tunnel built between AP and controller, AP know who is the controller, controller know who is the AP, then it's the role of WLC that you will go and check the image version. So there should not be mismatch in the WLC image and the AP image. So in that case, the AP will go and download the image, and then again it has to reboot. Suppose if the image is okay, then from WLC, the config will get pushed related to RF, service set identifiers, security, QoS, etc. And finally, the device will go into the run state. Now here you can see all the steps that are listed from 1 to 7. Now in some occasions, due to some issue, that WLC wants to reset the AP. So in that case, again, the AP will go and reset, and step number 1 will start. Okay, one point to note here, that while the APs, they are downloading the image. It may take some time to download and upgrade the image, because downloading the image and then booting will take some time. All right, so what's the process for discovering the WLC? There are processes that AP may have knowledge of WLC, or with help of DHCP and DNS, they are getting that information, or the WLC is in some other network, and then I have router in between who's relaying the information with help of broadcast. That's the broadcast on the local subnet. So for example, a broadcast on local subnet, what will happen? So suppose if your AP and WLC, they are in different subnet, then you have to go to the router in between, and you have to relay that information like IP forward protocol UDP 5246. This is the UDP port for CAP-WAP control tunnel. Then you have the interface VLAN, and you can go and give the IP helper address for different type of WLCs. Okay, so that's the one option, or one way. The other thing, that inside your AP you may have the information of the WLC, and as per the primary, secondary, tertiary, the AP will go and check WLC1, then WLC2, then WLC3, and then they will go and contact or discover the WLC. We have option with DHCP. So once they are getting the IP address, at that time DHCP option 43 will be there to suggest the list of WLC addresses. It can use DNS as well to resolve CAP-WAP controller.local domain with the DNS request. Again, if nothing will happen, again the AP will go reset and it will start the discovery process. At this point of time, when we have the discovering of a WLC that is working well, so at that time we have selecting a WLC option also. So what does it mean? It means that AP will go and try for primary, secondary, tertiary, means as per the priority of WLC, they will go and join. The second thing is that suppose if they don't have any primary, if they are not able to discover any primary, secondary, tertiary, then they will go and check in the local subnet. So who is the master controller? According to that, they will go and choose one of the controller. And finally, they can go and check the least loaded controller as well. So as per the controllers and their connectivity, means the controller, how many APs are associated, they can go and select one of the WLC. All right, so these are the methods for discovering and joining process for AP and WLC. We have layer 2 and layer 3 roaming. So let's understand that. We have already discussed this earlier, that when we are doing the roaming, say in case of autonomous AP, the client here, you can see in the diagram, can go and connect with client 2 as per their signal strength. When the signal strength will go decreasing, then he can go and join the other available high strength SSID or the AP. That's the normal way that the roaming is happening. And the other important thing here is that in between that distribution system, that's the switch, he has the state information of this particular client, and then he can go and join. Now this is very normal, easy, standard process that the roaming will happen. Now the problem here is that we are not using this type of architecture in the enterprise network, because enterprise network, we have n number of clients, we have n number of AP, we have good amount of WLCs, other controllers. So the methodology that we are using in the enterprise network is purely split MAC architecture. In case of split MAC architecture, what will happen? So let's try to understand that. We know that in split MAC architecture, the APs, they are going to form the CAP-WAP tunnel with the WLC, and in that case, if a client want to roam, there are two options. First, that roaming can be layer 2, the roaming can be layer 3. So what will be the difference between that? And there may be chances that I don't have only one WLC. We may have multiple WLCs connected with wired network. So let's try to understand layer 2 roaming. What is the key feature about layer 2 roaming is that in that case, we are in the same subnet. We have the same big IP subnet. Inside that, I want to roam. So here you can see in the diagram that I have a user in 100.0 subnet, and he wants to roam from one AP to other AP. Obviously, you can see that these APs, they have cap web tunnel with their WLC. Suppose I have two WLC, and their connected network is wired switch network. Okay, so this is the use case. Now what will happen that when you roam, obviously from one place you have to deassociate, other place you have to associate. So you will go and associate. Now this roaming is quite good, scalable. Why? Because most of the things we are not changing here. So we are not changing, uh, and again it depends upon the use case. So if this is up to us that if we don't want to change the IP address of this client, so in the new when he is going to join the new AP, at that time also the same IP, and even the state information will be sync across WLC1 and WLC2. So in that case, we will get the seamless roaming type of capability, or the experience will be good because usually it will be less than 20 millisecond of the roam. Now the second option we have is the layer 3 roaming. Layer 3 roaming simply means that you are in two different domains. So suppose your exact IP is 100.0 and then you want to roam to 200.0. So you're crossing the subnet and then you want to roam. Again, the structure will be looking like the same, but the cap web tunnel you can see for AP1 and WLC1 and AP2 and WLC2, both are in different IP subnet. So what will happen now if this client want to move and he want to deassociate and associate with other AP, he can do it. But still, because the IP segment will change, here you have 100.0, here you have 200.0. So these WLCs, they are behind the scene forming the cap web tunnel over the switching system. So here you can see in the diagram that 100 is going to change into 200, and then finally they have the cap web tunnel in between that just to exchange the state information of a client associated with AP1 with AP2. Correct, and you will find that naming of these WLCs are also different. So the initial client, when client is attached with one of the AP and he wants to roam, at that point of time that WLC is anchor, and where he is going and he's going to join the new AP associated with WLC, that will be the foreign controller. So from anchor, I am going to connect with the foreign controller, and then the roaming is happening as a L3 roaming. So here you can see with the help of diagram, it's easy to understand that how I'm connected with one AP and then I'm roaming, but again the state change is happening with the help of cap web tunnel in case of L3 roaming. What are the steps we should do while doing the troubleshooting for WLAN? From where should we go and start the troubleshooting? Because we know that in troubleshooting we have either top to bottom or bottom to top approach. So both the things we can do. Now when we are talking about, so for example, top to bottom, so obviously you are at the level of WLC, that's the top, and then you can go and check the cap web tunnel. You can go and check the access point, maybe access point related issue, maybe some physical issue, maybe memory, CPU, etc. Then you can go and check any authentication in between the endpoint and the access point. So you can go from top to bottom, you can go and check, or you can go from bottom to top and you can go and check. So what are the touch points? So whenever we are talking about the issue, we should go and check the touch points. So what are the things can be there? So here you can see at this in the diagram, you can see that you can go and check the channel visibility. You can go and check the access point feasibility, you can go and check the IP reachability in between the uh, access point and the WLC, and then the cap web tunnel related configurations or cap web related issues that we can go and check. Then we can go and check the authentication, the ICE integration, how it is integrated with the WLC. Again, we can go and check in case of dynamic address assignment that the DHCP and the DNS servers are working properly or not. Okay. So let's discuss more about the approach that we have to use or we should use while doing the troubleshooting. So for any troubleshooting, we should define the problem. So we should know what's the problem first. Then to reach out to the solution, we should have the multiple ways. Say for example, if certain destination, say for example, if ISP is down, or say for example, a certain destination is down, a certain website is down, then what are the things you will do? Obviously, we'll do the ping and trace route, and you can check the ping drop. You can go and check the trace route at which particular hop it is dropping. Now with ping, once you come to know that this is the point I'm unable to reach, then you can go log into that particular device, and then you can check that from there what are the issues. So here also we should first of all understand the problem. Is ISP issue or it's a website issue? It's a slowness, loss, latency, jitter. Likewise, here we can go and check, is it an authentication issue? It's a AP issue. It's a uh, WLC issue, etc. Okay, so we should know first of all what is the problem. Once we identify the problem, so from problem definition we should identify the problem. So we can go and ask questions related to problem definition, and we should finally know that what's the problem. Then we can go and do the testing. Now the testing means that we should have the basic sets of command. So basic set of command related to the basic troubleshooting. Once we do the basic set of, once we run the basic set of command, then we should go and analyze that in depth, and then we can move to the solution. Now here again you can see that the analysis phase, again we have chance with our questions and with our analysis to redefine the problem statement. Okay, so finding the problem is 50% to solve the problem. That's the thing. If you know the exact problem, where is the problem, that is the 50% of the solution for any type of troubleshooting. All right, so define the problem, understand the possible triggers, know the expected behavior. If we are able to reproduce it, do not jump to the conclusion initially. Understand the client state. We know that if we are using the bottom to top approach, so what is the state of client means the state of the machine who is connecting with AP. So is the application slowness? Are they are getting some IP address or flap in IP address, or they are not getting any IP address? Do any problem with the authentication? Are they able not, are they are not able to see the SSID, or maybe SSID strength or the signal strength is very slow or less. So those things should be added, and these things should go inside the uh, questions. So what you are doing, that you are going and asking that these questions, what exactly you are facing. So for example, application slowness, that means you have done the authentication, you have the IP address, you have the RF health, you can see the SSID. Again, application slowness can map to the RF health also. So if you have weak length, weak signal, then maybe the slowness of the application, correct? So we need to understand, here you can see this chart, that problem, then questions, and while you're doing the analysis, again redefine the problem. That's the important key we have. So let's know where is the process the client is currently at. Key item to know for the effective troubleshooting, needed to narrow down your problem scope. That's the key. Narrow down your problem. The controller keeps client state for all connected clients. Some items handle on the AP only probes, authentication, etc. We know this thing that these are the touch points. So you should know the touch point, narrow down the problem, reach out what exactly at which particular point the problem is there, and then solve it. So now again you can see that again if we go and break out this, so at what level? So we are going from the, say for example, if I start from top to bottom, so that means we are going from, actually this is bottom to top. So suppose I have client, and then once I have the client, obviously this client is connected with AP. So here you can see the AP related things that we can go and list. So listen for the beacons that uh, these are again related to clients, correct? So you can go and list out these informations. So you're listening for the beacons. The client can request probe, then they will get the response, the authentication request, authentication response. Here your authentication will go complete. Again, we are going to discuss more about authentication in upcoming section, in the security section. So where we'll go and learn about various ways of authentication and security feature inside wireless. So yeah, so you're listening, then you are sending the probe, and then the authentication is happening. That's the unauthenticated unassociated. So client want to associate with the AP. That's the process, or that's the phase. Then state 2 where you have authenticated unassociated. So you are getting the network, that's the SSID. You click to the uh, join button, you want to join it, and then your password is working. So that means you're authenticated but still you're unassociated. So what we can do, association request, association response, EAP over LAN authentication, encrypt the data, forward user data. So these are the 10 steps that you'll find that you have issue related to beacon, probe, authentication, association, or any type of authentication in between the user and the Redis server, end-to-end authentication. Next was the connection process. So we have discussed about this process earlier in the last slide. Probe, you're sending the probe, then you're getting the response, you're sending the association, remember authentication and then association. Then you can see that we have this process of 802.1x authentication. We are going to discuss this in the security section, more about the authentication and the security. Then exchange of encryption keys, DHCP, and then finally you will move to the run state. We know this is the final state, run state, where each and everything is working perfectly. Now again, if you want to know all the states more and more, so we have the policy enforcement module, that's the PIM in short, inside the split MAC architecture, the start till run. So here you can see step number 1 till the last step, start. So 1, 2, 3, 4, 5, 6, 7, 8 states we have. And if it is in run state, that means everything is working fine. So initial start of the client authentication check, 8021x, that is again .1x requirement, L2 authentication completed, WIP. If you have the WIP key, we'll discuss about security later on. Then DHCP request, web auth request, and finally in the run state. So in between, you may have any issue that you have to detect at exactly what point you have issue, and then you have to solve it. This is the final flow chart. Here you can see on your screen that is start, check the authentication, then .1x required, then your L2 is completed. If it is not, authentication failure. If it is, then you will go and move to the WIP required. WIP should be 100% successful. Then you will go and move to the next step. Next step, here you can see that you have the DHCP required. Again, DHCP required, then you have web required, web auth required. If it is fail, again it will go and stop. So likewise, you can see the complete chart here where you have L2 policy .1x, web required 8021x, OpenSSID, mobility, DHCP web keys, and again if you don't have any .1x, then it will go to the run state. So it will go and complete the steps. Say for example, it can go like this and this to reach to the run state. So it doesn't mean that always I have all the policy and it will go and cross all the 20 steps or all the steps that we are seeing here. But yeah, these are the steps and these are the touch points where we should go and examine and try to resolve in between that. Okay, so this is the troubleshooting option and how we can go and define and define the problem and uh, do the solution. So narrow down the problem, reach to the nearby touch point, go there and try to check exactly which technology the problem belongs to and then try to resolve it. In 3.4, we have to learn about IP services. In that, we have NTP, NAT, first hop redundancy protocol, and then multicast. So let's start with NTP, Network Time Protocol. We used to give the same time, obviously the time and the date, to all the devices in the enterprise network infrastructure. Now, one of the most important use case for this is that nowadays all the devices they are doing authentication with respect to their certificates. And for all those certificates, all digital certificates, we need to sync the time to all the devices in the IT infrastructure. So that's one of the main use case we have for NTP. Now, how we are going to do that? We'll see that, we'll discuss more about that. But we may have some external server hosted in cloud, or we may have some internal server inside in premises, or we may have any Cisco devices that is working as a NTP master or NTP server. So all these options are available. There are some terminology used inside NTP. Say for example, what is a stratum? So what is happening? That NTP device will form an association with NTP device closer to the time source. So you have your time source nearby and that measurement is the stratum. So for example, that a stratum 1 versus 2 means that if it is 1, that means your source is nearby. If it is 2, that means your source is 2 hop away. Source means the time source. Okay. Now, how we are going to configure the NTP? We have client server model. We'll see that in the lab section. So one is the NTP master and other will work as a client. We can do peer-to-peer as well. Now, peer-to-peer means, obviously we know peer-to-peer means point-to-point. So peered NTP device can get their time from each other depending on who is the closest. That is the lowest stratum. We'll see that all these things in the lab section. Now NTP, say control packet or NTP message exchange, we can do the encryption as well. So we have that encryption feature for NTP that also we can verify in the lab. Now here in the diagram you can see that you have the time source, and then suppose we are at router D. It's very easy and simple that we can go and simply give NTP server and then the server 1 versus 2. Now for example, if there are 2 server and one you want to give priority, so we have this keyword called prefer. So first will be preferred and then it will go and check the other. The NTP can do the tiered approach as well. So what does it mean? That since you're getting the NTP information from the servers, that's router D, C can get all those information for D as well. So that's the tiered approach. So here you can see that for C, the server is nothing but router D. So I can go to C and then I can tell, okay, NTP server and the server IP is 51111. Okay. Likewise, we can go and do the configuration for router A, and I can tell, okay, for router A, your NTP server is router C. So that hierarchy we can follow. Suppose in case that you don't have any external time source or maybe internal time source, in that case, any router, we can make that as a authoritative source or the NTP master. And from there, it will go and take the NTP information, or it will send the NTP information to all the clients. Again, in the diagram, you can see that we can do the peering as well. So suppose if we want to have some fallback or redundancy type of thing, so we can go and do the peering configuration as well. So here you can see that router D, I want to make as a master. So NTP master is the keyword, and then 10 is the stratum number. We can go to the router D, we can set the time, whatever current time is there, and then we can make that as a master. Then for A and B, here you can see that A and B I can go and make as a peer as well. So suppose if the Ethernet link will go down, because they are peer, they will update their NTP information to each other. So this is the way that we can go and create the master, and obviously we can go and create the client as well. So master will send and client will get the information. We'll see this in the lab section in the upcoming recording. Apart from that, we can go and do the authentication as well. Here you can see that I have NTP master, and then I can go and use NTP authentication, MD5 and then the password. Then I can go to the client side, and those client side I can go and tell, okay, NTP authenticate the key, the NTP trusted key, and what is the NTP server IP. Okay, so this way that master is sending the information to the clients, but the message exchange in between them is the MD5 encrypted, or MD5 actually authenticated. All right. We have some other commands as well. If you want to disable the NTP, we can go to the interface and disable it. If you want to do max association, means how many clients that a master has, so we can go and do the max association, 10, 20, etc. Just to prevent the interfaces, we can go and do the loopback interfaces. So in that case, if any of the physical interface is down, still the NTP is reachable via the loopback, and that's the standard configuration we have in the industry. If you go and check the NTP source, the AAA radius, or maybe TACACS authentication source addresses, TFTP source addresses. Generally, we used to use the loopback addresses because that will be always up, and any physical interface is down, still that loopback will be reachable. Then there are some verification. We can go and type show clock. We can check the time, show NTP status. It will tell you the detail about the NTP information. And finally, we can go and check the NTP association as well. All right, so let's just stop here, and in next section, we'll do the lab related to NTP. Let us perform the lab task. In this lab, we have router R1. So let me show you that I have a router that is connected with a switch that is 105. The router interface is 00, switch interface is 00. So over these interfaces, I'm going to enable the NTP. First of all, we'll go and check the time. So here you can see the time for router 1 is this. Then I can go and make this as a NTP master. Now my router 1 is NTP master. Then I can go to the switch, and then I can go to the NTP, and then I can give the server IP. Server IP is 10.111.1, and that's it. So I created master, and then I have this client who knows that how to reach to the server, what's the IP of the server. Then we can go and verify this. So we have two main verification command. One is show NTP association and one is show NTP status. Okay, so these are the two commands that we usually use to verify. Now suppose if we want to do the authentication. So for authentication, I can go ahead and use the NTP authentication key, say for example MD5 and Cisco. Now from other side, what you have to do is you have to go and do this NTP, first of all authenticate, then NTP authentication key, and that's it. So these are the commands that we should go and use. So here you can see that you should use trusted key as well. Key numbers for trusted times of source, say trusted key. I can go and give one. And if you go to NTP, the options that you can see here, you have the authentication key, and then you can go and use this trusted key as well. So this is the way we can go and check the we can put the authentication in between client and the server, or in between master and the server. Now other options, you can see clearly that you have authentication, you have max associations, you have peer command, you have server command, you have source command, etc. So now I can go and check show NTP association, and in the R1 also we can go and check show NTP association, show NTP status as well. All right, so that's the way that we can go and run and verify the commands related to NTP. We have done the lab for the NTP. That lab I have done actually over the URL, but we haven't seen the exact result that it should come. So then I have created this topology. Obviously, this topology I created for HSRP, another lab, but here I want to show you the NTP configuration. I have made this R2 as a NTP master, and this router 4 and router 5, although I have changed the uh, display, means this is a router, but I have changed the symbol. It is looking like a, PC or end machine. Anyways, I'm going to use these devices as a end machine as well, but R4, R5 and R2, they are part of one LAN segment. Even R3 is also part of LAN segment. I have done the configuration related to NTP to these devices on 4, 5 and 2. So if I go and log into router number 2, say for example I am here, and if I go and show you show run section NTP, so you'll see that here's the master, and what's time? Time is this 18/20/20. Now if I go to R3 and if I go and check show NTP status, you can see that it is synchronized with this IP, and show NTP. What other options we have? Association. So here you can see the association as well. We can go and check show clock. It is getting time from the master. So likewise, I haven't done any configuration to R3. So let me go and this is the R3. So the we have done for R3. Let me see that if I have done the configuration for R4 and R5. So if I go to R4 and we see show run section NTP. Yep, that's configuration is there. And if I go and check show run section NTP, NTP server and some clock period is there, it's okay. So everywhere you can see that this way we can do the lab. You can go and check the association, and you can go and check the status should show synchronized. All right, so let's stop here. In 3.4, we have to learn about network address translation and port address translation. Now, when we are talking about NAT, this is simply that you are translating one IP versus other. So there, actually, if you read the textbook, so it is given that you are translating private to public address, but actually it's not 100% correct. We can translate any IP to any IP, and that's the network address translation. But mainly we used to translate private address to public address just to save the private address space, and even in this way we are getting first level of security as well. So now we are doing the translation. At that time you will find that we may have three models. We may translate, for example, many to few. So for example, many to few means you have many private addresses and then you have less number of public addresses. Or you can do one-to-one translation or a static NAT. So that means you may have a dynamic NAT, you may have a static NAT, and then finally there are a chance that you are translating to one IP with multiple port. So that is nothing but port address translation. So these are the variations we have in the NAT, and then we'll learn different type of terminologies used inside the NAT. Obviously in Cisco, what are the things that can be used? Before that, we know that we have public address, that is the internet or routable address. We have private address for class A, B, and C. When we want to do, our aim is to do the private to public address translation. Uh, Somewhere it is written that you are translating unregistered address to registered address. So that's also true. Then what type of NAT we have? We have a static NAT, we have dynamic NAT, we have NAT overload, or we have port address translation. Now, I told you that we have some terminologies in NAT. So what terminologies are there? You have inside local, inside global, outside global, outside local. Wow. So what does it mean? How can I understand that what is inside local, what is inside global, outside local, outside global? So here in the diagram, you can understand, suppose this is the NAT router I have, where I'm enabling the NAT. I have my inside IP, and then I have my uh, inside global. Actually, this is outside IP, but technically it is as per the NAT document that this is your inside, obviously local, that is your private address, and then this is your inside global, that is the outside. Then when you are reaching towards the host B, that's your destination. So for that perspective, the NATed address. So here you can see this NAT. Uh, we are doing the NAT in this particular address. This is the public address from other side. So that will be the global, outside global. And then again, you'll find that your outside local address, actually, this address is represented by 99.1.1.1.2. So that is also the outside local address. So local, global, global means that's the routable from one side. Then you have local and global. Most of the time you'll find that the local and the global outside addresses are the same. Now, if you see the packet flow, so when you are sending the packet and you are doing the NAT and then you are sending to the destination, what is happening? So you know what is your source, you know what is your destination. Now this is the destination host because I can't send packet to private address, correct? I should send this to this particular destination. Obviously, here you can see at the destination end, the NAT will happen and the packet will get delivered to the destination. So you have source and destination. When it came here to the NAT router, so NAT will change the source IP. So here you can see that source IP has been changed to this IP plus port, but your destination address will be the same. Finally, when it reaches to the destination where you have the 99 address, obviously this 99 address will get converted to 1.5, and what he will think that my source is 55. And then same way the reverse uh, route will happen. So this is, so from A to B, and then again B to A will happen in the reverse direction. So what you can think here, that at each hop, because the NAT is there, or you can think that whenever you're doing the NAT, obviously NAT will change the source. So here source address is changing, and here when you are reaching to the destination, if you send the return packet again, the source will get changed. Correct. So what is your source here? Whatever destination for A, that will be the source for B. So that means the uh, B destination. So what will be the destination of B? That will be 10.1.1.10, but it should go to 55 address. Correct. So here you can see that destination, it will get reversed. So the source will be 192.168.1.5, but destination will be 55.1.1.1, and then the port number. How we can go and enable on the Cisco devices? We should go, so suppose if you have your Cisco router here and you are enabling the NAT, this is your inside, and obviously this is your outside. So you have to go and give the command IP inside and IP NAT inside and IP NAT outside to these interfaces. Then we have option, we can create the pool for pool of say for example public addresses where I want to do the translation. Then I can create the access list where I can put the private address, and then I have to go and give the NAT statement. This is for dynamic NAT. Then for static NAT, because I don't have the pool of addresses, for example, because I am doing the overload over the interface. So I'll show you the statement for a static for NAT overload and static NAT. Static NAT will be very easy. So let's check. Say static NAT will be very easy. The one-to-one. Okay. Then you have NAT. So for example, overload, where you want to do the um, translation with respect to interface with various port number, and then you have the dynamic NAT where you have many to many. Remember, many to many translation or many to few many translation. So here you can see that this case dynamic NAT, that I have pool of public address like this. Then I'll go and create the source like this, and then I have to go and give one NAT statement. So what will be the NAT statement? Let me show you the NAT statement in the next slide. Alright, so let me go to the next slide. Here you can see that you have the NAT statement. Let me erase this, and so here you can see that this is your, say for example, this is your access list, this is my private, and this should be first thing. Then this should be second, that you should define your public address, and then you have this NAT statement. So what you are doing basically, IP NAT inside source, so this will call this IP, and then you are translating to this IP, that is 2. So 1 to 2, inside to outside. Now how to do with respect to overload? So for that, let me show you that as well. And obviously we are going to do the lab, so it will be much more clear. Here you can see that in this case you have interface, you don't have this pool, but you have the interface. Over the interface you are doing the overload. How we can verify it? We have show IP NAT translation, show IP NAT stats. If you want to debug, we can go and do debug IP NAT. If you want to clear the translation table, then we can go and do the clear IP NAT translation. Okay, so let's stop here, and in the next section we'll perform the lab. Let us perform the lab task. So in this lab we have the small network, and IP that I'm going to use here is 10.1.1.0, that's the gateway. This is .3, this is .4. These routers I'm going to use as a host machine. They are not doing the routing, but they're working as a host. And for outside, I'm going to use 200.1.1.1.0, where at this point I have .1 and this point I have .2. Okay, so it's very simple topology, and this device is going to work as a NAT device. All right, so let's do that. I have already assigned the IP address. I haven't enabled the NAT on any of the devices. So let's do this. All right, so what we can do as per the diagram, R1, the gig 01 will become outside, 02 will become inside. So I'll go to router number 1, and here I should go and do the configuration. So let me do that. Say 0/1 is working as a IP NAT outside, and then interface gig 0 slash wow. So let me do interface gig 0/2 should work as a IP NAT inside. I'm running this configuration, this lab over the virtual machine, so that's why we are getting some sort of CPU hog errors. That's okay. So I have two interfaces assigned as a outside and inside. Then I should go and do the configuration for NAT. First of all, I want to do the NAT uh, dynamic NAT configuration. So where what we need to do, we need to create the ACL entries. So I can go and create IP access list, and then I can give a name. So for example, my host having IP range of 10, and let's do like this. I can give a standard as well, because I know that I have the ACL where I want to use only IP addresses. And then I can go and give the name. So for example, host 10. Then I can go and give permit 10.1.1.3, and then permit 10.1.1.4. These are the two IP I have here. 10.1.1.3, you can see that gateway is 10.1.1.1. And then I have 10.1.1.4, its gateway is 10.1.1.1, like that. And we are using no IP routing. That means if you go and check show IP route, you'll find that your routing is disabled. They're working as a host machine. All right, so I have my ACL created, what I want now. Next, I want to create pool of IP addresses. We have IP address, for example, this point, this external interface is 200.1.1.1.1, but let's see that I want to use say 200.1.1.1.5 to 10. So this is the pool of address I want to use. What we can do, that I can go here and I can create IP NAT, and then here you can see that we have pool. So let's create that IP NAT pool. Name of the pool is, say for example, NAT pool. Then what will be the address? So let's go and give the address 201.1.5. You can see the start address it is asking, and then it is asking the end address. Then I can go and give the net mask 255.255.255 dot anything. Say for example 248. Okay, Okay, it is telling that it should fall inside 240, so that will be 16 or the 14 valid addresses. All right, so once we have this, then what is the final thing that we need to do? Say IP NAT, and then you have to use the statement. So what is that? Say here you can see that IP NAT, what is your source? That will be the ACL. And what is the ACL? That was host 10. And then what is the pool name? We have the pool name called NAT pool, and that's it. So let's see that my access list name is correct. So host 10, that's 100% correct. And then we can go and verify the NAT configuration. So I can go and check NAT pool. All right, so now we have the correct NAT configuration. I can go here to host number 3 and then host number 4. So if I ping say 200.1.1.2, it should be reachable, right? And if I go here and check the NAT, show IP NAT translation. So let's see, it's not showing any NAT. Show an interface gig 0/1. Let's see the NAT inside and outside. So this is the outside, and if I go and check 2, this is the inside. First of all, let me check that from here I am able to ping to my gateway or not, and this is working. Then let me go and check that from here I am able to ping to my router outside interface or not. That is also correct. Then from here, do I am able to ping to the NAT address, that is 200.115, and it has some problem. So let's see. And show run interface gig 0/1. So here I can see that I have this address and this subnet mask. If I go and check my host section, alright, so I'll go and try to change this ACL, but you can see that we are doing the correct methodology to do this. Say 10.1.1, for example, 0. Let me see, do I have option to give wildcard? So I'm taking complete range here, and let's see. What's the final result? So I should go and remove few of the statement from here. Let me go and use IP access list standard host 10, and then I'll remove 10, 20, 30. Alright, so let's quickly see that what is the configuration. So permit 0, these wildcard bits. Wow. So let me do this one more time. What I want here, I want to permit, and I want to permit 10.1.1.0, 0.0.0.255, And then if you go and check show IP access list, you can understand why this is coming, because the wildcard that I have given was wrong. I should give the correct wildcard, otherwise it will obviously do like this. So we'll go here and we'll remove this line that is 40, and then we can go and verify. Finally, our access list is this, and then we can go here and try to reach the destinations. Say for example this is okay, they should be reachable, 200.111, but what about 200.112? And suppose if it work, then we should have a NAT entry over router 1 show IP NAT translation. So what are the verification commands we have? We have show IP NAT translation, and then we have show IP NAT stats. Okay, so what it is telling, that you have 01. So let's see that I have interface 02, that is inside, 01 is outside. Then we have the ACL, and what's that? 10 pool, NAT pool. Then you have this NAT pool where you have this start IP, this end IP. Okay. Now at this point of time, my IP that I'm using here is not routable. It's not reachable. I don't have the reachable IP address. So what I will do, that this scenario should work, is that I'll go and I should use the NAT overload configuration. So what does it mean? I should go and use IP NAT, and we have the, let's see that what we have. We have IP NAT source, and source is the list, and what was that? Source list, say host 10. Then I'm going to use the PAT. So the interface, now what interface we have? We have the interface gigabit Ethernet, and that interface is nothing but 0/1. 0/1 overload. Now we can go and check the NAT configuration. So we can go and check sure and selection NAT. Let's see. So now we have two statements here, and one statement is related to dynamic NAT, one statement is related to PAT. So if first statement will not work, then it will go and check the second statement. So now if you go and check 200.112, still it is not working. And if you go and check the show IP NAT translations and stats, so NAT translation is not working. And then we'll go and check the stats as well. So you can see that the stat is also not working. Now what wrong we have done here is, so if you go and check the syntax, you'll find that, let me remove this statement first. And then I'll go and use a IP, even let me remove the upper statement as well, 0. Okay, so what is wrong here? Why it is not working? When I'm using this IP NAT, I should use source list. That's the complete statement actually. And then the host, and then we have the pull. That pull is nothing but the NAT pull. That's it. So this is the valid configuration now. You should go and check. At least it should start translating the packets, correct? So if you go and do the ping for 2222, and now if you go check show IP NAT translation and show IP NAT stat, translations. I have built the lab over the viral, and in viral we are seeing some issue that NAT is not working properly. Although we have done the configuration, the same configuration I have done in GNS. Here you can see my laptop, all the same type of devices, and only thing that the interface is different, but same IP schema, everything is same, even the configuration and all the rules that I have created, each and everything is the same. Now here you can see that we have IP NAT inside, we have IP NAT outside. So let me show you that I have serial interface, and then I have fast Ethernet interface, and then I have this NAT configuration, then I have the access list 10 configuration. So we have all these configuration that we have studied in the previous recording. I just wanted to show you the verification command. So if you go and check show IP route, this is working as a host machine. I can ping to my gateway, that is 10111, and here you can see the diagram that this interface F00 is 10111, then this is 200.1111, and then you have the outside IP that is 200.1112. So let's do the verification. If I go and ping 200.1.1.2, you can see I'm able to reach, and if I go here and check show IP NAT translations, so here you can see the translation. I have one entry coming from this. The protocol is ICMP. If I go here to this device, that is the outside device, and if I go and enable say line VTY024 login local, and then if I give the username and the password Cisco, and then if I go here and do the telnet 201.1.2, connection refused by the host. But if I go and check the translation history, you can see that it tried to convert the IP, and on top you can see that I have inside global, inside local. So inside local to inside global, and then outside local and outside global are almost the same, correct? So in the same way we can go and create the PAT as well. So what was the command for that? Just for your revision, show IP NAT, and we can go and give source, and then we can go and give the interface. We know that the interface I have 0/0, I can use overload. Okay, what are the verification commands we have? We have show IP NAT translation, show IP NAT stats. So these are the command and the verification. Better we can do the lab over the GNS3. In 3.4c, we have to learn about FHRP, and we have to understand the theory, and then we have to perform the lab task as well related to first hop redundancy protocol, that is the hot standby redundancy protocol, HSRP, and then VRRP. All right, so let's start with HSRP. Uh, First of all, why we need first hop redundancy protocol? We need first hop redundancy protocol because you can see this diagram here. You'll find that, okay, uh, I can go and reach to the switch and then I can go out, or I can do anything, correct? The problem here is that suppose if this link will go down, then what we can do? Obviously, all the devices in the network, they will lose the control. Why? Because you have only one path, you have only one dependency. So you don't have triangle in a network, or you don't have loop in a network, or you don't have redundancy. Suppose if you have this type of connection, and then if these devices can work as an active or a standby or primary or secondary, if this link is down, still you have the way that you can go and reach outside, correct? So that's actually the concept, or that's actually the need behind creating the first hop redundancy protocol. Now, doing so, there is one other problem. Suppose if you want to use this path via this switch, so what will be the gateway address to the host? Because generally we used to hard code the gateway address. So either gateway address will be this switch physical interface, so this interface here, or maybe this interface here. Suppose if your switch is down, this end host machine, they can't dynamically change the gateway. So rather than, what is the strategy here is that you should use some virtual gateway, or you should have some virtual router in between these physical devices falling in the same network, and that virtual IP we are going to give as a gateway address to the client. So either if first or maybe second switch will go down, there is no impact in a network. So we have the label of redundancy. Now we have multiple protocols. We are going to discuss about hot standby redundancy protocol. Here you can see that you have switch 1 and switch 2. One is working as a active, one is working as a standby. Rest other devices are the listening router. As per the highest priority, so there is priority. So for example, 200 versus 10, so higher is better. As per the highest priority, one of the device will work as a active, and then rest of them will work as a standby and listening. In a group, we can go and put say 16 devices. So here you can see that you have priority from 0 to 255, and default is 100. Higher is better. So what does it mean? It means that although you have the virtual IP, and suppose his priority is 200 and this priority is, although it is rating 100 and 150, but let it be, this is 100. So the traffic will go in this direction. Now what will be the fallback? If you have LAN interface will go down, obviously they will do some sort of re-election, and this device, because one is unavailable, so you have one other path that you can go in this direction. But again, there is one question that what will happen if your WAN interface will go down? Okay, so there may be chance that your switch will go and reboot, your this interface will go down, your WAN interface will go down. What will happen with the active traffic? What will happen with the flow of the traffic? How it will converge? How there will be the fault tolerance, etc. Okay, so we can discuss that. Never mind, one by one. First of all, when we have the two routers in a group or two switch in a group, we can go and create, or we can do the HSRP configuration. Then they will go and elect who is the active and who is the standby. And the message that they are going to send across in between devices are, say, initial, learn, listening, speak, standby, and active. So in active state, we have this devices that is actively, means they will form the HSRP neighbor relationship. We can't tell that neighbor relationship, but they will form the HSRP in between them, and one will be the HSRP active, one will be the standby. So here you can see that in the active state, an interface in an active state is the live gateway and will forward traffic sent to the virtual IP addresses. Host will use the virtual IP as their gateway. The active router will respond to the ARP request for the virtual IP and the virtual MAC. So far we have discussed about virtual IP, but we have one other concept as well, that's the virtual MAC. Now the hello packet exchange for HSRP, we have is peak, standby, and active. Okay. All right, so let's quickly discuss about the virtual MAC. And once you go and do the basic configuration, I'll show you that virtual MAC in the next slide. So you can go to the interface, or you can go to the interface VLAN. You can go and use this command standby. You can define the priority. You can go and define the virtual IP, etc., etc. We'll see all these things in the lab. Then here you can see that this is the diagram, although our lab diagram is a bit different. I'll show you in the lab diagram. So these things I'm going to configure in the lab. Instead of interface VLAN, I'm going to use any Ethernet interface or any physical interface. So you can go and do the configuration. Now, important thing here, you can see that the ARP response will come from the virtual MAC. So this particular virtual MAC, what is the format? So here you can see this is the format 000.0C07AC, and then the group number. This XX is in the hex, that will represent the group number. So suppose if I go and give the HSRP group as 10, if you convert 10 into the hex, it will come 08. So that's why the final MAC address is 000.0C07AC08. Okay. We have this. If you want, we can do the MAC address manual configuration as well. If you want, we can do the authentication configuration as well. Then we have the concept of prompt. So what is mean by prompt? Suppose this is active and this is a standby, and it will go and reboot. So this will become active, but suppose it will come back online. So if you enable the prompt feature, that means when the active will come, the system will detect, oh, he has the highest priority. So for example, he has a priority 200, he has a priority 100. So this guy has the highest priority. That means again he will become active and he will become the standby if we do the prompt, if we enable the preemption. Otherwise, active will be active, standby will be a standby. After the failure, standby become active, he will be the active. Okay. So we have the command. We can go and use a standby one prompt. If you want, you can disable the prompt as well. Apart from that, we know that we have the timers for HSRP. By default, that will be 3 second and 10 second. 3 second of hello timer, 10 second of dead, means you are sending 3 packets. 4th packet you are not getting response. You'll make that your HSRP group partner is not active, maybe some issue, maybe you have a split brain issue, etc. They're using the multicast address 224002 and the UDP port 1984 for this particular hello exchange. If we want, we can give the time in milliseconds as well. So if you want aggressive timer, if you want fast convergence, you can go and change the hello timer. We have a few of the verification command that we can go and check show a standby. We can go and check show a standby brief. All right, so we have few more slides related to failure as well. So let's complete these slides, and in next session anyways we have to do the lab, so I'll go and discuss more and more in that. Now here you can see that tracking. Say for example, this link is down. Suppose his priority is 150 and this guy priority is 130. So obviously he is active and he is a standby. Now what you can do, you can track the interface that is going to WAN, say 223, and then you can decrement the priority, for example 60. So if we decrement the priority, if this link is down, what will happen? This priority will become 90, and this is what 130, 130. So that means the traffic will go in this direction. And that's the use of the live tracking, or that's the use of the tracking, that you can track the interface, you can decrement the priority, and the standby will become the active, and the traffic will go in that direction. All right, so these are the points you have. At this point of time, you can think that how we can check this link. Obviously, this link is tracked. If this link is down, automatically it will go in this direction. If this device will go, obviously it will go in this direction. If this is down, you should do the track and then decrement some sort of priority. So this direction will go in, and this traffic will go in this direction. All right, so these are the concepts related to HSRP. Let's stop here and perform the lab task. All right, so let's do the lab. I have created this topology in GNS3. Here you can see that I have router 2, I have router 3, and then I have one router. I have changed the display, means I have changed the look for these devices. It's a router, it's showing you as a cloud. Then I have this routers 4 and 5, but it looks like they are the host or end machines. I have assigned the IP addresses as per this schema 10110. This is obviously the LAN segment that you can see behind R2 and behind R3. And then I have a static route going or reaching towards R1 from R2 and R3. Okay, so let's do and enable the HSRP over R2 and R3. Obviously, I'm going to use F00 for these interfaces, and then I'll go and assign the default gateway for R4 and R5. So let's do this. If I am inside R5, let me check that what gateway I have given to these devices. This IP default gateway is 10.1.1.2. That's not correct. Means I should change this. I will go and change this because I want to use the default gateway as the virtual IP. So before changing anything here to these devices, let's go and do the configuration for the HSRP, hot standby redundancy protocol. So we can go to F00 and then you can use the keyword as standby. Then you can see that you have options: authentication, delay, IP, MAC, preempt, priority, redirect, timers, track, use BIA, burnt in address, and version. All right, so what we want to give the group, and then I want to give the virtual IP, say for example 10.1.1.250. I don't want to make this secondary, so leave it. So now I have assigned the virtual IP here. Then what I will do that I'll go and give the priority as well, because this R2 I want to make as the active at the master, you can think, and the other one will be the backup or standby. So what configuration we have done? We have done only two configuration: standby IP and the priority. I can go to R3. You can see that they try to move from speak standby active, and if I go and check show a standby brief, so he don't know who is the standby, but this state is active. Great. So let's go and do the configuration to R3. We have R2 and R3 connected via the LAN interface. I can go and do the debug as well, so we can see some of the packets. I can go to the fast Ethernet interface and priority I'll give 100. Now you can see that the state disable to init, redundancy, this is the group, disable init, and now you can see the other messages. I'll pause here, you can have a look. init to listen, passive, active, the group, this become the backup because it has a lower priority. Then it is telling who is the active, what is the VIP IP, what is the router ID. Then you can see all these messages. Now it is sending the hello packet after every 3 seconds. So since the debug is on this device, I'll go back here and we can check the standby. If I can get the detail. So what I can do here, that I can enter. Here you can see that what's the virtual IP, what's the MAC. We have discussed about this because we have used the group 10, so that's hex is 0A. This is by default running V version 1, the hello and dead timer, the active router is local. Now if you go and check the brief, then you can see who is the active, who is the standby. So it's very easy to actually configure at this point of time what we want. I want to go to these devices and I want to use the IP default gateway as 10.1.1.250. So these devices, they should have the proper gateway. All right. Now what we can do that we can go and test it. So I can go and ping to the R1. R1 has one loopback interface. So what does it mean? If I go to R2 and if I can say, for example, ping 1111, let's see if it is reachable. Otherwise, I'll go and create a static route from R2 to R1. Sure, and let me check the routing section. In R2, I can't see that I have any static route. So I'll do one thing. I'll go and create a static default route for the device 200.1.1.1.2. And if I ping now, yep, like that. If I can go here to R3 and let me undebug all to run section IP route. If we have any routing, no. And what IP we have here? So we have this 201. I can go and create IP route 000 and then the gateway 201.1.1.2. And if I ping 1111, if I can source as well, reachable. So now if I go to this guy here, that is one of the client. I should give the client instead of the R4. So suppose this is client 4, and if I ping 11111, that's the outside. Let's see if I'm able to ping. Yep. And if I do the trace route for 1111, let's see how it is going. So first it is going to the gateway that I have. This is the router from where I'm going, and then I'm going outside, correct? So what we can do here is that we can do the ping, and subsequently we can shut down one of the interface. So what I'm going to do, I'm going to shut down the R2 F00 interface. So I'll go to R2 interface F0/0, shut it down. So in that case, the HSRP will go change, and you can see a standby brief. Both sides you can see now it is unknown, but if you go to R3 and if you go check show standby brief, so he is the active, although his priority is less. Now we haven't done the print at this point of time. So if I go here and interface F0/0, if I do no shut and You can see that this is still active, although his priority is less, and this guy here is, let me show you the full output. Let me just this. So still it is in speak because we haven't enabled the prompt command. So still it is in standby. You can see state is a standby, although the priority is high. So for that reason, what we can do, we can go to 00 and standby 10, and we can go and enable the prompt command. I don't want to use delay and other thing, but if I do the prompt here, you can see the selection has been changed. I should go and do the prompt here as well. So I can go to R3 and I can enable prompt here as well. Now if you go and check the output, he is active because of the prompt command. Now likewise, if you want to go and check this interface up and down, so that also we can track serial 00 as well in this present scenario. So what does it mean? My priority is 200 and this guy has priority of 100. I will decrement the priority by 110. So what I can do, I can go to interface 00 and standby 10. We can track the serial interface 0/0, and then we can decrement the priority by, say for example, 110. Correct? Now if I go and make this interface down, so you can see that this is now unreachable. The traffic should redirect and it should go. So let's see that what happened actually. So standby brief. Now this is still showing active, but if I go here to R3, if you go and check show standby brief, what's the priority? 110. And this guy, what's the priority? 90. Okay, so that means the traffic should go, and here you can see that this link is down. So that means now this is the active one. So the traffic should go from here and then it should go and reach to here, although we have the different IP to the subnet, so it's okay. But if you go and let me stop the ping. Now if I do the trace route for 1111, you can see that how it is going. It's trying to reach to its fixed gateway. Let me see what's the gateway it has. Show run section default, that's true, and show IP interface brief. So what should be the order here, that it should try and check 1.3, means when I'm doing the trace route, so it should go by this, but actually the problem here is to announce the network in the bottom. So from R3, if we go and check the R3, from R3 I should go and ping 111 and source serial 0/0. Oops, let me see what source it has. 0/1. Yep. So we can see that main idea I want to show you here, that this guy, that's the router number 1, is become active, although it is showing active, but its priority become 90, and this guy is tracking the interface and he is the active one, means now its state is showing a standby. Let's see the configuration is standby. We'll do the troubleshooting. So what is there? No configuration. And let's see, show run interface F00, where we have done all the configuration. So we haven't done much configuration on R3, and probably that's the reason that is not showing you the result. So even we are seeing the troubleshooting as well. We can go here and give the command standby 10, and your priority by default will be 100, we know that, and then a standby 10, do the prompt if the state is changing, and then we can go and check show. Now you can see something is happening here. Now if I go and do the first route, now you can see that it is going by that path, correct? So that means if I do the ping now, okay, a little bit less, it is happening. And if I go and do the interface serial 00, no shutdown, because prompt is enabled, so this link will become active. We'll get the message and do show standby brief. And now if I do the shutdown, so it is down. So see, for some time it is unreachable now, but now it is going from the other side. So now it is this in a speak state. And if you go and check the standby configuration, this is the active. Alright, so this is the way that we can go and do the configuration. There are a few configurations as well, like if you want to change the timers, if you want to use the authentication, but this is the main thing that we use to uh, do or perform with respect to HSRP. Next we have VRRP. VRRP is nothing but Virtual Router Redundancy Protocol. Very much similar to the Cisco HSRP. The difference is that this is the industry standard and HSRP is Cisco standard. Almost they are same, but there are a few differences. We'll see that what differences they have. First of all, you can see their timer is 1 second. Then you can see that the MAC address is 224.0.0.18. The VRP prompt is on by default. VRP cannot directly track interfaces. It can track an object which is tied to an interface. Okay, so you can see that there are some difference, and again we are in the existing WAN. If you go to SD-WAN, specifically Cisco Viptela SD-WAN, in that we don't have HSRP, but we can run VRRP, and there we have the customized VRRP that I have explained in my SD-WAN course that you can refer. So VRRP in the existing WAN, VRRP in the SD-WAN, both are very different. Now this VRRP is very much like HSRP. It is working as a gateway, so we can have the virtual IP, we can have the priority. Again, higher priority is better. We can go and tune the timers. We can have the we can go and enable the authentication. We have the reserve MAC address, which is different. There we have the different MAC address. Here you have 4 times 05E00 dot 01XX. Okay, and here the name of the primary, say active, and the standby is master, and the backup that will go and verify in the lab section. We can go and use no VRRP prompt because by default this will be on. You can go, if you want, you can disable. You can go and check show VRRP. Very much same type of output you'll get that you have in HSRP. Now we have one very interesting topic here, that do VRRP and HSRP can do the load balancing. Because for load balancing we have Cisco proprietary protocol, that is GLBP, that is not in this particular course, but we have discussed earlier in section maybe 1 or section 2 that how this GLBP is working. GLBP is not that popular like VRRP or HSRP due to some GLBP. They have some reason behind that. They have some internal reason. The active forwarder or the standby, they are not able to do a load balancing in failure scenario, etc. Means they have some internal issues with GLBP. You will find that most of the places we are using either HSRP or VRRP. Now suppose you want to do the load balancing. You know that one of the router is active, one is a standby, and suppose if you have thousands of client or endpoint, you want that 500 will go via one router and 500 will go via other 100, the 500 will go via other router. Then how we can achieve that? So what I'm telling here, let me try to draw, and even you can see the configuration. That's the manual load balancing configuration we have. So what I'm telling here, that say I have these two devices and they are part of, say for example, VRRP or maybe HSRP. Now we know that one is active and one is standby, or one is master and then backup in case of HSRP and VRRP. And suppose if you have 1,000 users or 1,000 clients, then obviously as per the standard configuration, 1,000 of the devices will go via one gateway, one active gateway. So there is no load balancing. Rather, what we can do, that we can create group. So here you can see that inside VLAN we are creating one group and then we are creating other group. So one group is having higher priority, other group having lower priority. Obviously the VIP is different, virtual IP is different. Likewise, that means that as a whole, this will be the active for 500 user and this will be the active for 500 users, and as a whole they will work as an active load balancer. Okay, now once you have this configuration and you want to check it, verify it, you can go and check show standby brief. So in that output, what you will find, that you will go and get the output related to both the groups. So here you can see that you can see the first and the second device, active standby, standby active. Now this is not the limitation, but actually this is the feature that we can do the manual load balancing across the routers. All right, so let's stop here. We'll do the VRRP lab that we have done like HSRP, and then we'll check this load balancing methodology as well. Let us perform the lab task. Same lab setup, we'll go and enable the VRRP instead of the HSRP. So let me go and fix the screen. I have VRRP, HSRP enabled on router 1 and 2, so I can do this thing. No standby, say 10, like that. If I can do, interface should be fast Ethernet and 10. Then I'll go and remove the HSRP from R3 as well. So first of all, I will go and do the basic configuration, and once I will do the basic configuration, then we'll go and do the load balancing configuration as well. All right, so here we are in the router number 1. We are in the correct interface. I can go and enable VRRP 10 and we can see what options we have. So I have this IP, say 10.1.1.2.50, and that's it. Then VRRP 10. What other things we have? We can give the authentication, the preempt, priority, shutdown timers track, and track is event tracking. So here what I can do, that VRRP 10 and the say priority 150, that's the higher priority. Then we can go and check to show VRRP brief. So here you have the master, and we'll go to the other side. Here we can go and make this IPs 10.1.1.1.2.50. By default, the priority will be 100. So you will see that you need to backup. Now if I go here and check, so the priority, the preempt, the master address, the group address. So we can see that is the master. And if you go here and check, do show VRRP brief, so here's the backup. Okay, so here you can see that the master address, and you can see the master address, and then you have the group address, etc. So it is working fine, there's no problem. It will work. Now what we want here is that I want to create two groups. So for example, one IP will be 250, other I'll create 251. R4 I will put in one group, R5 I will put in another group. So I'll create two group, 10 and 20, and let's do that. So now what I will do that I'll go to R2. I already have the group that is this, whose priority is this. I will go and create one more. So for example 20, and the IP is 10.1.1.251. That is going to be the default gateway IP for 50% of the clients. And then the VRRP 20, the priority, say for example 50. So 150 and 50. Likewise, I'll go to R3 and VRRP 20 IP is 10.1.1.251, and VRRP 20. By default, it will be 100, so we can understand this that will be the master. Now we can go and check show VRRP brief. So here you can see backup master, correct? And if I go here and if I go and check show VRRP brief, so here you can see that master backup. So it is working. Only thing that we need to do that we should go to the client and we should change the gateway address. Rest each and everything will be the same. Now if you want to see the VRRP detail, you can go and check like this. Alright, so let's stop here. You can see that this way we can go and do the lab related to VRRP. In 3.4D, we have to learn about multicast, and we have to learn about multicast routing protocols as well, such as PIM and then IGMP. So let's start. Now, before starting multicast, I'm going to give you a brief introduction about what is multicast MAC address, the basic stuff related to multicast. So for example, we know that we have three different type of packets, say unicast packet, broadcast, multicast, even we have anycast as well. That's actually the type of communication. So unicast means that one-to-one communication. And there are such protocol, for example, Ospf, BGP, Eigrp, and other IGP protocol. They are basically destination-based routing protocol, and they are using. You can tell that the unicast-based routing protocol. Then we have broadcast. Now, broadcast means one to all. So someone is sending message to all. Then we have interesting packet type, that is the multicast. And that multicast is one to group. Again, we have anycast as well, that is one to nearby. Okay. In this section, obviously, we are going to focus more on multicast. So multicast means that the method of communication is from one to group. Now here, a very important fact is that if we compare unicast routing protocol and multicast routing protocol, the basic difference is that unicast routing protocol, you are building destination based routing, or you are doing destination based routing. In multicast, we are doing source based routing, means someone is the multicast source and then you have the multicast client. Those clients want to join the multicast source feed. That's the basic difference, and we'll understand more and more about that. So you have to define the group who are interested to join the multicast source. So multicast source is sending the feed, and we'll see that how the feed is sended. There are different methodologies, and then my host, they want to join the feed. Okay, so it's something like a reverse routing tree we are creating, and actually this is nothing but RPF. We'll see that in next section, but let me still focus on basics. So let's continue the basics. We know that we have class A, B, C, D addresses. D is there 224.0.0, 239, 255, 255, 255. That is reserved for multicast address. Then we have the link local addresses used for control mechanism or to find the neighbors. Say for example 224.0.0.0 up to 224.0.0.255. Then we have public and private address ranges for multicast. Here you can see all the linked local addresses. A few of them we have used earlier. So for example, Ospf, hello packets, and then the DRBDR selection. For that, we have different multicast link local address, then RIP, then Eigrp, then others as well. Right. So now basic question here is that in multicast we don't have multicast MAC address. So the question here is that how multicast they are framing their multicast MAC address. Correct? We know that MAC address is of 48-bit. So what is happening that whatever IPv4 multicast address we have, they are taking 23 bits from there, and then they are adding 25 bits of this address. So 25 plus 23, you will get 48 bit of MAC address. Now how it will be? So here you can see that this address 00, obviously this is in hex. If you convert this in binary, so 0 means 40, then 1 means 0001, then again 0 and 0, then you have 5, and then you have E, and then last 0. So now you have 8 plus 8 plus 8 plus 1, that means 25 bits. Now what is happening that we are going to add last 23 bit of the IPv4 address. So 8 plus 8 plus 7. So that means up to here. So if you go add this here, so you will get this, correct? Now this address again, if you go and convert into the hexadecimal, so you will find 0 1 0 0, then you have to check this. What is this? So 1 2 4, so that means 5, then 2 4 8, so 8 plus 4 plus 1, like that you have to do the calculation. I'll show you that what it will look like, or how it is look like. You can see here that now finally it will be looking like this. So this is the multicast MAC address, and here you can see the mathematics for that. So in decimal it is looking like this. In hex, because we are concerned or we are looking for hex format, MAC address is in hex format, so it will look like this. Okay. Now while doing this methodology, we have one problem. What problem we have? So for example, this two address 225 and 231, if you go and convert their MAC address, you will find that the MAC address is same. Why so? Because again, if you go and take 23 bits, so here you can see that 23 bits, so 8 plus 8 plus 7 and 8 plus 8 plus 7, these 23 bits are common, and again first 25 bits are also common because that's fixed. So this 25 plus 23, if you go and add, you'll find the same MAC address for different IPv4 multicast address. Now we have that problem, and truth is that there are 5 different bits. That means there are 32 multicast IP addresses for which we have single MAC address. Okay, why? Because you have 23 bit, that is you are taking from IPv4 address, and then because multicast address should start with 224, so that's why you have these 4 fixed bit. So you have this fixed 23 bits and then 4 fixed bit. You have 5 variable bits that can be anything, and the combination of these 5 bits can have 32 multicast address. So that's the problem we have in the multicast, but the arrangement of the bits and the IPv4 multicast address is in a way that this is not a bigger issue. So it's not a big thing in multicast. All right, so these are the basic things that we have discussed. That's what is multicast and what are the address family, how we are going to construct the multicast address, and what are the common IPv4 multicast address we have. So let's stop here. In next section, we'll discuss more about the multicast routing. Let us discuss about multicast routing protocol or multicast protocol. We have different protocols. We are going to discuss about that one by one. We know that we have a multicast protocol, and if we go and learn a little bit deep about that, you'll come to know that, okay, although we have multicast protocol, but still we need IGP, Interior Gateway Protocol, and the multicast protocol. Both are working hand on hand to provide the final multicast feed from source to the receivers. What protocols we have? We have protocol independent multicast. We have multicast Ospf, distance vector multicast routing protocol, core based trees. Now to enable this on Cisco devices, we have to run a command IP multicast routing. Again, when we'll go and study about PIM, we'll find that they have PIM, dense, sparse, dense mode, etc. Means different variations are there for that protocol. Now, earlier in this uh, section, we have a study that they are going to use reverse path forwarding, or they are going to look that exactly where is my source. So unlike destination protocol like OSPF or EIGRP, multicast is going to form the tree, and that tree will be based on the source. So not based on the destination, but based on the source, they are going to form their multicast tree, and that methodology is reverse path forwarding. Sometimes we'll tell this, okay, we have variations of PIM. So for example, dense mode, so we are flooding and then we are pruning. Or we have other methodology where we are flooding the feeds, and then in whatever link, I don't have the multicast host, so we used to prune that, because obviously I don't have the receivers, so why I will flood those feed in those particular link or locations. Now here you can say that we have different parameters like S and G, source, comma group. You will find a star comma G as well, that is for RAN debut point, and the group. Group means the multicast address. Source is multicast source. All right, then upstream and downstream. These are the concepts. So upstream means that the link that is going towards or reaching towards the multicast server or the feed, actual feed. And downstream means where you have the receivers. So the link that is going towards the receiver. Here you can see, say for example, for router 1, the link here that is going to the multicast source is the upstream, and then these interfaces are the downstream. One condition is there, that you should have multicast host in the downstream. Otherwise, there is no point of having the downstream if you don't have any multicast host. Okay, so how it is building the tree? First of all, it will send all the feeds, and in that location where there is no multicast host, they will prune those links. They will not send the feed on those links. So that's the flood and prune. At least the prune methodology we have. Now here you can see that we have multicast protocol like PIM, OSPF, multicast OSPF, etc. Then other concept we have is IGMP. Now this is not the PIM, or this is not the multicast OSPF, etc. IGMP is a protocol that is specific to the host or those type of group they want to join the multicast server or multicast source, correct? So for that, we have the Internet Group Management Protocol, IGMP. And now you can see that you have version 1, 2, and 3. Now, most popular is version 2 and 3. So what is happening in this case? Say, remember, if you see this diagram, you'll find that, okay, you are sending the feed, but you should have interested receiver or receivers who will show the interest for that particular multicast feed. Suppose if you have 3 to 4 different type of sources who are sending the multicast feed, obviously one host can take only one multicast feed, So in that regard, there should be membership for that particular source. And that's the key we have. All right. So let's discuss that how this IGMP is working. Now, it's very easy to enable. You can go and enable the IGMP. Actually, when we are going and creating when we are enabling the multicast, it should enable, or by default in Cisco switches, this multicast is IGMP is enabled. But if you want to change the uh, version, then we have command here. You can see that I can go and change the version, say IP IGMP version 1, because no configuration is required to enable IGMP, except then you have to go and enable IP multicast routing. Okay, so let's try to understand that how this IGMP group protocol is working. So for example, IGMP version 1 router send out query every 60 seconds. Remember the words here, you can see that IGMP version 1 routers, say your end machine, they should have gateway. That means they will connect it with switch, and the switch will go and connect with the router. So now that router, that the nearby router, the gateway router, who is very near to the host or the receivers, the router is sending query every 60 seconds in case of IGMP version 1 to determine if any host need access to multicast server. So because router has built the tree, router know that with help of PIM how he can reach to the multicast source. So he is sending the query. Now this query is the multicast address 224.0.0.1. Now what is happening after that? Interested host must reply with a membership report. That's important. So host, they are replying with membership report for that query, stating that what multicast group they wish to join. Correct? So router is sending query, and host, they are sending the membership report. Just they want to join. Now there is problem with IGMP version 1 because they does not allow host to dynamically leave a group. Instead, if no membership report are received after 3 times the query interval, so router keeps sending query, 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 and you're not sending the membership report, then router will come to know, okay, these guys are not interested. They have turned off their receiving, or they have turned off, or they are not interested to receive the feed. It's something like when we are using, so for example, radio or FM channel, we tune to go to different band, and whatever band we want to use, that particular feed will come and that music will play on. Now suppose you're not interested and you don't want to join any group, so that means you will not respond for the query. Now this is with version 1. Now if you go and check version 2, you'll find that there is enhancement in version 2 related to leave message. So what is happening in version 2? The queries are sent from the router as a general query or group specific query. Additionally, host can send a leave group. So now what is happening, the routers, instead of query, they are sending group specific query to the host, and host, say once they are joined, obviously they have their membership report while they are joining the or they are responding the query. So what the host can do now, that the host can send the leave message as well. Okay, I'm not interested, I'm turning off my receiving capability, I don't want to receive it. Then it will be stopped. Now all versions of IGMP elect one router to be designated querier for the subnet. The router with the lowest IP become the designated. Again, if you go and if you check some more details, suppose in that group, if I have 4 or 5 routers, so they will go and select who will send the query to all the host, and which is the router who will get all the membership report, and then he will forward that message to the multicast source, or who is sending the multicast feed. IGMP version 1 is not compatible with version 2. If any IGMP version 1 router exists on the network, all routers should running version 1. So version 1 and 2 are not compatible even in the CCNP core. The syllabus is to know understand version 2 and version 3 as well. Now, so version 2 is running by default, and it's most of the places you'll find version 2, but still in version 3 we have enhancement. So what enhancement we have in version 3? Version 3 enhancement in V2 by supporting source-based filtering of multicast group. So now we have the filtering for the source. Essentially, when a host responds to an IGMP query with membership report, it can specifically identify which sources within the multicast group to leave or join or not to join. Okay, so that means that uh, we have even more granularity inside version 3 where we can do the source-based filtering as well. Now here you can see that you have multi-cast source, then you have the router who will send the query, and then the host, they will send the membership report. That membership report is nothing but they want to join or they're willing to join. We know from this that who is the upstream. So FA01 is the upstream, and then downstream you have 2, 3, and 4. But in 04 you can see that there is no multicast host. That means the downstream interfaces are 2 and 3. FA02 and FA03 are the downstream. How we can go and enable it? By default, version 2 is up and running. Once you enable IP multicast routing, you can go and check show IP IGMP groups. If you want to have any static group, you can go and do that. If your IGMP wants to join any specific multicast group, you have both the options, correct? And suppose if you want to filter, so we have the filtering option as well. Here you can see that I have created access list for 10 and 11. These are the multicast address. And then in the IGMP access group, we want to join only 10 and 11. Rest anything will come, it will not join. Okay, so let me quickly log into the router, and I'll show you this configuration in CLI. Alright, so we have this topology. I'll go and show you all the commands configuration in router 2. So let me go here in router 2, and in router 2, what interfaces we have? We have A00, and I'm just showing you the configurations, how it look like. So first of all, I should go there and enable IP multicast routing, and then I can go to the interface, and I can go and check IP IGMP version, and say for example by default version will be there. So if we go and check this, oops, show IP IGMP, you can see that you have groups, interface, membership. One of the important command we have is the membership. Okay, so at the moment nothing is there, so that's why most of the things are empty. I can go here and okay, let's see that what other things we have here. You can see that group, interface, membership, SSM, UDLR, VRF. Okay, leave it. So I'll go here to the interface, save 00 IP IGMP version, so for example 2. Okay, and then obviously we can go and check show IP IGMP interface, say FA0/0. These are the important commands. So here you can see that the internet address, the IGMP is disabled on interface. Okay, multicast routing is disabled, TTL0, no multicast group, interface is up and running. Later if you go and enable the PIM, and you can go and check the mroute as well, we'll check that later on. Okay, so I want to join any of the group, say IPIGMP, join the group. So let me see if I can see here. Okay, IPIGMP. Yep, you can go to the interface and then you can join the group. Say, as per our example, 226.1, say 5.10. and we'll leave that source show IP IGMP interface FS0/0. Now here you can see that IGMP is enabled, version 2, the query interval, the timeout, max time. Okay, so I can see that join interface is this. Now again, I can go to that interface and I want to use the IP IGMP join. And if I go here and check what options we have, so we can go and use the static group as well, and say 226 1.5.11, and we can go and see this. All right. Suppose if you want to filter, so you can go and use the filter as well. Although you can see that the static group is not working, because if we want to do any manual methods, at that time only we are using the static group. But I'll go and use the join group one more time to the interface F00 IP IGMP join group 226 say 11511 and then 12 and then say. Okay, so you can see that you have these groups, and now if you want to filter, you can go and create the access list 10, say permit these addresses. So I want to permit 10 and 11, and then I want to use this IP IGMP access group, say 10, and then we can go and verify the output. So just I'm showing that this is the way that once you apply this filter, so it will not go and join, although it is showing here in the configuration, but it will not go and join the other group, whatever not mentioned in the ACL list. Right, so let's stop here. Next important topic, we have PIM, that is protocol independent multicast. Now here you can see that PIM has variation. It can run in dense mode, sparse mode, and sparse dense mode. That's the Cisco proprietary. Now we should understand that why and what is the use case of dense mode and then the sparse mode. Now dense mode is something like you are doing the flood and prune method, means you have the multicast source. He is flooding the multicast traffic throughout the network, and then the receivers, if you have receivers, they will join that. If you don't have receivers, it will get pruned, correct? But what is happening in the sparse mode is that is the intelligent way of doing flood and prune method. So in this case, you have one authority termed as a rendezvous point, RP. So what will happen that RP will get selected, and now it's the responsibility of rendezvous point or the RP is to do the flooding in the network. So it's something like you are saving the bandwidth, you are selective throughout the network, you know who has the authority to do the flood and prune to build the multicast tree. Correct. So in this way, we can save the bandwidth. We will not unnecessarily flood the multicast traffic throughout the network. So it's a bandwidth savior methodology. It's efficient, but again, there is use case that at what time we should use the dense mode, what time we should use the sparse mode. So here you can see that the key point is that when we are going to use the dense mode, so suppose in a network, if we have the large number of multicast hosts, so in that case, actually it's very easy. So everyone will send the multicast feed, and then pruning will happen. It's very easy, and it's like you can think, if you want to compare, then you can compare that, okay, so for example, RIP versus OSPF. RIP is something, router RIP and then network command, but OSPF define the area, limit the LSAs, do the things in efficient manner. They will do the SPF calculations and all, correct? Although in other hand, the sparse mode, again, the thing is that you are doing it efficiently, but the use case is that when you have the limited number of multicast hosts. Okay? So both have pros, both have cons, but recommended that we should use the sparse mode, at least in the enterprise network. All right, so here you can see that in PIM dense mode, you have the multicast source. It's sending the feed to all the throughout the network, and where you don't have the host multicast receivers, so you will go and do the pruning. So here you can see that now finally we have the tree structure that is built towards the receivers. So sender and receiver, source and receivers. Right? This is the dense mode. Easy to use, very easy to build, but it is consuming the bandwidth. Now the next we have the sparse mode. In sparse mode, suppose if we have two multicast source here who is going to send the feed, first of all they will go and select the rendezvous point. So here you can see the selection of RP will happen. Once you have the selection of RP, rendezvous point, then it's the responsibility of RP that he will send the feed to the selected interfaces where you have the multicast receiver. Obviously, this is the efficient way to build and maintain the multicast routing or multicast feed. Great. Now you can see that you have version 1 and version 2. How we can go and enable it? We can go to the interface, and then we have option either we are running PIM in the dense mode or a sparse mode or a sparse dense mode. Now you have this RP option as well. So RP can be identified manually. Suppose this is your RP. You can go and run the command, manual command, and we have the auto RP in Cisco as well. So if you want to do it manually, the command is ippim RP address 192.168.1.1. Again, if you have the multicast source, so these are the feeds. We can go and create the ACL, and with the RP address, we can go and map this ACL entry. Correct. So this thing we have seen earlier as well in the previous section. When we have created the ACL just to limit the number of multicast source, and then if you want, you can map with the RP as well. Okay. Next, the verification and troubleshooting commands. So we can go and check show IP IGMP groups, show IP IGMP neighbors, show IP PIM who is the RP. Then we have debug command, debug IP IGMP, debug IP PIM. Okay, so let's do one thing. Let's stop here, and in next section we'll continue from here, and then I'll show you these CLA command in the GNS lab as well. Let's continue. So we have some commands to do the verification and debug as well. Once we build the multicast tree, then we can go and check show IP mroute. We have already discussed about source comma group entry, and if you have the rendezvous point, you'll find the star comma G entry as well. We have the upstream and the downstream interfaces. Suppose if you go and run show IP mroute in dense mode, you will see the output like this. So here you can see that you have the source, and then you have the multicast group address, the uptime, then incoming interface, the outgoing interface, who is your RPF reverse path forwarding neighbor, and here you can see the interfaces. Okay, so there is flag as well. Suppose if flag is not mentioned, this is dense mode, and if you go and check the flag, so let me show you that. Show IP mroute, and here you can see the flag is showing SC, that is for sparse mode. Okay, and you can see a star comma G entry for the rendezvous point. So if you are running the multicast in the sparse mode, then you will see output like this. Okay, so there are some notes as well. You can go and check the upstream and then downstream interfaces. So notice that SG pairing is labeled as a star comma G entry in the sparse mode. We can have multiple source share with the same multicast tree. The rendezvous point is 10.1.1.10. The flag is SC, that means route is running in a sparse mode. Then you can go and check who is the outgoing interface, who is the incoming interface. So it's just like the dense mode. The incoming interfaces indicates the upstream, means where is your multicast source, and the outgoing interface showing is the downstream, that where is your receivers. All right, so let me quickly log into the lab, the same lab we have, and I'll run through a few of the important commands just for just to know that the commands are supported and what type of commands we can run in the PIM mode. Let me go and start this lab. Again, I'll go to R2. We have done some of testing. I'll go to R3, and inside R3, so first of all, we should go and enable IP multicast routing. See, that's the first command. Then I can go to the interface and we can go and run IP PIM, and here you can see that the mode. So we have dense mode, we have a sparse mode, sparse dense mode. Here you can see sparse dense mode, sparse mode, dense mode. So let me go and use this dense mode. Once we go and run the dense mode, then here you can see that DR has been changed, who is the neighbor. So I can go and check show IP PIM neighbors and show IP. Actually, this command is quite useful. Show IP PIM neighbor. It will show you whoever is your neighbor, and even we can go and check the interfaces as well. Okay. So now you can see the DR and DR priority. Now next, what we can do, that suppose if you want to go and check the RP, so we can go and assign that RP address, rendezvous point. So I can go to IP PIM and the RP address. What is that address? Say 192.168.1.1. We can give the ACL as well. I'll show you the ACL formation in this command. So for example, ACL 10 and then permit 226, say 11, 10, 11, 12, etc. And then I can go and assign this to IP PIM RP address 192.168.1.10 and then 10. Okay, so these are the commands that we can go and run. We can go and check that what commands we have used related to PIM and related to RP. Okay, so we have enabled the PIM in dense mode, and then we have enabled the RP as well. If you want to check show IP mroute, we can go and check like this. All right, so you can see that all the addresses that we have given, for that we have a star comma G entry, and you can see the flag as well. Now flag is telling that we are running SJC. So S stand for obviously sparse, and then we have the flag J and C. J stand for join the SPT. You have a small s as well. You have big S as well. And C is connected. Okay. Show IP PIM and the neighbor. Show IP PIM interfaces detail. We know that we have one interface here. So here you can see that PIM is enabled. PIM version is 2, and everything related to PIM. I can go here and make this as a dense mode. So IP. Remember, whenever we are doing say IP PIM in dense mode. Okay, so at that time there is no selection of RP, but at the moment you'll go and give the RP address. So here you can see that you are seeing all this rendezvous point and all. That's the reason we are seeing this. So what I'll do here, I'll go quickly and I will remove this statement and this statement, and again I'll go to interface F0/0 IP PIM in dense mode and interface serial 0/0. Let me see that what interface we have. Interface is serial 0/1. So IP PIM in dense mode. For dense mode, nothing is required. Simply if we run that much command, that is good and enough. So I can go and check show IP mroute, and since this is running in dense mode, so you will see now I should clear this clear IP mroute. Wow, VRF clear IP. So you can see that VRF is there and we don't have VRF related to that. I just wanted to clear these multicast entry. Alright, so I have cleared the entries and now I can see that we have the DC, day for dense. Because we have enabled this feature on router 2 as well, and if you go and check, we are getting the feeds from router 2. So if I go and check if I have some configuration related to IGMP and all, so you can see that he is willing to join the IGMP group. We have some access protection as well, and those entries actually I'm getting here. Okay, but the idea of concept behind this, that we have the D, C entry, and now if I go and assign the RP, so IP PIM RP address say 192.168.1.1, and then if you go and check mroute, so you can see the flag will change to sparse. So it is changing from dense to the sparse mode. Alright, so let's stop here. In section 4.0, we have to learn about network assurance. Here you can see the topic. We have to learn about various type of troubleshooting mechanism or diagnostic mechanism like trace route ping, SNMP, netflow, SLA, IPSLA, netconf, restconf, etc. Okay, so what I'm going to do that, as we have done earlier, one by one and section by section, module by module, we are going to discuss each and every topic. So let's start with debug. We have debugs and conditional debugs. We know that in Cisco routers and switches, we used to run debugs to know more about what is happening in the break scenario or what is happening behind the scene. But doing so, whenever we are enabling the debug, there is a chance that we can increase the CPU, obviously, because now you are getting all the informations about what is happening to that particular process. Again, Cisco has given one nice option that we can use conditional debug as well. Now, conditional debug is a way that we can prevent or protect from the utilization of high CPU and memory. We have certain commands to do that we'll go and check in the lab section. So what we can do, that we can go and enable debug. So for that, we should go to the exact mode and run debug, and then we have multiple options to enable that debug. We can go and undebug as well with the command no debug protocol. So enable the protocol or turn on the protocol, take the logs, do the analysis and turn off the protocol. Then we have so debugging option. With that, we can understand that how many debugs that we have used, how many debugs actually are running in that device. Then we have conditional debug. So for example, I can go and use debug condition interface, and over that interface, what is happening will get to know. Again, for the conditional debug, we have option to do the no debug for the conditional debug, and conditional interface means debug over that interface. All right, so let me quickly log into the lab section and let me show you the lab topology as well. And then we'll go and enable the debug and we'll play around. So here you can see that I have my lab topology. It's very straightforward lab topology where you have 4 routers and you can see the network as well. The router 1 has IP 12.0.0.0.1 and router 2 has .2, then 3 has 23.0.0.3, etc. So let me quickly log into the device, and first of all let me show you the IP schema that we are using here. So I can go and run the script, show IP interface brief, select all, send the script. So you can see the IP assigned to the interfaces. So for example, for router number 4, I want to create one loopback as well. So I'll go and assign one loopback address for our future troubleshooting and testing. So here you can see R1, R2, R3, R4. These are the IP addresses. So far, I have assigned only the IP addresses. Later on, we'll go and run any of the routing protocol as well. So what I want to do here is that I want to do the ping to router number 2, and whose IP here you can see 12.0.0.2. So even we can do like this. So I'm going to do the ping to 12.0.0.2. Here you can see that I am sending the ping packet and ping is successful. So what I want to do here, that I will initiate the ping, and I can do the repeat count more number of times. Then I can go to router number 2 and I can enable the debug. So what I can do here, debug IP, and here you can see at what options you have. So we have long list of protocols that is supported. What I want to do here, I want to do the debug for IP. So let me do that. Alright, so debug IP, and then again after IP also you can see that we have options related to so many things. Say ICMP. Enter. Now you can see here at the moment I enable the debug, I can see that echo reply. So this device is sending the echo reply, correct? You can see it is sending the echo reply, and it is so fast because it is coming from here. I can go and stop this. So let me go and complete that, and here you can see there is still whatever requested are there in the buffer, still we can go and see that. Now in this case you can see there is no chance that I can go and turn off the debug because already it is cached, correct? So what you can do, that you can re-log into the device, or otherwise you have to wait to that particular point. It will come where you can go and stop the debug. So one thing you can see here, that at the moment I enable the debug, I start getting so many packets, correct? Now while it is going on, let me show you that what other option we have with the debug. Now it's gone seems, so I'll go here, and if you want to stop, you can go and use undebug all. Before doing that, let me show you that what debug we have on. So here you can see that it is showing that your debug is ICMP packet. Now if I go here and use IP packets detail instead of ICMP, and now if I go and show you show debug, now you can see that we have 2 debugs on. And now if I go and initiate the ping, while initiating the ping, let me reduce the size as well. So for example 3. Now you can see the debug is on and we are getting the output in detail because we have done IP packet detail. So we are getting the ICMP type and code that we are going to discuss in the upcoming session. So here you can see that with help of debug, we are getting much more information about the ping and what is happening behind the scene. Okay. Now next what we can do, next we can go and verify the conditional debug as well. Now before doing conditional debug, if we go and check the IP route, so I have created one IP route here for 2222. Say in router 2 I have one loopback 2.2.2.2. So for that I have created one IP route statement that I can go to the next router and then the next hop. Great. So now if I go and enable, say, debug IP packet details, and if I go and do the ping for 22222, so you can see that we have flood of message. Rather than getting the flood of message, what we can do that we can go and create one condition, say for example IP access list standard or maybe extended, where you can go and define the source and destination. So I want to do, say for example, permit IP host. My source is, say, this, and then I can go and give the destination as 22222. Then inside the debug statement, I can go and use it. So anyways, if I am using debug on this router, I should use the condition here, correct? So I can do this thing. I can copy and paste this condition here, and even here also I can run the debug, correct? So no problem. So here also I'll go and enable the debug IP packets in detail, and here I'll do undebug. Say for example undebug all. Now I can ping to 12.0.0.0.1 with the source of 222, and I can repeat, for example, 4 times. Now here you can see that you have this debug. Again, you have long list of debug packet that you want to shrink or you want to minimize that. So for that we have this option. I can go and use IP debug packets, and then you can see that I can use the ACL, although I don't have option to apply the named based ACL, correct? So I can go and create the same thing with the named based number based ACL. So I can go and create, say, IP access list, not IP access list extended. I can give the number, so we know that the number, so 1333 is my number. Permit IP, who is the source, set let's give the source and the wildcard, correct? So IP is 12.0.0.0.1, 0.0.0.0 means the host, and then the destination. All right, let me quickly see that what's the issue. If I just wanted to use the extended ACL, and do I have number for extended ACL? Here you can see it's a little bit different than the other. I can go and give the extended ACL number as 100, and then I can go and give permit IP host 12.0.0.1 and then host 2222. Great. Then we can go and apply to debug IP packets 100, correct? Detail. And then if I go and do the testing, so from other side I'll go and ping. So I can come here and I can do that ping one more time. Here it is. Oops. And here you can see that your table has decreased. So initially we have big table. Let me do that one more time. Now you are capturing the source and destination. Okay, so this way that we can go and use condition in terms of we can apply the ACL with the debug. The other variation we have actually is the condition. So I can go here and give the condition, and inside that condition I can go and match the fast Ethernet 0/1. Now you can see that one condition has been set, and then I can go and do the same thing. So let's do the ping. We can go and check here. So in this, what is happening, that the condition will match only fast Ethernet 0/1. You can go and check the condition, and you can see that one flag has been triggered. So this is the way that we can do the debug. So I have shown you the normal debug, then debug with ACL, then also we can go and use the debug with condition as well. The next topic, we have packet internet grouper or ping. Now, how ping working? Ping depends upon ICMP messages, and with help of ICMP message, we can determine that whether the remote destination is active or inactive, what's the round trip delay, the packet loss. Now, when we are sending the first packet with help of ping, we are sending the echo request, and if we are getting the echo reply in the specified time, that means that the remote destination is up, and then we can get certain information about remote destination. Now here you can see that ICMP type and code, these are the messages and codes the ping is using to get the information about the remote host. So first of all, it is sending the echo, that is the type 8, and then it is waiting for echo reply. Again, you can see that type 3, destination unreachable, network unreachable, host unreachable, protocol unreachable, etc. So we have long list of type and code. Say for example, other popular one is 11, time exceed code, time to leave exceed in transit, etc. So these are the code messages that we can go and refer while we are doing the troubleshooting. There are other characters as well. We are very much familiar with the exclamatory. That means it is successful. Dot means maybe some issue with the network. It is waiting. Maybe ARP resolution or any other network stuff. U means unreachable. Destination is unreachable. Q means source quench, destination too busy. M stands for could not fragment. Question mark means you don't know to reach to that particular IP in that subnet. Generally in firewall, when we used to ping without some specified information, we are getting this question mark. And then you have this AND, that means the packet life time exceeded. So let me log into the device in the lab section, and let me show you a few of the ICMP code messages. Alright, so I am in the lab, and here you can see the same lab setup we are using for ping as well. I can go here to R1, and then I can ping to 22222, and if I go and do this, maybe I can do ping from R1, and then I can go and verify in R2. So in R2 I'll go and enable the Debug Ip Packet in detail, and then I can do the ping say 1. So now here you can see that you are getting the information, and now you can go and check the ICMP code. So this is nothing but the echo, and again you can see that you have the echo reply as well. So you have the ICMP here, you can see who's the source, who's the destination. So if I am the source, so here you can see the source and the destination packet. You have the source and the destination packet. Again, you can see the source and destination. Means suppose for the destination, I will be the source. Means that thing will reverse. Again, here you can see that the ICMP type 0, that's the reply, and then ICMP echo. If I go and enable the debug on the source as well, so debug IP packet in detail, and then if I go and do the ping for one time, so here also you can see the message, the type length code, and the message, so 80 and 00. So that's okay. We're sending echo, we are sending the echo packet, and we're getting the response as well. Easy and straightforward. Now I'll go and do some trick. I'll go and go to interface F0/1 0, I'll make this shutdown. And now if I do that ping, so here you can see that now you're sending the echoes, but you will not get the response, correct? Because anyways the destination is down because the interface is down. And here you can see that we are sending this packet, but we are not getting any response back. So we are sending the echo and the reply is not coming back, correct? So constantly we are sending the echo packets and we are not getting the response. I'll go and make this no shut, and for example, if you go and check the routing, so this time I'll go and change the routing, means let me remove this default router statement. And then if we go and do the ping, so now again I am sending the echo, but we are seeing here that we are getting the dot, means that you don't have network to reach there because you don't have route, correct? So this time we are getting the dot 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 dot. Okay, this time you clearly can see that we are getting the dots. So now I can go here and do this as a this. All right. Next, what I want to do, I'll go to router number 2 or maybe router number 1 also, but I can go to router number 2 and then I can create one access list. Say access list 11 and deny 12.0.0.1, and then I'll go and apply to the interface in the inward direction, in the incoming direction. And then again, if I go and do the ping this time, so it is working. Maybe what exactly I was looking for, it is not the same. So let me quickly go and check. Show IP interface brief. What I want that the router number 2 should not accept 12.0.0.1 whenever it will come. Okay. So if you go and check 0/0, I have IP access group in the inward direction that should deny show IP access list 10, oh sorry, 11. Yeah, so it should deny, it should not do the ping, and 12.110 will come to this device in the ingress direction and it should drop it. So undebug all. If I do the ping, see, you're getting this unreachable. Say for example, some more. So I just wanted to show you this unreachable, and you can see here in the router number 2 that what type of message you are getting. So yeah, you have the echo, but you have type 3 and 13, that's unreachable as well. Both at the source location and the destination location, you can go and see this. Okay, so far we have discussed about debug, conditional debug, debug with condition, or debug with some access list. Again, you're seeing different type of ping messages and with different type of options as well. Okay, so adding to this, we have a nice advanced option in the ping, that is the conditional ping. So let me show you the simple ping. Whenever you're doing the ping, what is your simple ping? Your simple ping is telling that you are sending some echoes with some repetitive uh, frames, with some timeout, with some uh, frame size or packet size. So for example, 10 times, this is not successful. So let me quickly do one thing. Let me quickly go and remove the ACL, say no IP access group 11 in. And now if you do the ping, first of all, you should understand that we are getting the round trip information as well. How many packet, what is the packet loss, etc. So you have packet loss, round trip, and then the reachability. Three information you are getting, correct? But we can do more than this as well. So what I am telling here that you can go and do the extended ping as well. So suppose your destination is this, your repeat count, suppose I want to do this 2 repeat count. The datagram size I can go and give more or less. The timeout in second is okay. And you want to do extended ping? Yes, I want to do. What is the SOAR interface? I will leave this. You have any TOS in your IPv4 frame? We'll leave this as the default. 0 is the default. You want to set any DF bit? We can leave that. That is to not fragment bit. Validate reply data? No, we'll leave that. You have any pattern? You can leave that. So what I want to tell you here, this particular section is very important. Now remember, when you are doing the trace, and again the next topic is related to trace route. So you're going hop by hop by hop by hop. You will see the logic as well in the upcoming section. But you are not getting any information for the reverse direction or reverse route. That you can go and get from the record option. So here you can see that you have lose option, you have a strict option, record, timestamp, and verbose. If you want, you can use all. So if I go and use the lose one, I want to show you all. In lose, it's not that what exact path you want to give. So you have any exact path? If you don't have, that's the lose. If you want that your ping will go with certain route, it will go with certain hop, certain route. So that's the lose and strict. That is not that much informative in case of troubleshooting, but this record will be very much important. Timestamp is again just the timestamp. So at this point of time, I don't have the source route, so I will leave it. But if you have any, you can go and give the source. So here you can see that you have loose and verbose. You can go and you have any sweep range in sizes. You want to have any variable MTU size in between. If you want to give, leave it. Now here you can see that you have this output. Again, it's not that exactly informative that we are looking for. So you will not get much help while doing the troubleshooting related to two options, that is the loose and strict, but although they have their own use cases. But for response, so for response you will get that, okay? Not response, that record, you will get that. So let me go and do the same thing. So I'm going to do the ping, and IP is 222. This is my destination IP. Repeat count is 3. The rest of the things I will leave it. Extended yes. Source interface, leave it, and then say record. By default, it has maximum actually 9 number of hops. You can reduce, but you can't increase from this. So for example, I'll give 4. Now you can see this option is RV, that is record and verbose. I can go. We'll leave that sweep range, but here you can see that reply to request, correct? So how the packet you are sending, how it is coming back. So while it is coming back from here, it is going to this and it is going to this, correct? So that's actually the key we have that you will not get in the trace route. When you're doing the trace route, you don't know that if in case you have the asymmetric path. So here all the paths, although they are showing the same, because we don't have asymmetry at this point of time, but suppose if you have asymmetry in route, it will catch and it will give you the information about the asymmetry as well. Okay, so you can see the record route started from here the destination. This is the source and this is the destination actually, but the reply is coming to this and coming to this. So you can think like this: reply to response 0, reply to response 1. Now to add some more visibility here, what I will do, I'll go and run the some sort of IGP in between R1, R2, R3. So let me quickly do here. Router Eigrp 10 network 0000, no auto summary. Eigrp, I should take this and then I'll go and run copy paste this command to all the devices so I can do some bigger ping and bigger trace route. And then finally here. So that means if I go and check show IP route, we have one loopback at 44444. So I should get the loopback 4444 somewhere. So here you can see this 2222 and then here you can see 444. So if I ping 4444, okay, my ping is there. Now I want to do the extended ping. 444 is the destination. Hop count I will take, say for example, okay, 4 we can take. Datagram is okay, timeout is okay, extended I want to do. Source interface, leave it at this point of time. What I'm looking for is the record option and the verbose with that. So till 9 hop, although it is 4 or 5 hop away, we can go and check the reverse route we are looking for. Now you can see that where is your destination? This is your destination. Now if you go and check the diagram parallelly, so let me show you this diagram as well. In parallel, here you have the destination at what point? So you have 4444 and here you have, then this is dot 3, this is dot 4. So you can see your destination starting from here, then you have dot 4, so here, then you have 23003. See, from here you have 23, this interface, and then you have 12002, this interface. So basically we are talking about which interfaces? Basically we are talking about these interfaces, correct? And then finally you have 12.1. So that should be the response, correct? Response packet. Now if I do the trace route, and we haven't covered trace route at this point of time, but if I do the trace route for 44444 and you can see the output here. So to reach to 4444, how you're going, see, that's the difference. That's the big thing we have. So 12.1.1, here you can see 12.1.1.2, 23.0.0.3 and 34.0.0.3. So reaching here, coming back. It is showing you both the things, correct? Now if clearly you can check the trace route and the record option here. And I'm taking some more time here because this will be useful tool actually to do this. So here you can see that with a trace route, we are going here, we are going here, and then we are going here. With the record option, you can see that when we are reaching there, this interface, this interface, this interface, let me correct it. So dot 1, so not this interface. Let me quickly erase and draw both the things. So with the record option, this interface, and this interface, correct? And then you are reaching to 444. Again from 444, how you're coming? this interface, this interface, this interface means this is covering all the outgoing interface, incoming interface, correct? But with the trace route, outgoing interface, and that's the key, and that's the important information we have with the record option. So I hope you understand the power of ICMP as well, the power of ping as well, and you can utilize it for the troubleshooting. Next tool we have in our toolbox is the traceroute command. How traceroute is working is actually simple, that we know the destination and this testing is based on the destination. So what we are doing, that we are sending the UDP packet with invalid port to the destination. But I don't know that how many hops my destination is away. So for that reason, when I send my first packet, then I'll make TTL as 1. Obviously TTL 1 means at the moment it will go and hit the first router, the TTL will got expire, and then I will get message called ICMP exceed time message. That is TEM, time exceed message. So what does it mean? It means that your first 3 packet, actually we are sending 3 packets. So your first 3 packets by default, they reach to first hop, your TTL got expire, and then you are ready to send the next packet, next 3 packets for next hop. So next time we are adding TTL plus 1, so the TTL become 2, and then we are sending the packet. Now suppose at this point of time in our lab also that I am 4 hop away. So again I will go and send the packets because I am 4 hop away, correct? So again I will increase the TTL. Again I will get the message called ICMP time exceed. Next time I'll make my TTL as 4. So this time I have the destination with me. That means my UDP packet will go and reach to the destination. And how could I know that I have reached to the destination is with different type of code, because we are sending the packet to invalid port. So that means we'll get the message ICMP port unreachable, correct? So two type of messages we have. First of all, ICMP time to exceed, because I want to bypass that router, I want to add some more TTL and I want to proceed, correct? And at the moment I will go and reach to ICMP port unreachable, that means I reach my destination. And that's the way, actually that's very much hit and trial type of method, but that's the way we are reaching to the destination hop by hop. Now there are some terms, or there are some symbols that you will get. Say for example a star or asterisk, that is the probe timeout. A stands for administratively prohibited if you have any ACL or any other blocking. If you have Q stand for source quench, destination is busy. I stand for user interrupt test. Then U port unreachability, H host unreachability, N network unreachable, P protocol unreachable, timeout, and unknown packet type. Okay, so let's test this like we have done the ping test. So let me go and log into the lab and verify it. Although we have done the trace route, here you can see that I can go to next hop, next hop, next hop. Here you can see that I am sending 3, and again you can see that packets are in milliseconds. So 72 millisecond, 80 millisecond, and 72 millisecond. 3 packets we are sending for first hop. And here you can see the hops, the first destination, second, and third. At the moment you will go and reach to the destination, you'll get some other code, ICMP code. So let me show you that packet and detail. And if I do the trace route, so here you can see that what type of code messages we are getting, because we have 333. So total you can see how many packets we have sent, and that's why you have these many messages that you're getting here. And still we are getting, Let me go up because we are running EIGRP, so some EIGRP debugs may be coming up. All right, so yep. Let me scroll up. Let me do this thing and debug all, and will not get the debug. Let me scroll up. So here you can see that you have source and destination. This is the source, this is the destination, and you are sending the packet with the destination port that is invalid, because once it will reach to that particular destination, it will get some invalid code message. So here you can see that type 11 code 0. We can go back to our notes and we can check type 11 code 0 in the ICMP list. So here you can see type 11 code 0 time exceed, correct? And then we should have the unreachable code as well, that is the invalid port. Let me circle that, or let me spotlight this. So that will be 3 and 3. Type 3 code 3, that is port unreachable. So we are going to get from the destination 3 that's the code, and from the source, obviously whenever we are going to the next hop, that should be 11.0 time exceed. So let's go back to the lab that we have here, and we can go and check that in the code. So here you can see that you're sending the packet with the variable destination port. It is going to add 37 and then maybe 3839, etc. You can see 3839. You can see the ICMP code when you have the source and destination, and what code you are getting from the destination once you reach to the destination. So here you can see that we have this type 3 code 3, and that's true. That's the port invalid or port unreachable. Now this is not the only way then in Cisco devices that we can go and do the trace route. We have option that we can go and add the probe as well. So number of probes you want to add. Then if you want to add the TTL, means from where you want to start and where you want to stop. If you just want to make this little bit small, so you can do like this. Even if you want, you can go and increase the probe. Here you can see probe 10, and then I just want to show you this. So TTL is to 222, for example. So now here you can see if you want to check the latency, if you have to certain destination, you can go and check this. This is actually the round trip delay that we have. Like that we can go and add. Now in trace route also we have the extended trace route. So likewise we have the extended IP. We can go and do that. So here you can see that we are getting the options in the same way that we have in the last or in the extended ping, but obviously because this is trace route, so some of the options are different. Port number if you want to add, otherwise default will be okay. And if you want to record, you can go and record up to maximum 9. I don't want 9, so for example 4 only, and you can go and do like this. Still this is not as much clean that we have with the extended ping, but yeah, we have option to do the extended trace route filtering, all sort of option in the Cisco devices as well. We have the management protocol for the network, that's the simple network management protocol, SNMP. Let's first of all understand the terminologies used in SNMP. Basically, we have three main or major component. We have SNMP manager. You can think this as a collector where it is getting the information from the SNMP agents. So you have agents, that's the network devices, and you have manager where all those information are getting collected with help of MIB. So third very important component, we have the SNMP management information base. Now what is happening? Now these MIBs are nothing but the information that is stored inside the agents, and managers, they are using get, that means to retrieve the information, and suppose if they want to change certain parameters, they can use set. So managers, they are using get and set methodology to get the information, or if they want to change anything, they can change. Now again, the communication channel we'll see that we have versions of SNMP. So for example, community based version, SNMP version 1, SNMP version 2C, and then we have something like authentication or user based SNMP methodology as well, that is the SNMP version 3. But yeah, we have different version as per different RFC standard, and these SNMP or the SNMP protocol in general, they are used to collect the information for the management purposes. So for example, what type of information? Say interface monitoring type of information or protocol monitoring type of information. Now one of the popular tool for SNMP at this point of time we have, so for example, third party SolarWinds tool, where we are going to do the testing as well in the upcoming lab session. Uh, Most of the production network, they are using SolarWinds, or there are various tools as well. Just they are using SNMP methodology, same methodology that you have manager, you have agent, and then MIB, and then they are collecting information at a common place again for the analysis purpose. Now here you can see that the SNMP get method, we have three type of get method, means we are getting the method, we are getting the information, we are getting the next variable information, or we are getting the information in the bulk as well. So three get methods inside get method we have. And finally, we have SNMP notification as well. Now what is SNMP notification? This is again a type of information, and it is referred as a unsolicited asynchronous notification that can be generated as a trap or information. So in the configuration, I will show you that we can use the methods, the agents can use these methods to tell the manager about the various type of information. So in trap or maybe in inform, you have various type of information that you want to tell to the manager, and in the configuration I'll show you that what exactly trap look like. Now we have trap and we have inform. Most popular in these two is trap. That is less reliable as well. So what is happening actually, what's the core difference or basic difference between trap and inform is that trap is a message that the manager is getting that don't have any acknowledgement. On other hand, the inform, they have the acknowledgement as well. So that's the reason the trap is faster, or trap methodology is faster than the inform method. But yeah, inform method is reliable because it has its acknowledgement as well. So we know the basics terminology used in SNMP. Let's stop here, and next section we are going to study about SNMP MIB and versions of SNMP. Let us understand Cisco MIB and versions of SNMP. Now this MIB is nothing but a database, and this MIB is in form of tree structure. Again, if you want to learn more about MIB, you can go and refer these RFC 1213, and for traps we have 1215. And even with respect to Cisco, if you want to again see the tree structure and the hierarchy, you can go and check Cisco MIB, and you'll get long list of MIB related to most of the things. So for example, the information related to protocols, the information related to traps, the information related to flaps, information related to CPU, interface, monitoring, etc. etc. And again, major vendors, say for example, who is working on SNMP, SolarWinds and others, they are using this MIB, and they have the SNMP manager where they can go and collect all this information that I'll show you in the upcoming session, that how you can retrieve these informations, how you can query. So suppose if I have SNMP manager, I can send the query. That's nothing but the get method. I can send that get method, and once I do this get method, the responder, that is nothing but the agent, they will give me all the information that I query inside this string. Okay. Now we have three versions. We have version 1, 2C, and version 3. 1 and 2, SNMP version 1 and 2C, they are very much community based. So obviously they are doing the community based authentication. The method of authentication is the community string. Again, in the lab section, we'll see that we have the community string. Even we can put some sort of ACL as well for that if we want to filter out the uh, number of volume or number of requests we can put inside the ACL. That we'll see in the lab section. Then we have version 3, that's the secure model. We have version 3 is supporting, say for example, message integrity, authentication, and encryption. Now there is a huge improvement with respect to version 1 versus 2C, and you see that still most of the organizations, they are using community based version 2C. Why? Because they can do bulk retrieval of data. That's obviously the tables and large quantity of information. Again, these are uh, belonging to the tables. Whenever we are talking about tables, they are belonging to the database system. So maybe MySQL or any type of databases that these managers, they are using behind the scene. So maybe they can use MySQL or any type of database, depending upon those company and their partnership with the database companies. All right, so version 2 can get a large volume of data with less amount of expense. Expense here means the memory, the round trip delay, etc. That's the power we have with respect to 2C versus SNMP version 1. And when we are talking about version 3, this is based on the security model for users or users belonging to group. Now, what is the difference? I have the slide for that. Here you can see that we have model, we have label, authentication, encryption, and what is going to happen. Now, version 1 and 2C, we know that they are community based, so that's why we have the community string for obviously authentication, but they are no auth, no priv, no auth, no priv, no authentication, no priv. Uh, Again, I told you that community is itself a type of a string, or you can think a password just to do the authentication, but it's not exact authentication like you have MD5 SHA that we used to learn inside various other protocol like IPsec and others. Okay, but still you can think that community is a password, or it's a authentication way of protection to do the authentication between the agent and the manager. So for inside V3 again, V3 just not only supporting the authentication and the encryption, but they have uh, no auth, no priv method as well. So you can do username. So user the username match for the authentication. Then you have auth, no priv. Auth means authentication, no privacy. At that time you have the MD5, maybe SHA. At that time they will go and do the authentication. And finally it has auth and priv, where you are using both the MD5 and DX56 as a data encryption. Okay, so these are the versions we have related to SNMP. Let us understand the configuration, and obviously we are going to do the configuration in lab. Now, when we are doing the SNMP configuration, we can go and give the SNMP contact location chassis ID. Then we can go and verify as well. So for example, show SNMP contact location and chassis. Now, when we are configuring version 1 and version 2, we know these are the community-based versions. And what are the prerequisites then? How we can go and configure? So the prerequisite we have that we should follow these, at least these three things, that who is the manager, and we can put those managers in ACL, and what type of roles they have, like read only, read write, etc. Then if we want to cut down the SNMP MIB view or MIB view, just to protect to get too much information. Obviously what is happening that you have agent, and suppose you have 4 or 5 different manager, or obviously different IPs, means you have different managers at different location to pull those information. So pull those MIB information related to network management. Now if you put too much load on a network device, means all the time they are giving so much information to all the managers, there are chances that the CPU spike will be very high. So there may be issues related to CPU, maybe issues related to memory, maybe issues related to congestion. So unnecessarily do not burden your device with full MIB, and that's one of the thing that even the best practice, that we can cut down the MIB database and we can create views, and then that view access will be um, through, or that view access through the community string or through the community, or sometimes we are referring community as a password as well. Then we can have the read and write permission. So 3 things: define the manager with ACL, or maybe if you have only 1 or 2 manager, then simply you can go and give the manager IP. Define the view if it is required, if you are facing issues related to a spike, CPU, etc. And then we can go and give the read write permission to the community. We'll see that in the lab section, that how this configuration template look likes. Now you can see that's very easy: SNMP server, community string, view, read only, read write, then ACL number. If you want to shut this down means if you want to remove the SNMP, you can go and use no SNMP server community. Again, we can go and check show SNMP community. Now if you want to give that notification message in terms of trap, so for that we can go and put these configuration here. Either we can go and use trap or inform. So here we can see the configuration is SNMP host ID, trap, inform, version 123, auth, no auth, priv, etc. Alright, so in case of version 3, again it belongs to user, or users belong to group, where we can have authentication and encryption. So we should go and define the group as well. That's why you can see here that we have SNMP server and group, and then group name version 123, auth, no auth, priv, that we have already discussed earlier, and notify and access list. Again, you can go and check with show SNMP group. So let me quickly log in to the lab devices, and let's perform the lab task related to SNMP. Here you can see the lab setup. So I have a switch, actually all these devices except this SNMP server. SNMP server is my local system where I have put the SNMP server. And then I have this host 3. This is nothing but a router. I have made this as a the display is like host, the laptop or a PC. These are connected with the Ethernet port with the router, where I'm using the Ethernet switching capability. Inside VLAN 2, I will go and show you the configuration for this switch 1, that is again the router. Just for the simulation, I have made this as a switch. So let me quickly show you the configuration for switch 1 interface F1/1415, and then the IP addresses of these host, so host 3 and switch 1. Obviously this is going to be my SNMP server. So what I will do, that I will go and pull the information. Okay, so let me show you all those things. Obviously we have to do the configuration for SNMP as well. So here I have, you can see I don't have SNMP configuration at this point of time that I want to put. And with this host, if I go and check show IP interface brief, what IP it has. So here you can see that I have interface 1/15, and who is the gateway? Gateway is .2, and where is .2? So that we can go and check where is the gateway. Gateway is the VLAN 2 actually. So here you can see that do I have VLAN? Switch 1. I don't have VLAN that I want to make it. So how I can do this? Say VLAN database name if I can give, or maybe we can give like this VLAN 2 name just. All right. Let us perform the lab task. Here you can see in the lab that I have one SNMP server that is again I'm going to use as a manager. And then the switch one that you are seeing here in the diagram, that is actually router 1 that I'm going to use as a agent. And then from this host, I will go and generate the traffic. This host is also one router. I have made this to look like as a PC. Okay, so what we can do first of all, let me show you the configuration for host 3 and switch 1, because anyways this SNMP server is my local system where I'm doing the recording for this session. So let's go and open the CLI. Here you can see this is actually the switch. So let me go and change the name. So this is the switch one I have, and if I can show you the gateway for all the PCs belonging to the VLAN 2, we can go and check show VLAN and then switch. Here you can see that I have VLAN 2 and these two interfaces, 1/14 and 1/15, they are belonging to the VLAN that is VLAN 2 that you can see here 14 and 15. So the manager and the host, they are belonging to the access VLAN 2. Alright, so what we want to do here, I want to do the SNMP configuration for the switch. So I can go and do the SNMP configuration, say SNMP server, and then I can give the location. So for example, ABC, then SNMP server, the chassis ID, and then SNMP server. We have the connection or something, contact. So here you can see contact is okay. And now you can go and check the show SNMP server or show SNMP contact or something. So these things we have seen. You can go and check this thing, contact, and then the chassis ID, etc., etc. What configuration we have done so far? Show run section SNMP. Now I have one template configuration. So here you can see some old configurations are also there. But here you can see that we have the template of configuration that I can copy and paste. Here in this configuration, you can see that the host that my local system has this particular IP, and I'm using the community name is this RATNESH. Again, I'm going to create one ACL, and inside that ACL, whatever IPs that I have, I'm giving read write permission. Okay. So like that, we can go and do the configuration. Even you'll find in the configuration, we have more a number of traps and what is there in the ACL. So I can go and show you this access list where I'm giving permit any, but we can have the list of the managers in the ACL. Okay. So here you can see this configuration looks like very straightforward, and then we can go and verify it. Okay. So how we can do the verification? I have one SNMP manager engine installed in my system. I can do the SNMP walk. So I am inside this particular folder in my local system, in my Windows system, and then I can go and do the SNMP walk. Here you can see snmp walk.exe. Then you can go and give the version. That version is 2, and then I can go and give the community and then the snmp manager IP. So that is 192.168.56.1. And now here you can see on top that the new window is coming up where I want to use the port, the timeout, the snmp version. Obviously I should go and give the agent address. So my agent address is 192.168.56.2. That's the IP of the switch VLAN 2. I should go and give the community like this. Now here you can see this is the root OID. I can go and do the scan. Once I do the scan, you will see that it will go and download one text file that I can open and I can show you that. Now, important thing here is that when we are doing this NMP walk, we should not have blockage for port number 161. Alright, so I disable the firewall port in my local system. And now if I want to ping from here to my agent, that's again the switch we have in between. So you can see that I have reachability. So that means that I can go and do the walk. I should go and change the IP 6856.2 and then the string, that's the password. Scan. Now you can see the OID started scanning. And because we are using the root OID, although we have option that we can go and give the string as well. So here you can see that we have this output saved. Let me open this output. Let me open this. Now here you can see this polling, or you can say that this SNMP walk. You can see the OID and what it is doing. So we have the complete output related to interfaces. Let me scroll down. You can see the IP addresses. So we have interfaces, we have IP addresses, the status of the interface, but you can see that it's a long output we have, and that's the power we have with SNMP version 2, that it will go and take all those information that we have, although we have used the root MIB or OID to get this information, but it depends that what exact information you need. According to that, you can go and put the filters. All right, so this is the way that we can go and run the walk. We are going to do a quick revision about the configuration of various versions that we have. We have already studied that how we can go and configure the important version, that is version 2, and C stands for community. Here you can see that it's a straightforward. We can go to the global configuration mode. We can do SNMP community public. Again, it depends that what type of community is string I have, public, private, or if we have any type of restriction, we can go and use with certain ACL as well. So again, here you can see that you can go and give the host version 2C and host version 1 as well. If you want to limit the number of managers, you can go and give even the permission as well. For example, read only or read write, and then mapped with the ACL 4 where I have the group of the manager. Again, we can go and enable various type of trap. We have a long list of trap or notifications that we can go and enable. We can go and give the host in terms of DNS as well or URL as well. Now again, we have the use case related to version 3. We know that version 3, where we have the group or the users belonging to the group. We can have option if we want no authentication, no priv. That means that we want a user-based SNMP version 3 configuration. So here you can see that you have to go here and define the group. So SNMP server, group 1, version 3, no auth. And then we can go and give the user as a remote user part of group 1, and the remote uh, server is 10.12.8.4. Then SNMP server host, and there we have the informs version 3 with no auth. Again, the remote user config. So we can go and give the configuration like that. This is the case with no auth and no priv. Again, if we have case related to authentication with no priv, so again we can go and define the group with auth, and then auth user group remote version 3 auth MD5 password. Correct? Now again, if you have option or if you have use case that you want to give the priv security, so again we can go and define one group with the priv, and now I have the private user with group 3 with this remote location version 3, and again we have the authentication and the priv access. We know that the encryption that we are using is days 56 bits of encryption with days algorithm. Okay, so here you can see that it include everything, that it include auth and priv. You have the authentication, so here you can see auth MD5 password, and then you have the encryption as well, like priv access for this particular user, that is the private user. Okay, so this was the summary that what we have studied so far. In next section, we have to go and study about the syslog, and we have a small lab related to syslog. Over the network devices, we are getting the log messages. Now we have the buffer limit in the network devices. So what we can do, that we can redirect these log messages to the remote logging server. And again, we can use any industry standard remote log server. Now here, one important thing we have is that we have different type of log messages. So what different type of log messages we have here? You can see that they're starting from emergencies going to debugging, level 0 to 7. So these type of log messages we have, and it is up to us that what type of log messages we want to see over that remote logging server. To set up that, we have option. We can go and use logging, and then the server name where we want to send these log messages. We can go and do logging buffer as well, means how much you want to buffer in your local system, how much you want to redirect. If you want to redirect all the messages, it's fine. We can go and redirect all the messages to the remote login server. Now, once we do that, at that time they are using the syslog messages or syslog server. The communication channel is over UDP port number 514. So if in between we have any ACL or any firewall who is blocking this port, we should go and unblock it. Now, if you want to see that log message is in different timestamp format, then we have option that we can go and use service timestamp log datetime, service timestamp debug datetime. So these commands we have to set the log message in millisecond, and it will show you the time zone as well. Now again, some of the commands, if you want to go and check the logging history, you can go and set the label here. You can see uh, by default, it is showing warning, error, critical alert, and the emergency. So here you can see that emergency alert, critical warning, and errors. So from 0 to 5 it will show. If you want, you can go and set the history label. Even we can go and set the logging history size as well. Okay, so let me quickly log into the system, and in that system let me show you that how our lab look likes. In my local system, I install DNS, and here you can see that you have your server, you have your host, and you have your switch as well. So what I have done, to examine the syslog message. Over the server, I have installed this TFTP, Jonin TFTP server, and inside that you can see that you have syslog server option. So if you go and click, at the moment we don't have any log message, so it is not showing anything. I can go here and I can set that. So I can go to the switch and I can give logging, and this logging I want to the server, so I should go and give the server IP as well. So let me show you these things parallelly, and here you can see that you have your syslog server. So I can go here and I can give logging 192.168.56.1, and then let's see that what other options we have. So if I can do logging buffer, and here you can see that in the buffer also we can go and give the label of the severity starting from 0 to 7. So I can go and give, say for example, up to 5, and here you can see this 5 is warning. Apart from that, if you go and see that what other options we have multiple options with logging, and we can see logging and then question mark. Here you can see that you have options. You can give the address for the remote login server. Buffer, you can go and set the logging buffer. Then exception facility, filter history. Here you can see that you have logging history, host, monitor, etc. So we have multiple options here. If I want to set the trap, and then again if I go and set the informational logging, and then here you can see that you have history. So logging history, and then here I can go and see set the size, history size say 200, and then finally logging history, and the message is say for example informational. Alright, so once we have this log configured, we can go and check the logging, that what configuration that we have put. Here you can see these are the things that we have put. Now if we want to see this in the syslog server, so here you can see it has been started and it is stored at this point 192.168.56.1, and we should get that information over here. So let me go and set this syslog. So if I go to interface 1/5, and if I do shutdown, so we should see here the syslog messages. Here you can see that now it is showing over the screen, but I want to send this, and we should have the communication between my system and the logging server, which is not at this point of time. So let me see, 1/15 is down. So what I can do here, that I should bring up that interface 15 no shutdown. They should be up, otherwise there is no communication in between my log server and my local system. Alright, so we can go and check the log configuration. First of all, it should be correct, and if I try to ping, it's not reachable. If I go to the system and if I try to ping from there to my local switch, let's see if I'm able to ping. Yep. So in between, if we have any firewall rule which is blocking the port number, it will not work. We should check, we should disable that firewall or allow that port at least. All right. So meanwhile, we can go and check the logging message here. And in the local system, you can see that we are getting some sort of messages. So what it is telling, let us see in the local system. Logging to this, audit disable, link is up, filter is disable, and here in the local system we can see that yeah, we are getting the log messages. You should get this in the remote server as well. In my local system, I have disabled the firewall rule. Now you can see that from a switch, I'm able to ping to the TFTP server. Now let's try to generate the log messages. So I can go here to the interface 1/4, and if I do the shutdown for that interface, so at the moment it generates the log. Here you can see in the remote logging server, we are getting the log messages. Now if I go and do the no shutdown, again you will go and see that the log messages will come to the remote logging server. So this is the way that we can go and check the log messages. Next important topic, we have net flow and flexible net flow. Now, as the IT evolve and as we need to analyze more and more data with respect to security analysis, with respect to troubleshooting, with respect to network analysis, we need to learn and understand the flow or the record. So for that reason, we have NetFlow. And again, if you see the versions of NetFlow, you'll find that we have NetFlow from version 1 to 9. 5 is most important and actually most popular. Uh, Now, what's the difference? You will see the main difference here is that in version 1, we have less capability that we can analyze less number of field in the flow or the traffic flow. Rather than if you go and see, say for example, version 9, where you have much capability to analyze the flow, means we have much more option, much more capability to see inside the flow, what type of headers and fields we have. We'll see that how many fields that we can analyze inside a flow in different versions. Now here you can see that, so for example, you have source and you may have destination, and then you are using net flow. So what are the things that you can check? Uh, Again, we'll see that we have multiple options to verify, but at least we can go and check the IP addresses, source and destination, the port numbers, source and destination port, protocol, packet send, packet receive, if you have any tagging related to source and destination, and then various TCP flag. Now this information is huge because this is going to answer us 5 different Ws. So who is sending means what is the source and destination IP, what's the port, where it is sending, what is the destination's IP, so who and where, again related to the addresses, what they are sending, so which application they are using, what are the port numbers they have, so who, where, what, how, again you can see that how many packets or bytes they're sending. So here you can see the packet counter, the byte counter, and when they are sending, that's the time stamp, at what time this transaction happened. So again, we are getting 5W answer: who, where, what, how, and when. And that's important to do the analysis with respect to either security or network analysis. Now again, if you want to correlate this with the phone book, again you will get to know that net flow equal to the flow. Inside that flow, who, what, where, when, all these informations we are getting with respect to flow. Now the next important question is that which version should we use? Again, we have version 1 up to 9 and 5 is most popular. So here you can see that, for example, in the popular version, that's version 5, what are the content and again the description. So we can go and check the addresses, we can check the next hop, the SNMP index, packet flow, total number of L3 byte, system uptime, TCP UDP port, if you have any flag. Again, you can see these key information. Again, the argue is there. So still the version 5 is not giving us each and everything inside the flow. If I want to see more and more number of fields, then what version we should use. So here you can see in this chart that version 5 is giving only 18 exportable fields. There are some limitation as well, that they are fixed with IPv4, they have fixed level length, single flow cache. Okay, so there are advantage with version 5, but there are certain disadvantages as well with version 5. Then we have version 9. Now version 9 is template based, it is much more robust, it can have the MPLS and BGP supported fields as well. It is going to support 104 fields. So you can see 18 versus 104 fields. But again, it has limitations that IPv6 flows are exported inside IPv4. Fixed length field use more memory, slow performance, single flow cache. So you can see, although you have ease of use, but on other side, it is consuming much more resources. So if it is easy to use, it is giving less number of fields. If we are using more much robust uh, options, then at the rate of high memory and slow performance, etc. Okay. Again, we have the flexible net flow, that is again using version 9. So you can think that version 9.1 or 9.2, that's a flexible net flow. This supports flow monitor, supports selectable key fields for IPv6, supports NBAR. Again, this NBAR network based application recognition protocol, and uh, even the Cisco who has made this NBAR, uh, just to analyze the application, and I have given so much theory related to NBAR in my SD-WAN curriculum, because if it is a Cisco device, so for example ISR or any type of Cisco device, at that time uh, NBAR 2 can recognize the metadata of application, and they can recognize up to 1400 or 1400 plus applications, rather than the other vendors. Also, they are claiming that they can recognize more and more. But again, we can recognize the application with the NBAR, and in this NetFlow, these are supported. In this session, we are going to learn about the terminology, and we are going to learn that how we can collect all these pieces, and then we can go and configure the NetFlow as well. So let's start. First of all, flow. We know that we are going to analyze the traffic flow. So whenever I have a flow, obviously that particular traffic flow or flow having various type of key and non-key. So what does it mean by key and non-key? We will go and understand that. But at this point of time, we can think that there may be some mandatory things. There may be some optional things that we want to collect or measure. Correct? So according to that, we can categorize these as a key and non-key, that we'll see. Starting with flow, they have the key field like source, IP destination, IP port number, protocol, etc. Then we have the flow record. Again, the record, you can think as a office and file system. In a file, you're putting all the records of all the customer or clients. So like that, you may have a record what you want to collect. And this record may be key values, this record may be non-key values, or mix of both. Correct? So generally it is key plus non-key value that is there in the record. Then we have flow collector, where you want to collect this flow. What is your destination server? That we can go and give the collector IP. Template based configuration, nowadays we are using, even if you go and check the SD-WAN configuration, inside SD-WAN we have, nowadays we have option for NetFlow plus the SD-WAN own cFlow template. So both the things are there. There we need to create the template as well. Template is again the format where you are putting various parameters. Then the exporter is nothing but you are going to collect the information, and you have the exporter where you want to analyze all these things. Finally, the NetFlow generator, that is nothing but who is going to generate the flow? That's the devices to whom we want to analyze the flow. Okay. Now again, all these terms, when we are going to do the configuration, at least when we'll see the configuration, we'll find that where we are going to use all these configuration options. The traditional NetFlow configuration is very easy and straightforward. What you have to do, that you go and first of all define the export version, then who is your destination and the port number. So destination IP and the port number. This IP is your NetFlow collector IP, maybe any type of server. Which interface you want to enable? I can go and use IP flow ingress. I can go and use IP flow egress. So both options are there. Let me quickly log into the device and let me show you that how you can go and do these configurations. So here I am. I can go to the flow export say version, and here you can see that we have 1, 5 and 9. I can go and use 5. Then IP flow export destination, I can go and give 192.168 say 56.1. That's my server, and then I can go and give the port number say 2055. Then I can go and check the interfaces. So I have interface say for example 15, and I can go and use IP flow, and here you can see that we have option. First of all, I should make this as IP interface, because by default it was the L2 interface. And then I can go and use IP flow ingress. If I want, I can use IP flow egress as well. We can go and check the configuration, and if you want to filter, you can use the flow option. So here you can see that it's very easy and straightforward that you can go and do the configuration for the traditional net flow. Now the next very important thing we have is the flexible net flow. Most of the places you will see that we are using the flexible net flow, and the key term there is that you should know that what is your key item versus your non-key item. So we have the mandatory and optional things. Anything that will start with match option, that will be the key field. So TOS, type of service, protocol, source address, destination address, port number, etc. Then anything that is collecting, that will start with the collect option, that will be the non-key item. Correct? So TCP flag, byte long, packet long, absolute first, etc. Again, this also if you want to do the configuration. So now you can go and give IP flow and what version you want to do here. So IP flow export version, say for example 9, and then we can go and use flow, and let's do the configuration for this as well. Say for example flow record, and we are inside the sampler, say match, and so here we can see that with this particular version, and here you can see the version of the image, the 12.4, flexible net flow is not supported. So what we'll do, that we'll check this configuration in the other version where we have the FNF support. So here you can see that you can go and create the flow record. Again, we have learned that NBAR2 is supported inside version 9, and whenever we have this network-based application recognition software or the feature, nowadays Cisco has launched the NBAR VM as well, that you can check inside SD-WAN software module inside Cisco software downloads. So now we have this feature to analyze the application how actually it is analyzing the application. So here you can see that whenever the traffic will go and hit the router or the device where you have enabled the ENCOR capability. So suppose someone is surfing the website and then the packet will go and hit this device and ENCOR is enabled as per this record. So here you can see that flow record has IPv4 source address, destination address. The key thing here is that they are matching the application name as well. So once they have the application matching criteria enabled inside the net flow, then they can go and hit and match that application. And in the flow, certainly you can go and see that you have the source IP, destination IP, everything, and then you have the application matching name as well. Okay, so that's the power we have with the integration of NetFlow with flexible NetFlow with ENCOR. Okay, so ENCOR is giving us much more visibility inside the flow of that particular traffic. All right, so how we can go and configure here, you can see that you can go and create the exporter who is your destination where you want to export. Then you can match the key and non-key items like match and collect keyword. Then inside the monitor you can call point 1 and point 2, that is the flow exporter and flow record, and then obviously you should go and apply over the interface. Okay, so these are the steps that we can go and use to enable the net flow. Now there are some use cases. The point here is that at what particular point and how much match statement we need, how much collect statement we need, and that depends upon what exactly we want to analyze. So for example, in client and server communication, here you can see that for the client server state, you can go and match the DHCP protocol, addresses, source port, destination port, and in the non-key item, the interface output, bytes, packets, plus the application name. So here the application name, we have the account on resolution. Again, this ENCOR, it is showing the capability of ENCOR, that is giving you the visibility for the application to check the application flow as well. Now we have complete replacement for IP accounting keyword, where you can go and check which IPs are using how much volume. So here you can see that we can go and use this IPv4 DHCP bytes long. So that's the counter bytes long, counter packet long, and then they collect application name. So we have application visibility, and then we have the IP accounting, and then we have the DHCP matching as well. If you want to analyze the QoS queue hierarchy for QoS, so this is the QoS configuration. We already know about QoS. We have learned about that. So you have the parent and you have the child policies. Inside child, you have the class map like this, and inside class map, you are matching certain DHCP. Now, how inside the flow we can match it? So again, in the optional field, we have an option that we can go and collect the policy and QoS policy, QoS queue, and drops. Again, this is just for the reference that how the protocols fields are getting matched with which type of FNF statement. So we can go and collect the application called SNMP, server, sender, POP, NNTP, SIP applications, HTTP applications. So we have long list of application matching criteria that we can go and check inside the flow. Now, how it is working behind the scene, here you can see that in any of the flow, they will go and extract the URL, the agent, the application refer, the application HTTP host. That's the capability, and that's the visibility we have with respect to ENCOR. And finally, we have one example here that you want to have this record option. So here you can see this flow record, and in that record what you want to match. So you want to match the data link MAC, the destination data link MAC, VLAN, TTL TOS, protocol, source address, destination address, and then finally you have the optional, that's the key and non-key option as well. Those things you can go and match. Now let's see that how we can go and do the configuration for flexible net flow. I'm running 15.0. So first of all, I can go and give the exporter version, and then we can go and create the flow, and then we have this exporter. So let's do that. Say flow exporter my exporter, and then I can go and give the destination, that is my local server, as a destination. Then we should go and create the flow record. So for that we have flow record, say my record, and then I can go and match various parameters. So what is the destination address, then match. These are the key values that we are matching here. Source address. Again, you can see that with match option, what are the things we have. So we have the option to match the application as well for the N bar, and I can go and use the match and then the application name, and we can leave it. So system will automatically understand that which application is going, and it will go and match. Again, you can see that inside the match you have application, data link, flow, interfaces, IPv4, IPv6 routing, and the transport as well. Say routing destination, you can see that we can go and match the AS and the traffic index as well for the BGP. So we have these robust options related to match. Then we can go and use the collect. Inside collect, we can go and use the counter for byte, counter for packets. Again, you can see with the collect option, we can go and collect the application and then the name. Now flow record field is already present. So already we have given this field in the key. So it's not required to give in the non-key as that we have already defined in the key. But you can see that we have options related to non-key item as well. Some of the options are there in key as well. If you define in the key that has a higher preference, that will not go and take in the non-key. Alright, so once we define the flow record, then we can go and create the monitor, and inside monitor we can call all these things that we have created earlier. Means we can go and call the exporter, that is my exporter. I can go and call the record, that is my record, and then finally you have to go and apply this monitor over the interface. So I can go to my interface, and then I can go and use this monitor word, that's my monitor, in the input direction, and it is taking a while because we have enabled the applications as well. Whenever you are enabling the N bar, that's indirectly the application, it will go and take some time to apply it. Once it is done, then we'll get the line. So these are the things that we should go and check and enable. So define the exporter, define the record, call inside the monitor, and then apply it. I can go to the output as well, and then we can go and check show flow monitor. If you know what is your monitor name, you can go and give the monitor name. Okay. Apart from that, we can go and verify the flow interface. If I know the interface name, I can go and check. Then we have the flow record. If you have multiple records, you can go and select, and you can selectively go and check this. Okay, so this is the way that we can go and enable the flexible net flow. Next important topic we have that capture the packet at the level of data plane. For that, we are using the popular technique, that is switch port analyzer. This is nothing but a technique that we can mirror the port, or we can send one copy of the traffic that is going via the port to certain destination. So here in the diagram, you can see that we have source for the span, means the traffic is coming, and that traffic we want to copy and we want to send to certain destination. So for that, you have to define the source, and then you have to define the destination. Now at the destination end, we can use again the popular tool such as Wireshark to analyze the traffic that will go and verify in our lab section. Now adding span in our tool belt, we have other option with a span as well. Suppose we want to do, or we want to take the copy in case of remote, or we want to have the capture for the remote packet, and that remote packet is layer 2 extended. So in that case, we can go and use the remote span or remote switch port analyzer. Again, you can see that same thing, that you have the source, but you have the destination, and you are extending over the layer 2 domain. Then again, at the destination end, you have the sniffing tool where you can go and analyze the packet. So we have option related to a span, related to RS span as well. Now here you can see the configuration that is quite straightforward. And again, we are going to have this configuration for local span. So you have to go and define the monitor session. What interface is your source? What interface is your destination? And that's it. Then you can open the sniffer and you can check the packets that is going through. Now, in case of remote span, you have to go and define the VLAN for remote span. And again, you have two configuration. You have configuration related to source. Then you have configuration related to destination. So at the level of R span source, you have to go and again enable the monitor session 1 source, monitor session 1 destination. Then at the destination end, again you have to define the source and the destination. Now in some of the switch platform, you have different type of configuration. In some of the switch platform, you have different type of configuration, but obviously the end goal is the same. The last flavor we have is the encapsulated remote span. So here you can see the difference between RS span and ERS span is that one span section you are extending over layer 2, and other, that is the ERS span, you are extending over layer 3 domain. Correct? So in this case, for example, I'm using GRE as an encapsulation. Again, I have the ERS span source and ERS span destination, but these packets that I want to analyze, it is expanded over the GRE session. As we discussed earlier, that for ERS span, we are encapsulating the traffic over source and destination IP with the ERS span. So here we can see the configuration for router 1, where we have to go and start the monitor session, type ERS span. We should define the source interface and the destination addresses. From the other side, where I have the destination, where I have the Wireshark, at that side of router, we should go and give ER span destination, the destination interface, and then the source, ER span ID, and the IP address. Okay, so this way we can go and capture and then analyze the packets that is coming from the source we are sending to the destination, where we have the sniffer, and there we can analyze the packet. Now in this lab, what I want to show you is that how we can go and do the configuration for the span. So one of the interface that we want to create the mirror or the copy of, that we'll go and send those copies to the server. So for example, let me show my diagram. Let me share my diagram. So here you can see that I have one switch, and then I have one host connected. What I will do, that this particular interface, so let me show you the interface. 1/15, this will be the source of the traffic, and then I will send this to the 1/14. That will become the destination for the traffic. So let me quickly open the CLI. Meanwhile, you can see the configuration is very straightforward. For switch, we have VLAN configured, and then for the host, that is also a router, but we are treating this as a host. And here you can see the IP and the configuration as well. Now if I ping from here to the switch, that is 192.168.56.2, so you can see the reachability is there. Even I can go to the switch, and if I enable the line VTY say login local. So we can go and check the TCP packets as well if you want. And then I should go and give say username admin, password admin, say enable password is also admin. So not only that we can go and test the ping packets or ICMP packets, but we can go and check the telnet packets as well. Now in the same line, if you're at the line VTY level, and if you want to check the SSH traffic, so you can go here and you can do input output as a SSH for example, and then you should have some IP domain name configured, and then you have to generate the crypto key and say 1024. So once I have the domain, once I have the key, once I have the transport input configured, then I can go and give the version as to. So I can go and verify the SSH as well, correct? So let's go here to switch number 1 and configure this monitor. Say monitor session 1, what is your source? Source interface is fast ethernet 1/15. And likewise we can go and give monitor session 1. The destination interface is fast ethernet 1/4, 14 where you have connected the sniffer. So here you can see the configuration. Again, we have seen this that with different platform your configuration may vary, but the concept is same. You are mirroring from one place and you are sending to the other place. Now here you can see I have my Wireshark and I can go and start my capture. So continue without saving. Some other traffic capturing has been started. Alright, so let's go here and first of all, let's do the ping for some bigger number. And then I can go here and I can check show monitor session 1. You can see this is the configuration. Now if I go to the Wireshark, here you can see this is at the server end as per our diagram. Here you can see that here we are sending the span session, and yeah, we are getting the packets. I can go and stop this. Now you're getting this ICMP request and response. If you want to filter it, you can go and filter and you can analyze this. There's no problem on that. Now let's try to get some packets related to telnet and SSH. So still this ping is going on. I should go and stop this. So let me stop this sequence. And then if I do SSH 56.2, and let me go here to the Wireshark. Here you can see that we have the packets for SSH, and yeah, we are able to capture. You can see the encryption and all those things, correct? So likewise, we can go and analyze all type of packets. Right, so we are inside switch number 2, and here you can see your SSH and packet transmission is happening. All right, so this is the way that we can go and enable the span, and then we can verify it as well. Next important topic we have Cisco IP SLA. Now Cisco IP SLA is a mechanism in the existing WAN or in the existing network that is giving us the capability that dynamically we can track certain services, certain IPs, and according to that, dynamically again it can change the path. So suppose if your primary link is down, then you can go via the secondary link, or there is other option as well related to loss, jitter, latency, etc. So let's try to understand this IPSLA workflow, how it is working. We're going to understand about IPSLA, its operation, and then obviously we'll do the configuration and we'll verify as well in the lab. Now, what features that IPSLA provide us? Here you can see that with help of IPSLA, we can go and understand and collect the parameters related to loss, latency, jitter, packet sequencing, path per hop, how it is going, and the connectivity. And according to these parameters, we can go and change it dynamically, correct? So how it look like, how we will go and configure it. We should go and enable the IPSLA. So for example, IPSLA1, I want to check this particular destination. So what I can do that, so for example, I can send uh, the ICMP echo packets just to check that this destination is there or not. And suppose if I have multi-path, so if one path is down, automatically you will go and then uh, because one path is already down, you can go via the second path. That's the overall idea behind this. So this frequency 5, that is the overall rate that we are sending the echo packets to the destination, that is 1111 in this case. We have started this IPSLA and it is a start now, and maybe we can give forever. So life forever is started now. And finally, we have to glue this with the tracking. So again, over the configuration mode, we'll go and enable the track 1 for IPSLA 1 for reachability. So what this track will do, it will start tracking this particular destination with the ICMP echo packet. Now how it is working behind the scene, again we'll see in the lab that for IP route, with IP route actually, I have two IP route statement. We know that by default IP route has a higher AD value with respect to any other protocol, and then you can give some bigger AD value, say for example 30. So the best one is the first line. It will go and hit the first line, so this will be the primary, and then you have enable the track on this. So primary path with tracking, that is ICMP echo of frequency of 5. That means if this track is down, that means if destination is down, obviously you will get this track is down, you will start going via the other link, correct? Now once you do this configuration, then we have the verification command. We can go and check show IP SLA application, SLA configuration, history, and stats. So let me quickly show you the lab setup. So here you can see that we have the lab setup, and in this lab, say for example, this is my source and 111 over R1 is the destination. You can see that I can reach to R1, loop back via R2, and then I can go and reach via R3. So what configuration I have done, obviously we have the IP assignment to all the interfaces, etc. Let me quickly go and open the putty. So I just wanted to show you here that what configuration I have for router number 1. So for example, at the moment the IPSL is not started, and you can see that we have the IP route command, and we should go and check this R4 because R4 is the source generator. So I can go here and I can show you this. Let me quickly show you this IP route configuration. At the moment it is 3040, so this is the preferred and this is the backup. Uh, Again, it depends upon what type of IP route statements you have. So what does it mean at this point of time with this statement is that 34.3. So this path, because you can see the IP assignment here, This is the IP, and then the IPs over these interfaces are of the range of say 24.0/24, and here the IP address is 10.1.34.0/24. So these are the IPs we are using. Router 2 means .2, router 4 means .4, like that we have the IP convention. Alright, so now here you can see clearly that with this rule, if I do the trace route for the destination, obviously it will go via R3. And now if I go and change this, say for example this statement to 50, and if you check this now, so that means this is the lower, the traffic will go via this direction. Okay, and that's the case. What I want this traffic should go via this direction, and we should go and track this with IPSLA. So I can go here and I can enable say IPSLA 1, and then I can set the frequency and other stuff. So let's see that what are the other things that we can go and set here. So now you can see that once you go and enable the IPSLA, you have this ICMP echo. What is your destination? You want to check this, and to send the packets you can go and use the frequency, so for example of 5, and if you have any timeout you can go and use the timeout 1000. So what does it mean? That within 1 second, so its default is 5000 millisecond means 5 seconds, so frequency is 5 means per second you are sending one ICMP echo packet. Great. So once we have this, we should go and start this. So here you can see that IPSLA scheduling and a start time is now, and then the lifetime is forever. Correct? So once we have all the configuration related to IPSLA, we should go and enable the track as well. So what is that? Track, say 1, and then what you want to track, say IPSLA 1 reachability. Correct? Now since we have all this configuration, we should go and apply this track to the IP route statement. So what I can do here, first of all, let me delete this, otherwise you will find multiple entries. Now I can go here and then I can give track as 1. Now the track has been glued, and here you can see this track is glued with the IP SLA. Even you can go and check the route. So you have 2 routes now. One is the primary, one is the secondary, obviously with the tracking. So now if I go and check show IP track, or let's try to check show track 1, and here you can see this track is up, it is working with a static IP routing. Now what we can do here, that we can go and shut down the interface, any of the interface that will not allow us to reach to this destination. So for example E1/0 over R2. So I can go here, interface E1/0, I can do shutdown, and then you can go and check the output here on 4. So now here you can see this is track is down because in this direction we have the track. And now if you go and check show IP route, so you will find that the static route entry, so you have seen both. Now it is via 34.3, and it was, and the track is also up. So this is the way that we can go and verify the IP SLA.